Hello everybody, welcome to the Introductory Rust course. In this video, I'm going to show you the features of Rust language, and I'm also going to tell you a number of things to learn for Rust language. Before I tell you the content of Rust language, I have to show you a number of advantages of using Rust language. The first advantage is the memory safety issue. By using the ownership system that the Rust language has, we don't need to use the garbage collector. Also, the null pointers and the data races can all be avoided by using the ownership system, so we can see that the Rust language can achieve memory safety. The second advantage of using Rust is that we can handle concurrency and parallelism quite easily. The combination of the ownership system, threads, and message passing all together could help us minimize the deadlocks and the data races. Also, the third advantage is the performance issue. Rust can focus on the low-level control and zero-cost abstractions so that we can make the performance comparable to C and C++. So Rust is a fast-running programming language, as fast as C and C++ in general. The fourth advantage of using Rust is the cross-platform compatibility. Rust can be run on Linux, macOS, and Windows. The package manager called Cargo can make the managing of dependencies and cross-compilation quite straightforward. Number 5, the community has already written a lot of great documentations, and the official package manager called Cargo can provide us with access to a wide range of libraries and tools, so we can make and build our applications quite easily by calling the libraries provided by the community. And my course is going to rely on two major sources. The first one is called the Rust programming language, which is also called the Rust book, and the hyperlink is already here. Okay, this is the Rust book. This is a book that most learners of Rust should read beforehand. And I'm going to use this one as the major source of my reference. Also, the other major source that I used is this one called Rust by Example. So the content is shown here. This is also a very good source of learning Rust. So you can just click on any one of them, and you can just play with the code on the browser. And if you can run the source code correctly, you can see the effect that will be shown on the screen directly. And of course, if you have got some errors, you can just see the error messages at the bottom of the page. Okay, so these two sources are quite helpful to learn Rust for beginners or even for advanced learners of Rust. Now, let us try to run a Rust project with Cargo. Cargo is the Rust programming package manager, and it is also the build system for Rust. So we can use Cargo to compile the files, to build libraries, and to add dependencies. So let us try to create a simple project. The idea is to use this command, cargo followed by new followed by the project name. Okay, and then I can change the directory to the project directory. So I already have a folder called Rust course, and in this folder I'm going to create my project folder. Okay, it is already created. And then I'm going to go to the project directory, and then we can go to the Explorer, and you can see that the project is already created. And when I click on it, you can see a number of things. For example, the source code folder, and in the source code folder, I have a file called main.rs. But that is the file that Rust must play with when we run a program. So this is the main thing to run. RS here means the Rust extension, okay? And we can also see a TOML file here, okay? The TOML file means the Tom's obvious minimal language. So what does it contain? It contains a number of things. We have the package name. In my case, it is just the project name. The version here means the version of the package. So the current package is set at 0.1.0 for my current project. And addition here means the addition of the Rust language that I'm using. I'm using the version of 2021. That's why I have 2021 as the addition. Also, the dependencies are going to show the list of project dependencies. Since I'm just doing a Hello World program, I don't need to depend on other modules to help me achieve this task. That's why this part is empty for now. So let us go to the RS file. And you can see that I already got a Hello World program by default. So fn here means the function, and main here means the main program or the main function that I'm going to run when I execute the program. So the program has one command, print line, exclamation mark, and then hello world. Exclamation mark here means that I'm having a macro. So macro, this is a macro. And print line macro wants to print the content on the standard output or on the terminal. So we can use this command to print out this string slice. Okay. So before I want to execute it, I have to build the program first so that I will have an executable file. So how can I do so? I can say cargo build. Okay, you can see that I have already built a project, and since I'm using the debug mode, you will be able to see that the debug mode is activated. So if I don't add anything after the word build, I will just use the debug mode. The debug mode is a bit unoptimized compared to the release mode. So it doesn't matter for our current project because this program is just a simple demonstration. So if you want to build a program in release mode, you just add 2 minus signs followed by the word release. Okay. So you can see that in the debug folder, I have got my project file that is already the executable file already obtained from the building process shown above. Okay. So we can execute the build file on the terminal. For example, when I use the terminal right here, I can just go to the location of this file. And then I just run it. Okay, you can see hello world has come out. Okay, hello world has come out, which is just the content shown here. Okay, so the program can be executed after I have built it by using the cargo build command. Okay, so if you want to have the release mode to be built, you can add more words after the build keyword. Okay, is it possible to build and execute together? Yes, it is possible in Rust. We can build and run the executable file in just one command by doing cargo run. So let me try to do it now. Okay, you can see that I have already built the program for the second time, and I can just show the hello world as the answer to the programming result. Okay. And you can notice something right here. If the source code has no changes, there is no need to rebuild the code. So I can always just go to the terminal and play with the program again and again. Okay, so you can see that I haven't compiled the program again to run this executable file because it is already built. I can just run the originally built version of the program to get hello world again right here. Okay, and in the code we have the print line keyword. I already explained the print line macro a little bit. It is a macro that shows the string to the standard output, so you can see the answer from the terminal. And what is a macro? A macro is a command ending with the exclamation mark, okay, like print line here. Okay, more code will be added to the source code before compiling to do the task. That means when we use a macro, the compiler will add more code to our current code so that the printing action of this string slice can be achieved on the terminal. Okay, so this is something we have to understand. When we see the exclamation mark, we have to understand the nature of this kind of command. Now let's talk about the basic programming concepts of Rust. The first thing to talk about is the variables. So we can make a variable in Rust, but we have to notice a very important point about Rust. The variables are immutable by default in Rust. The word immutable here means that we cannot change the value of the variable after it has been set up by default. Okay, and we have to use the snake case for variables. The snake case means that all the letters are in lowercase letters, and if we want to join two words together, we have to use an underscore to help us do so. So for example, we can see the situation right here. If I want to let my var to become 1, I can use let my underscore var equals 1. So this equals sign is meaning the assignment statement. So I want to put the value of 1 into this variable name or the identifier called my var. Okay. After I have set up this my var to be 1, I cannot change the value to 2. Otherwise, I will have a compile time error because variables are immutable by default in Rust. So let me try to demonstrate this idea to you on the editor. Okay, you can see that I have read a wavy line here saying that I cannot mutate an immutable variable called my var, which is obtained by the Rust analyzer. And you can see that I cannot do so because my var here is an immutable variable by default. And I have to tell you something about the Rust analyzer. You can see that my original code was just let my underscore var equals 1 semicolon, which means the end of my statement. But you can see that the Rust analyzer helps me to add something here, which is a colon, a space, followed by I32. This highlighted part is actually called the inlay hints. The inlay hint can help us understand the data type that a variable has. So when I say 1 here, by default an integer would have a certain data type called I32. I here means signed integer. So we have a sign for this integer, which is positive. Okay, so I32 means that it is a signed integer in 32 bits, which is the default data type for an integer in Rust. Okay, so this part is the inlay hint that I didn't really type in, but the Rust analyzer can show me the inlay hint to indicate the data type that can be inferred by the Rust analyzer. The word infer here means that the Rust analyzer can understand this value and assign the data type to this variable name, okay, or what we call the identifier. Okay, so we can also see that we cannot do the further assignment because a variable is immutable by default in Rust. Okay. Okay, we can have a compile time error when we do the further assignment of an immutable variable. But is it possible to make a variable mutable? Yes, it is possible. We can use the mut keyword before the identifier. So we can change the value of the variable without altering the data type. We use the mut keyword. Okay, so let me try to do it right here. Let mut my var equals 7. And after that, my var can become 8 because this variable is already mutable by saying mut before the identifier name. Of course, when you see 7, the Rust analyzer can infer the data type of this variable name called my var to be i32 by default. So when I get 7 as the value, I can change it to 8 because 7 and 8 are both integers and Rust can treat them as i32 data type. Okay, so we have to notice that the data type has to be the same when I do the mutation of the variable content. Okay, and of course we have to use the snake case for variables. We use lowercase letters, and when we want to join the words together, we use the underscores to help us do so. Okay, remember, when I want to do a certain statement, I have to end the statement with a semicolon. Okay, and we will notice some subtle thing about the statement later on, which involves the use of the semicolon at the end of the statement. Okay, so let me try to compile it. It should be possible to compile right now. Of course, I can compile it, and of course, it is possible to run it. I haven't saved it yet, so let me try to save it again. And let me try to build it. Of course, you can see that we have some warning right here because I haven't used the variable name here in my upcoming code. So you will see some kind of warning, but the warning doesn't matter. We can still make the code compile. It can still be run. Okay, it can still be run, but I haven't printed out anything on the standard output, so that's why I have nothing to output on the terminal. Okay, so at least we know that we can compile by using the mut keyword to help me change the content of a variable. Okay. And another concept to talk about is the shadowing. Shadowing here means something like this. The variables can be shadowed by using the let keyword on the same variable name in a given scope. That means the original variable can be hidden or shadowed or covered by using the let keyword again, and we will show the example later on. By shadowing, both the variable data type and the data value can be changed. So that means after we have covered the original variable, we can change the content of the variable as well as the data type. So originally it was 7, but it can be changed to a real number. Okay, so it is possible by using the shadowing technique. So by shadowing, we are really creating a new variable that hides the original variable. Okay, that's the meaning of shadowing. We hide the original variable by creating a new variable, which has the same name as before. The working principle of shadowing is like a stack. After the shadowing has been applied, the variable is immutable. That means the shadowing effect gives me a certain immutable variable that is having the same name as before. Shadowing is quite useful when we want to change the purpose of the variable while keeping the same variable name. If we want to keep the same purpose of a variable, we can just use mute, so that I don't use shadowing to help me use the variable name with the same purpose. So the purpose here can be elaborated by this example. So let us read it now. I have a variable called month, which is equal to 11. So 11 can refer to month 11. That means November, for example. And when I have an inner scope right here, I can change the month to 12. You can see that I haven't added the mut keyword before the word month. So you can see that I also used the let keyword before a variable name called month, which is shown up for the second time in this code snippet. So here, when I use the let keyword, I'm doing the shadowing. So the original value of 11 will be covered by my new variable called 12. Okay. So the idea is like this. We have a stack. Originally, it has a value of 11 for the month variable. And after going through this line in the inner scope, you can see that the original variable of month is already shadowed by a new value called 12. And the 11 will be something like covered or put below the stack. Okay. And then I can just print it out as usual. I can show 12, of course, because it is already a shadowed value. And by using a shadowed variable, we can also change the data type in our shadowing process. So what does it mean by that? If I want to change the variable content from a certain integer to another string slice in Rust terminology, you can see that the data type can be changed. So originally, the variable has a type of an integer or i32 by default, but now it is a string slice, and we will talk about string slice later on for string manipulation in Rust. And of course, right, when I print this variable out, I will have December, which is a string slice. Okay, when this scope ends, the value called December and 12 will be removed one by one. The latest content is December, so it will be removed first, or it will be popped from the stack, and then the second value to be popped is the number 12. So after the popping of the two numbers, the two values from the variable called month, due to the shadowing effect, we will have only 11 remaining in the outer scope. Okay. So 11 was the original number. So when I run this sentence, I'm able to get the original variable back. So let us try to play with this code snippet on the editor. Okay, let us try to play with it. I haven't saved it yet. Try again. Okay, you can see that this is month 12. This is the value already shadowed. Okay, and this is December is coming from another shadowed value. Okay, so December is shadowing 12, which is shadowing 11. Okay, so when we talk about the stack again, you can see the shadowing effect more clearly by means of the stack operation. Okay, and after running the inner scope, both the December and 12 will be popped, and we have only 11 remaining. That's why the last statement will help us print out month 11 again. Okay, so that is the effect of shadowing. We can change the variable type from i32 to a string slice. So these two variable types are inferred by the Rust analyzer. Okay, I didn't have them in the original code, but they are both inferred by the Rust analyzer. Okay, so you can see the shadowing effect can help us change the variable type as well as the variable content. even though they are of different types. Okay. Another concept to talk about is constants. A constant is something like a certain immutable variable. A constant cannot be changed after the assignment, which is something like an immutable variable. But there is some difference, okay? The type of constant must be annotated, meaning that the data type must be specified explicitly. And of course, constants are immutable already, and we don't need to use the mut keyword to ever try to mutate the content of a constant. So you can see that for variables, we don't always need to specify the data type by ourselves, because the data type can be inferred by the Rust analyzer. But when we want to declare a constant, we have to really specify the data type explicitly. So let us see an example right here. So for example, I want to say the number of hours in a week. I have to say U32 here. U32 means unsigned integer in 32 bits. I have to add this part explicitly. And of course, the value to be assigned to the constant can be evaluated on the right-hand side of the equal sign, which means the assignment statement. Of course, for a statement, I have to end it with a semicolon. And of course, I can just print the constant out. So let me try to do it now. Okay, let me save it first. And you can see that I have to really type U32 here to really specify the 32-bit unsigned integer type to this constant. And we have to use the screaming snake case for the constants. Screaming means that I have to use uppercase letters for all the words in my variable name. And of course, I have to join all the words by the underscores, okay? So when I want to print the variable content, I can use something like this. A pair of double quotation marks and then a pair of curly braces to help me make the placeholder for this variable name, okay? So I'm going to put the content of this constant into the curly braces, okay? So let us see the result. Cargo run. You can see I can get 168, okay, which is already evaluated on the right-hand side of the equal sign, okay. Is it possible to ignore the explicit annotation? Let us try. You can see that I really can't do so. I have to really specify the type, otherwise there will be a syntax error. That's why I have to really specify the data type when I want to say a constant, okay. Of course, we cannot use mut for a constant because they can never be changed after it has been set up, okay. Another concept to talk about is the primitive data types. So Rust is a statically typed language. That means we have to tell Rust the data type before doing compilation, okay. So it is something similar to many other languages like Java or C++ and so on. We have to give the data type beforehand. So there are a number of possible data types in Rust. Number one, we have scalar types. For integers, there are a number of integer data types. We have 8 bits, 16 bits, 32 bits, 64 bits, 182 bits. And I've also a certain data type called I-size. I-size and U-size here are determined by the CPU architecture. If you have a 64-bit CPU, you will have 64 bits as the meaning of I-size, and 64 bits for U-size when you have a 64-bit CPU. Okay, so if you have a 32-bit CPU, I-size will be 32 bits and U-size will also be 32 bits. Okay, signed is I, unsigned is U. So you can see that there are a number of ways to represent the integer in Rust. Okay, Usually we can use the default type, which is I32, without any annotation explicitly. We can do the annotation in two ways, the prefix form and the suffix form. If there's no annotation, I32 will be the default type. So what is the annotation? Annotation means that I just type the data type after the identifier. Okay. For example, I32 here, which can be typed by ourselves. If I don't type anything, I32 will be used by default. Of course, you can also do the suffix form. The suffix form is like this 45, and I want to change the data type to U64. That's why I would say 45 U64. So I do the suffix form here. Okay. Another way to do the suffix form is to use the keyword s, 52 as U32. So you can see that I want to change the 54 value in the form of unsigned 32 bits. Okay. So let me try to do it on the editor. Okay, you can see that I can save them without the curly red lines. That means I'm able to pass the compiler. Of course, these orange wavy lines are meaning that I have some warning because I haven't really used those variables in my upcoming code. But it is still possible to make it executable because I just show nothing on the terminal or the standard output. Okay, so we can have many ways to do the prefix notation or suffix notation for the data types. Okay. For integer literals, we have some ways to do so. If I want to specify a decimal number, I can use an underscore to indicate 3 digits as a group, just like we use a comma or a period to indicate a group of 3 digits. Okay. If I want to indicate a hexadecimal number, I can use 0x before my hexadecimal number. If I want to use the octal system, I say 0O followed by the number in octal unit. That means base 8. If I want to indicate a binary number, I can use 0B followed by the bit pattern. For every 4 binary digits, I can separate them with the use of an underscore. Okay. If I want to indicate a byte, which is in the form of unsigned 8 bits, I can use B, which is a lowercase letter followed by a pair of single quotation mark surrounding a certain letter. Okay, so I can just use 8 bits or 1 byte to indicate the capital letter K in my case. Okay. So let us try to focus on another type called floating point types. There are 2 types for floating point numbers, F32 and F64. They are for 32 bits and for 64 bits of floating point numbers respectively. The default data type for floating point numbers is F64. Okay. So let us try these 2 examples. If I say F32, then this value of x will be in F32 data type, which has to be annotated explicitly. Otherwise, the Rust analyzer will give us F64 as the default data type, like the following one, y equals 7.1. 7.1 will be of F64 data type. Okay. Okay, you can see that I have to type it explicitly so that the Rust analyzer understands my data type for the value of x. Okay. But for y, I don't need to do so because Rust analyzer can help me infer the type okay, which is F64 by default, okay. Another data type is called the Boolean type. We can annotate a Boolean type with the keyword bool. So we can see this example. We can let a certain variable called is expired to be a Boolean variable by using true or false. Okay, if I want to annotate it explicitly, I can say colon space bool after the variable name. Of course, the Rust analyzer can help us infer the data type. That's why I can just say true or false after the variable name to make the Rust analyzer know that it is a Boolean variable. Okay, you can see that it can be inferred immediately, okay. I don't need to do the explicit annotation, although I can do so. Another data type is called character type, which has 4 bytes. So it can store characters other than English letters. So a character has 4 bytes in Rust. So many other languages can be stored in this kind of byte settings, okay. We need to use a pair of single quotation marks to enclose the character. So we can see the following examples here. I can use A to represent a character called X, and I can also use a variable name called B to represent a Chinese character. Okay, of course, for this Chinese character, I've enclosed it with a pair of single quotation marks. So Chinese character can use up all the 4 bytes. That's why Rust is able to handle a character in this sense, because a character has 4 bytes in memory to occupy. Okay, you can see that the data type can be inferred for us by the use of the analyzer. Okay, and we have one more type to consider, which is the simple data type called unit type. The unit type is just a pair of parentheses, okay, which is a tuple of no elements. So we have nothing inside the parentheses, okay, which is called the unit type. We will use the unit type later on in our further discussion of other topics of Rust. But now we just need to memorize that we have one more type called unit type for the primitive data type in Rust, okay? Other than the primitive data type, we have another group of data types called compound types. That means we can collect many variables in one type. So we have some examples of compound types. The first one is called a tuple type. A tuple is like this. We can use a pair of round brackets to enclose each element of different data types. The size of the tuple has to be fixed. The keyword is the different data types, okay? So you can see this example. I have a tuple. This is an integer, of course, but it is a floating point number. So I can put a floating point number together with a certain integer into a tuple. So the tuple can have different data types as its elements, okay? Of course, the first example tells us that we can just let the Rust analyzer infer the data type for us. Of course, we can also just annotate that data type by ourselves by using a pair of brackets, and inside the brackets we have to specify the data type of each of the elements explicitly. So for this tuple, the first character is n in character type, and the other one is Boolean type, so I can have true or false. Okay, so let me try to show it on the Okay, you can see that the first example shows our annotated type inferred by the Rust analyzer. Okay, I32 is of course an integer, so the default type is I32. 5.9 is a floating point number. By default, it is F64. Okay. So the other example is that I annotate the type explicitly so that the first element is of character, the second content is of Boolean type. Okay. And when we have a tuple, we can destructure a tuple into separate variables. Destructuring in this context means that I can just pick up each of the content out. So, for example, I have a tuple here. When I say A, B equals my tuple, I can put the first content into A and the second content into B respectively. And then when I do the printing, I'm able to get the two things respectively. Okay. So that's a 6.8, not 6, comma 8. So let me try it now. Okay, you can see that the data type can be inferred from here. Okay, so for the first data type, it is F64, and for the second one, it is I32 by default. And you can see that I can just do the destructuring right here. A will become 6.8 and B will become 3. So let me try to run it. Cargo run. Okay, I forgot to do something else right here. Okay, I forgot to comment it. So let me try again. Cargo run. I haven't saved it yet. Okay, let me try again. Cargo run. You can see 6.8 followed by 3 can be printed out, and this comma is just coming from this comma. Okay, so I can just destructure a tuple and print the content out respectively. So I can put A into the content of the curly braces, and I can also put B in the content of the curly braces to just print the destructured content out. Okay. Alternatively, we can use a period to obtain an element out of the tuple. So other than using the destructuring technique, I can use my tuple.0, my tuple.1, my tuple.2 to indicate the respective element from my tuple. Okay. In Rust, the index would start with 0. That's why I have to use 0 to represent the first element, index 1 for the second element, and so on. So let me try to run this example. Okay, let me try it here. Okay, you can see that 1.3, 7, and true can be printed out. Okay. Because 0 means the first element, 1 means the second element, and 2 means the third element. Okay. So we can use a period to indicate the element in the order of appearance. Okay. Another compound type is called the array type. We can just collect the data of the same type in an array of fixed length. Same type and fixed length. Okay. For tuples, the data type of elements can vary, but for arrays, the elements have to be of the same data type. Okay. We can use it when we are sure that the fixed size is helpful, like storing the data of all the months in a year. So when we are pretty sure that the data can be stored in a fixed size, we can use an array to help us do so. When we do arrays, we have to use square brackets to contain the elements. So like this example, I use a pair of square brackets to enclose 3 floating point numbers. Okay. The element type can be annotated together with the array size in this way. So I want to annotate this array. I don't want to use the Rust analyzer to help me infer the data type. If I want to annotate the data type by myself, I can use something like this. A pair of square brackets, and then first as F64 as the first data type, separated by a semicolon, and then the second value here means I want to have 2 elements in my array. Okay, so both numbers have to be of the same data type, and this array has a length of 2 indicated by here. Okay, that's why I can put 2 floating point numbers right here. Okay, so I can let x in this way. Of course, I can also let y be like this by annotating the data type together with the length of my array in this way. Okay, and the first example shows that the data type together with the length can be inferred by the Rust analyzer. Okay, when we want to initialize an array with the same element for a number of times, we can use this syntax. I want to have 3 A's as the element of my array called set. Then I can just say the element followed by a semicolon and followed by the number of times to show up. Okay, you can see that the data type can be inferred for me, which is a char here, and the length is of course 3. Okay, so I will have A in my array called set. Okay, we can also use an index to access an element. The first index has an index of 0. Okay, so for this one, I have 4, 7, and 2. There are 3 elements, and if I say x2, it means that I'm able to get the third element of an array, which is just this element. Okay, so this is the major idea of using an index to access an element from an array. Okay, x2, 2 here has to be embraced by a pair of square brackets. Okay, if the index is out of bounds, Rust will panic by indicating the runtime error. Panicking here is meaning a way for Rust to handle runtime errors, so we will talk about the meaning of panicking later on when we talk about error handling for Rust. Okay, that means if the error is out of bounds, if the index is out of bounds, the program will panic by showing a certain runtime error. So we have to make sure that the index has to be within the length of our given array. Okay, so you can see that these 2 lines can pass the compiler. And the next topic to talk about is the relational operators. So we can compare the values using relational operators. So we have a number of ways to do the comparison: smaller than, larger than, smaller than or equal to, larger than or equal to or not equal to. So we can just use these symbols to help me compare the 2 values. So for example, 5 is smaller than 9, 3 is not larger than 9, 6 is smaller than or equal to 6, 4 is not larger than or equal to 7, it is smaller than 7, 3 is not equal to 4, and 6 is of course not equal to 7, so this statement is true. Okay, and for logical operators, we can use the 3 basic ideas called AND, or, NOT. The symbol for AND is 2 ampersands. The symbol for OR is 2 pipes. The symbol for NOT is just an exclamation mark. So how can we use these 3 logical operators? We can do something like this. 4 is larger than 2 and 9 is smaller than 3. For this situation, I have true and false. So when I want to make n to be true, I have to make sure that both conditions are true. But this condition fails. That means I will have true and false, giving me a false as the answer. When we use the OR operator, we have to make sure that at least one condition is true to make the result of OR to become true. 3 is smaller than 5 or 8 is smaller than 3 is true, because the first statement is true, but the second one is false. True or false is also true because at least one condition is already true, which is the first condition. Okay, When we use the not operator, we just negate a Boolean value. 5 is larger than 2 is already true, but if I do the negation, I will turn a true value to a false value. Okay, so we can use and or not to do the logical operation. We have to notice something when we do the logical operator. We have to note that short-circuiting is applied to logical operators. The meaning of short-circuiting is like this. When the early conditions are able to warrant the logical value of the whole expression, further conditions are not evaluated. Let us see an example like this one. X equals 5 larger than 6 and 3 less than 10. So I want to assign true or false value to x. Okay, so I have to evaluate this logical operation. 5 is larger than 6, which is false. When this one is false, no matter how we present the Boolean value of the second part, I will still get false. So this part is true, false, and true. Of course, we will get false. But even though I don't need to handle the second part, I'm already able to know that the first one being false will give me the answer to the logical AND operation to be false already. Okay, so this part can just be skipped because we are already sure that x will be false after running the first comparison. Okay, so we will get false by ignoring the further comparison in the second part. Okay, and then we are going to talk about functions in Rust. When we want to do a function, I have to use a fn followed by a function name that we create. We use the curly brackets to indicate the scope of the function code. So I have some examples right here. Of course, I have the main function, which is something we need to run for every Rust program. And in the main program, I have a greet function, and the greet function is defined outside the main function. So I can just say hello. Okay, so let me try to play with it. Okay, then let's try to play with it. Okay, you can see hello right here. Because when I have the greet function to be called, Rust will try to find the function back, and the Rust compiler will try to do the action indicated in the function content. That's why I have to print hello by calling the greet function. Okay. Of course, I will get hello as the output. And that is the case of function without parameters. So greet here has nothing inside the pair of round brackets. Okay, so it is possible for the round brackets to have some content being known as the parameters. We can declare a function with parameter names and their type separated by a colon. So we will see this meaning very soon. It is mandatory to declare all the types of your parameters, so we have to annotate all the types of the parameters when we want to make a function. The Rust compiler can check the arguments passed to the respective position of the parameter list. So let us see this example. I have a certain function called doQuestion, and there are two parameters. One is called number, and the other one is called part. Number has to be in I32, part has to be in character. Okay, so the annotation right here has to be done when we create a function. Okay, so when I call the function, I just pass I32 to be 3 and char to be letter A. So I will say doQuestion 3A when I say 3 as the first parameter value and A as the second parameter value. So let me try this example. Okay, then let's try to play with it. Okay, you can see do question 3a. So 3 is passed to the first position and part is put in the second position. Okay, so Rust has to check the data type passed to the functions at compile time. So I have to pass an integer, which is 3 in my case, and a character, which is a in my case, to parameter 1 and parameter 2 respectively. Okay. Otherwise, the compiler would just stop me from going further. And a function can have return type. So let us try to discuss it. In the last two examples, I didn't want the function to really return something to another variable to store the content of the function return value. I just tell the function to do something and the function doesn't need to return anything out. Okay. So if a function has some kind of return value, we have to follow the following rules. So you can see that I have to call a function called add, defined right here, and I have to remember the output of a variable of a function. Sorry, I have to remember the output of a certain function by using a variable. So I let a variable called answer to store the output coming from this function, and then I can print the function out, the answer out. So the function has something to do with the return value. So I have an add function. The add function tries to do simple addition. So x plus y will be the output. So if I want to really output something out of the function, I have to say x plus y as our way to manipulate the two parameters. And we have to notice something. I don't put a semicolon at the end of x plus y because I want to show an expression which is to be returned to the outside world. An expression to evaluate the sum of two arguments is shown here. X plus y is an expression. We don't put a semicolon here because for semicolon we are doing a statement. A statement doesn't return anything out, but for an expression it has to return something out. So x plus y will be returned by the function to the outside world, and that's why I can use an answer variable to get the result. Okay, I can just print out the answer as well. A function has two parameters, both of I32 type. Okay, and one return type of I32 type. So the arrow indicates the data type to be returned. So this function has to return a data type of I32. The operation indicated by the content of this add function will have a value of I32 type as the return value of the expression shown here. Okay. So the arrow here means the mapping direction. So I want to do the mapping. So when I have x and y, I can map them to another I32 value, which is just the sum of the two values passed to the function. Okay. So let me try to play with the program again. Okay, you can get 3, okay, which is just the answer to 1 plus 2. 1 is passed to x, 2 is passed to y, okay. So you can see that the answer would become 3, which is saved in the variable called answer, and I can just print out the answer out, okay. If a function has a return data type, but the function does not end with the expression for the return value, then a unit type will be returned, which does not match the concrete data type of the function. Since the unit type does not match the return data type, the program cannot compile. So what does it mean by that? As I said, I have to end the expression without adding a semicolon. Okay, if this ends with a semicolon, the function would just have a statement inside, but it doesn't have a return value, which is in the form of an expression. If I put a semicolon here, the value of answer won't be 3, but just a data type called unit type, which does not match the concrete data type of I32 here. So x plus y semicolon would just give me a unit type which is not equal to this particular data type. Okay, so it is not possible for the program to compile. So let us see. I add a semicolon here, and when I do so, you can see something right here. I have to remove the semicolon to return the value out, and you can see that I have to return I32, but the program found a unit type which is not allowed because the unit type doesn't match the return type as expected by the function. Okay, so I can't even compile, and of course the answer variable can never get this unit type out because the compilation has failed. You can see here, when I just compiled, I can see this kind of possible problem with the program, mismatched type. If I add a semicolon right here, I will have a unit type coming out, which is not equal to the desired data type of I32. That's why the program cannot compile. I have to just remove the semicolon to help me compile the program. Okay. Differences between a statement and an expression. This is something quite important in Rust. If we don't care about the differences between these two things, it is easy to make mistakes. A statement is a certain instruction to do something. No return value is given out. An expression is a formula to result in a value. So these are the definitions of a statement and an expression. A statement has to end with a semicolon, while an expression doesn't end with a semicolon. That is something we already stressed in the previous discussion. So when we want to do something like this, Rust would disallow us to do so. Let's see what's happening right here. I want to assign a value to a variable x, and the value comes from this scope. Let y equals 3 without semicolon. Okay, so let y equals 3 is a statement. Okay, so this statement has no return values, not even 0. Okay, so this statement would not return any value to be captured by the variable x. So this is a statement which cannot return a value like an expression does. Okay, so let us try it on the editor. You can see that the compilation fails. Okay, so we have to bear in mind the statement and the expression. Also, an expression can be a part of a statement which can be used in assigning a variable. So let us see this example, which is a bit long. I want to assign some value to A, and the value of A is evaluated in the inner scope like this one. I have B equals 1, and then I want to return B plus 1. So B was 1, and after this expression, B would become 2, and you can see that it is an expression because it doesn't end with a semicolon. So the value will be passed to the content of A. Okay, so in this case, an expression can be bound to a variable called A, and I will see 2 as the output. So let us play with it. Okay, you can see that A is 2 because it is a value obtained by operating on B using this expression, B plus 1, okay? Another topic to discuss is the comments. Line comments would start with 2 slashes, just like what I did here, okay? And for block comments, they will start with a slash followed by an asterisk and end with an asterisk followed by a slash, like the one shown here, okay? So I have already commented out this whole block with the block comments, okay? But for Rust, it is idiomatic to use 2 slashes to do the commenting. But we can use the block comments to hide the code that we don't want to execute during the testing, just like what I did now. When I don't want to execute some of the code, I'll just use the block comments to hide them out, okay? So when we want to use the line comment, we can do something like this. Only this line is printed, okay? So this is something happening after the statement. So starting from this position, the content will not be evaluated by the compiler. But before the 2 slashes, the content will still be evaluated, okay? Another topic is the control flow. So we can play with else, else if, and if statements. So if one condition is met, I can run the block of code and ignore the upcoming blocks, even though the upcoming blocks can return true. Else, I check the next condition, okay? This is the meaning of if, else if, or else. This is the major idea, okay? We will see an example later on. The else if or else part is optional. We don't always have to mention else if or else all the time in our conditional statements or our control flow statements. We can have a number of else if arms and only one else arm at the end. So the meaning of arm here is just like a possible result that will be printed out or that will be executed if a certain condition is met. We can have multiple else if statements, but only one else arm. So let us see this example. The block of code for each condition is known as an arm. So in my example here, I have 1 arm, 2 arms, and 3 arms. Okay, I have 3 arms in this example. So I have a number which is 2. If the first condition is met, I can just print this statement out. So I will print this one out, because the first condition is met. 2 is really smaller than 5. Okay. If this one fails, I will go to the next statement. And if the second statement fails, I will try to do the else part. Okay, so let us see this program by playing with it now. So let us play with it. I got a number smaller than 5, which is natural because the first arm is able to be executed because the condition is met for the first arm, okay? We can also combine if with let. So this is a bit subtle, so let us see an example like this one. If here is an expression, it can return a value. So the if statement is actually an expression which can return a value. So we can combine the if keyword together with the let keyword to do assignment. We have to make sure that the arms return the same data type, because a variable to be assigned can have only one concrete data type determined at the compile time. So let us see an example. My number is 2, so I want to assign some value to the isCorrect variable. The way is like this. I want to do a lot of things right here to evaluate the value to be assigned to the isCorrect variable. What is the value to be assigned? I have to check my number variable. If it is 2, then I will assign true to isCorrect. If it is false, that means if my number isn't equal to 2, I will assign false to isCorrect variable. And of course, this is a statement. I have to end the statement with a semicolon. So the whole thing is a statement. That's why I have to end the whole thing with a semicolon. So let me play with it. Okay, you can see true here because the value of isCorrect is assigned to be true. Why I would have true? Because my number is really equal to 2. That means this arm is executed. Okay, so this arm is executed, meaning that the value of true will be returned. Because you can see that I have no semicolon at the end. It is a pure expression which will do the assignment statement correctly. Okay. The next part to talk about is the loops. Okay. We can have loop and break keywords. A loop can repeat itself endlessly unless it is stopped by a break keyword. And the break keyword is applied to the innermost loop. So let us see this example. I want to change the content of x by adding 1 for a number of times until I get x equals 5. If x is equal to 5, the loop will be broken. That means I will just leave the loop and I will just go to this particular position shown by my current cursor position. Okay, and then the program will just end. So let me play with it. You see 1, 2, 3, 4 coming out right here. Okay. Because when x is equal to 5, I just break the loop. That means I leave the loop. So we have a loop here, and if I don't have a break keyword, or if I don't have this condition, the loop will continue forever and ever. Okay. It won't stop. But if I have the break keyword, when x is equal to 5, I will just quit the loop. Okay. We can return a value with the break keyword, and then that value is assigned to a variable. So in the previous example, I don't have a value following the break keyword. I just leave the loop. If I want to leave the loop with something coming out of the loop, I can do the assignment as follows. My value is equal to something which is obtained by breaking the loop and returning a value from the broken loop. Okay. So you will see that this program is able to give me 10 as the answer. Because when x is equal to 5, I will leave the loop and assign 2 times 5, which is equal to 10, to the my value variable. So let me play with it. My value is 10 has come out. Because when I do the breaking, 5 times 2 becomes 10, which is assigned to the my value variable. And of course, for this assignment, I have to use a semicolon to express the statement. Okay. If we want to skip some iterations, we can use the continue keyword to do so. So we don't always need to loop over all possible steps involved in the loop. We can just skip some of the iterations by using the continue keyword. And then we can see something like this. We are going to talk about the while keyword. While the condition is true, we can do the instruction in the block. So if x is still smaller than 6, I can always add x by 1. Okay, so plus equal is the shorthand form of x equals x plus 1. Okay, So let me try to play with it. Okay, you can see that I have 1, 2, 3, 4, 5 as the output, okay. But not 6, because when x is equal to 6, I will just leave the loop. So this condition is not met when x is equal to 2 exactly. X is not smaller than 2 at that time, okay. That's why I will have only 5 numbers coming out, okay. And let us talk about the for loop. The iteration will be executed from the starting point to the point before the ending point when we use the for loop. The starting point and the ending point will be separated by 2 periods. So let us see this example. For index in 0 to my array.length, this len method would just tell me the length of this array. So the length of my array is 5. So it will be equal to for index in 0 to 5. But I would stop before the ending point. So I would just have 0, 1, 2, 3, and 4 as the indices. Okay, 0, 1, 2, 3, and 4 as the indices. That's why I'm able to print out all the integers in my array. Okay. Two, 1, 6, 3, 4. Okay. So index 0 to index 4 will be printed, and I won't have the index out of bounds error. Okay. Because I just have 0 to 4. Okay. The for loop can also be done with the use of in keyword. In this case, we don't need to use the indices, and the element will be obtained directly. So you can see I can use for number in my array. Then I will just pick up each number out. Okay, you can see I have 2, 1, 6, 3, 4 as the answer, okay? So that is quite easy to understand. Number will be the individual content of my array, okay? So I can use the in keyword to help me do this task without the use of the indices all the time. We can also iterate over a reversed tuple so that the index obtained will be reversed. So I can use the .rev method to do the reversal of the tuple. So I have 1 to 5 as my original tuple. Then when I do the reversal, I will have 5, 4, 3, 2, 1. Okay. So let me play with it. 5, 4, 3, 2, 1 has come out. Okay. Actually, we have another approach called iterators to do the looping over an array in Rust. We will cover the iterators in other chapters. So we will learn the way to do the iterating by using iterators later. And let us go to the keyword called continue. We can ignore particular iterations and do the rest of the iterations. So, for example, in this situation, if index becomes 2, I will just skip this condition. So I will go back to the for loop and do the looping in other steps. So I will just do the situation when the index is not equal to 2. So let us play with the example. I have an array right here. The length is 5. So 0 to 5 means 0, 1, 2, 3, 4. If index is equal to 2, I will continue. That means when index is 2, I will go to index equals 3. So in this situation, I will just skip the printing of index equals 2. Then I will just print 2, 1, 3, and 4, okay? the index 2 will be skipped by the continue keyword. Okay, you see 2, 1, 3, and 4. Because index 2, which is representing number 6, will be skipped by the word continue, okay? When I see the word continue, I will just go to the next step to do, okay? Another thing to talk about is the loop labels. The break keyword can help us jump out of the innermost loop only. To jump to even the outer loops, we can use the label to help me do so. A loop label will start with an apostrophe and ends with a colon. The loop label is placed before the loop keyword. So this is the label, an apostrophe followed by the loop name. So when I want to break this outer loop, I can just say break outer loop here. So you can see that I have a nested for loop here. So if I use break without the outer loop label here, I will just go to the outer loop to do the rest. I won't just leave both the inner and outer loops. On the other hand, if I use the outer loop label after the break keyword, I'm even able to quit the outer loop. That means I will not do any further things, okay? So let me play with it. Okay, you can see 0, 1, and 2, okay? So you will see 0 plus 0 equals 0, 0 plus 1 is 1, 0 plus 2 is 2. So if I plus j equals 2, I will break the outer loop. That means I will just go to this position, okay? And then I will do nothing because I've already quit the outer loop already. Then I will not go to the inner part of the loop to do further calculations. That is the meaning of the outer loop label in my case. So we can use a loop label to help me jump out of the outermost loop, okay? The next topic is called formatted print. There are a number of format macros to print the text on the standard output. The first one is the print macro. It can print the text on the console without adding a new line. So the next printed text can continue on the same line. So let me try to do it. For this one, I will have A, B, C, D, E, F on one line. Okay, you can see the result. When I say print A, B, C followed by print D, E, F, I will have all the 6 letters together. Since I haven't added any new line character, I will just have the cursor being stopped at F, and my terminal will continue printing following the character F, okay? So we can also learn something right here. A, B, C, and D, E, F are called string literals. And actually, string literals are string slices that have a fixed size. They are saved in the compiled program and cannot be mutated. We will have a topic about the string literals and the strings in Rust. So these concepts will be quite special in Rust. We will talk about them later on. So at least we have to know that the string slices will be stored in the compiled program, and we cannot mutate the string slices once they have been created, okay? And the other formatted print method is called print line, which is a macro, of course. It prints the text on the console without adding a new line, and the next printed text will start on the next line. So we have already seen this effect quite a lot already. we will add a new line character after using the print line macro. Okay. We can also do format macro. It will store the further contents on the string. So this is called a format macro. When I say format and I put something right here, you can see that I will put a lengthened sentence into the curly brackets. So when I do the printing, I will be able to have a very long sentence rather than just this is. Okay. Okay, we have this is a lengthened sentence. So when we use the format macro, I'm able to put the second part into the curly braces to make a longer sentence, which is in the form of string. Here, the letter is capital for the first letter S. Okay, so this is a string type in Rust, which will be discussed later on. And we can also print the error on the standard error rather than just printing everything on the standard output. So if I want to do printing on the standard error, I can add E before print. Okay. The terminal can still show the standard error, but we have to notice that they are not from the standard output already. They are from the standard error. Okay, so even though they can be joined together and they can be shown on the terminal, they are actually from the standard error. Okay, so if I want to do the new line character after the standard error printing, I can use ePrint line. Okay, in using both the ePrint and ePrint line macros, we can divert the standard output to a file and leave the standard errors show on the screen. So that is something I'm going to demonstrate. The A, B, C, D, E, F is something I'm going to print out. Now, I want to divert the standard output to a file called output.txt. So I say cargo run, and I have a certain arrow, and the arrow will help me print the standard output to a file instead of on the screen. So on the screen you will just see A, B, C, D, E, F, but on a text file called output.txt you will see the hello. So let me try it now. Okay, you can see A, B, C, D, E, F, which is from the standard error. And how about the hello? It is shown on output.txt file. Okay, so with standard error, we can show the error and we can just divert the standard output to a text file instead of showing everything on the terminal. Okay. We can also do the formatting of text. The formatting is quite straightforward. The first curly brackets refers to the first content. The second pair of curly brackets corresponds to the second content. Okay, and of course we can also use the positional arguments to represent the position to be put. So the 0 here means the first value, which is Smith. Number 1 here means the second argument, which is just John. So you will see first name John, last name Smith. We can also use the named arguments. The first name is here, the last name is here. So last name equals something and first name equals something, and then we can just recognize the named arguments and put the corresponding values correctly. So let me play with it. Oh, here. Okay, you can see that the values can be printed in order, and we can also use the positional arguments. 0 means the first argument, 1 means the second argument, and so on. And I can use the named argument as well to put the corresponding values into the corresponding names. Okay, that's why I have these results. We can also pad some zeros or spaces into our result when we do the print line macros. So we can do the right justifying. That means we can insert spaces and then insert a digit. And the inserted space plus the digit would use 4 spaces in my current example. I want to pad some spaces, and the final digit will be 2. So I have 1, 2, 3, 4 spaces including the digit 2. And we can use a smaller than sign to do left justification. It means that we insert digits and then insert zeros. And the digit plus the inserted zeros would use 3 spaces in this example. I want to pad zeros after the left justification. So 600. I want to have 3 digits for my whole answer, and the first number will be 6. Okay. We can also insert zeros and then the digit. The inserted zeros plus the digit will be using 4 spaces in this current example. I want to add zeros and add 3 at the end. That's why I say 0 here, because I want to pad zeros. Okay. If I want to pad zeros, I have to say digit colon 0 and then larger than. Okay. The resulting width can be specified outside the string. We can use the $sign to specify the resultant width. So I want to pad zeros, and the width will be 5. So the value 5 is obtained outside the curly braces. Okay. Digit will be 8, so I pass the digit which is 8 to here and 5 to here, so it will become digit as the first value, and then I have to add 4 more zeros so that the whole width would become 5. Okay, so you can see the result. Okay, you can see 2 here with 3 spaces before, 600, 0003, and 80000 at the end. Okay, so they just follow the principle shown here. Okay, 0 means padding zeros. Nothing here means padding spaces. Okay, the less than sign means left justification, while the larger than sign means right justification. We can also do formatting of numbers of different number systems, so we don't always stick to integers all the time. We can change the decimal number system to others. So let us see this example. I have 1, 2, 3, 4 as a decimal number, so that is 1234 as the value of A. I can change the number system of A to other number systems. I can change it to a binary system. I can change it to an octal system in base 8. I can also change it to the hexadecimal system in base 16. So I use B for binary system, O for octal system, and X for hexadecimal system. So let us see the result. Okay, you can see 1, 2, 3, 4 as the original value. I have only one here. Okay, so for binary system, it will be this long thing, a stream of ones and zeros. For octal system, it will be 2, 3, 2, 2, means base 8. 4D2 means the hexadecimal system, base 16. Okay. So we have learned a lot of things about the basic types of data and some basic operations of Rust, including the control statements, while statements, and so on. We have also noticed the meaning of the statements and expressions in Rust. They are very different, and we have to notice their differences very clearly before we can use them right. Now let us take a look at this example. I'm going to apply the basic programming techniques to handle this problem. Given the fixed cost of production and the possible variable costs of production, I would like to find the number of items and the corresponding variable cost that would make the total cost exceed the maximum cost of production. Due to the time constraint, I can only produce at most 3 items for all the possible variable costs. So let me try to show my function signature that can handle the calculation, and then I will show you my way to call that function in the main function. Okay, this is my function. I want to write a function called getMaxValues. I would like to return a tuple that contains the limiting variable cost and the limiting number of items. And the fixed cost is an integer. I can use i32 by default, and the variable costs are put in the form of an array. So the array would contain i32 elements, and there are 3 elements in this array. So I use this notation, i32 semicolon 3, to denote the data type and the size of this array. And I would like to include the maximum total cost, so that I want to check whether the fixed cost plus the variable costs would exceed the maximum cost of production. So the maximum cost is shown here, which is an i32 type, and this function would return a tuple having 2 integers in i32 format, and these 2 values would refer to the limiting variable cost and the limiting number of items. So I will try to show the way to call that function in the main function now. Okay, I put the fixed cost of $1,000, the variable costs in terms of an array, $20, $30, and $50 for the elements, and the maximum total cost is $1,100. Okay, so the first value to output in the tuple as the return value is the limiting variable cost, and the second value in the tuple to be returned is the limiting number of items. So let me try to continue with the function. So I just produce two mutable variables, and they will try to store the answers to the problem, and I will just return the two numbers in the form of a tuple. Okay. Now I want to loop over the variable cost coming from the variable costs array, and I'm also going to loop over the number of items to try. The question says that we can try at most 3 items. That's why I'll just say 1 period 4, so that the number of items can only be 1, 2, or 3. So number 4 is not included in the looping. Okay. And then let's see how I can try to find out the required variable cost and the number of items. So I define the total cost first, which is equal to the fixed cost, which is already applied by the function's signature. And of course I have to use the variable cost obtained from the array one by one, and the variable cost is multiplied by the number of items, which can be 1, 2, or 3. And I want to see whether this total cost exceeds the maximum total cost. If the total cost evaluated is actually larger than the maximum total cost passed to the function, what will I do? I just remember the limiting variable cost and the limiting number of items, and I will just return these two values in the form of a tuple, so that the main function is able to obtain the function result. Okay, the idea is to just update the variables called limiting variable cost and the limiting number of items, and they are both mutable. That's why I can do the reassignment again. Okay, and if the limiting variable cost and the limiting number of items are already found, I can just end the whole for loop, including the outer for loop. So that's why I can just use a loop label to indicate that I want to break both for loops. If I don't include the loop label, I'm just able to quit the nearest for loop, but not other for loops that are even far away from the current for loop. So let me try to add the loop labels. Okay, when I break the outer loop, I'm able to just go outside the nested for loop. Okay. And I'm going to return the limiting variable cost and the limiting number of items as the answer. Now, since I just want to output an expression, I don't need to add a semicolon at the end. Otherwise, I would turn the line to a statement which is not returned to the outside world from the function. And let us see how I can just print out the values obtained from the tuple in the main function. Okay, I just want to use the print line macro to return the limiting variable cost obtained from the function output and the limiting number of items from the function output as well. So let us see if I'm able to play with the program. Okay, you can see that the total cost is exceeded when the variable cost is $50 and the number of items is 3. So why is it the case? Let us put the values into the equation to see whether I'm able to get a sensible output. Fixed cost is 1,000 and the maximum cost is 1,100. So I can try 50. 50 times 3 gives me 150. 150 plus 1000 gives me 1150. That is larger than the maximum total cost of 1100. Okay. So since I can try at most 3 number of items shown here, 20 times 3 is 60. 30 times 3 is 90, and 50 times 3 is 150. That's why I can find the variable cost and the number of items that can exceed the total cost of production given by here. Okay. So this function is complete, and I'm able to show the values correctly. So to wrap up, I can say that the function has this purpose. So this is the essence of my function. The function accepts the fixed cost, an array of variable costs, and the maximum cost of production. And the function would return a tuple that stores the limiting variable cost and the limiting number of items. So you can see the function call is like this one, and you can see the function signature is like this one, and you can see how these function arguments can be matched to the function parameters. And we can use the nested for loop to help me loop over both the variable costs from the array and the number of items from 1 to 3. And you can use the loop label to control the time we want to quit the nested for loop. Now let's go to the ownership part of Rust. This is an important part of learning Rust because the memory safety is achieved by using the ownership mechanism. So the Rust program relies on ownership rules to manage the memory. And when the ownership rules are violated, the program cannot compile. That's why the program can be safe in terms of memory issue. Rust has a lot of treatments of the data stored on the stack and on the heap respectively. So there are two types of memory, the stack and the heap, and we treat the memory on the stack and the memory on the heap differently, and I'm going to tell you the differences in detail. First, we have to distinguish between the stack and the heap. Stack and heap are memory locations that store the values in different mechanisms. The data put on the stack must have a given fixed size at compile time already, okay? And the primitive data of fixed size at compile time can be stored on the stack because we know the size already at compile time. By default, the values are put on the stack, and the stack would follow the last in first out principle, LRFO. So this is something about the stack. The heap will be a bit different. The heap does not follow the last in first out principle. Rust will just help us to find a location that is sufficient to store the data for us in the memory, corresponding to the heap part, okay? And then a pointer is returned to us from the memory, which helps us to locate the value on the heap. So for heap allocated memory, we will have a pointer to help us locate it in the program, okay? The return pointer is of some known size, and we store the pointer on the stack because a pointer of this type has a known size already. For the data with a given known size, we can save it on the stack. That's why the pointer can be saved on the stack, even though the pointer would point to a part in the heap. Okay? The pointer of the actual data can help us retrieve the data that is allocated on the heap, so we just rely on the pointer to get back the memory on the heap. Putting the data on the stack is usually faster as it is done at the top of the stack by doing pushing and popping. But putting the data on the heap is lower as it takes time to find the sufficient space to store the element or the value on the memory corresponding to the heap part. Also, we need to create a pointer. So finding a space to store the memory and creating a pointer would take more time than doing data treatment on a stack. Accessing data on the stack is usually faster as it is achieved by popping. So I just remove the upmost element on the stack. But accessing the data on the heap is slower because it takes time to find the data on the heap, which are not necessarily put in the particular order. So the data on the heap can be put randomly, and it takes time to find a piece of data from a heap that does random allocation, okay? And there are a number of types that are put on the heap. So we already know that the data type with known fixed size can be put on the stack. But for the heap, there are a number of types that can have some kind of varying size of data. For example, we have a box here. A box is actually a pointer type, which is a smart pointer type that we will discuss later on, to wrap a generic type that is put on the heap. So we rely on the box pointer to locate a part of memory that is put on the heap, okay? The other example is a string. Here, the string has a capital letter S, so it is a particular data type in Rust. So a string here is a type to store strings on the heap. So we have a mechanism to use a reference to locate the value on the heap that is in the form of a string. RC here is another type of smart pointers that we will discuss later on. RC here means the reference counting pointer type. This is the pointer type that allows multiple ownership. We will discuss RC pointer in detail later on. Another type that is put on the heap is a vector. A vector is a type that stores a number of values of the same data type. We will play with the vectors later on as well. So we can see that these four types would store the data on the memory part corresponding to the heap part, okay? And we also need some kind of pointers to help us locate the memory on the heap. After we have already discussed the stack and the heap, we can discuss the ownership rules. We have three rules to remember. Number one, each value has an owner. And number two, each value has only one owner at a time. We cannot have multiple owners at a time. And number three, when the owner is out of scope, the value is dropped automatically. That means it is cleared from the heap as well. So the value will be removed from the heap. And of course, the pointer corresponding to this data on the heap could also be removed. We will mention these rules in future to explain the way Rust manages data on the stack and on the heap. So when we talk about other sections in the later part of the video, we will sometimes refer to these ownership rules to help you understand why we will have this kind of treatment. Now let's take a look at the data on the stack. When we assign a variable to another variable, a copy is made on the stack, and then both variables would own their values. That means when we do an assignment of a variable to another one, we will just copy the content on the stack. So the reason for the copying is that it is quite fast to do so on the stack. So let us see an example. Suppose I have this simple program, a equals 1, and then I assign a to b, which is another variable. In this situation, we would have two pieces of data on the stack. One is called a equals 1, and the other one is called b equals 1. Because b happens later, it is put on top of the stack. So when the program ends, b will be removed first because it has the last element to be produced. And a will be removed later because it is the very first variable created in the program. So by following the last in first out principle, the variable b will be removed first, followed by variable a. Okay, so this is a timeline of the stack situation. So you can see that both variables would have a value of 1. So that's why I would say that a copy is made on the stack. Two variables and two values. Okay. We know that integers are of fixed long size at compile time. For example, for i32, we have 32 bits to store an integer. Therefore, a and b can be stored on the stack. And by using a stack, we can illustrate the memory allocation on this diagram, and this is a timeline from left to right. So let us try to play with this program on the editor. Okay, you can see 1, 1 here. That means a is equal to 1 and b is also equal to 1. And the value of 1 is copied to another variable. So we have two 1s on the stack. Okay, that is the meaning of the copying action on the stack. Okay, so data on the stack can be copied. Okay. And then we talk about the data on the heap. We take string as an example. String here has a capital letter S, so it is a data type in the standard library. Strings can be stored on the heap. Its size can vary at one time. That means when we run the program, we can understand the size of a string, and then for this kind of memory, we need to put them on the heap. Note that the strings are different from string slices, which we will discuss later. A string slice is stored on the stack, which is different from the treatment of strings that is stored on a heap. Its size cannot be varied at runtime. I mean, a string slice here cannot vary its size at runtime. So the size is already determined at compile time for string slices. Okay. We can use the from function of strings to make a string on the heap from a string literal. String literal is similar to a string slice, so we just use a pair of double quotation marks to enclose a string literal, and then when we want to create a string on the heap, we just use the from function. Okay. The variable named myString, which is this one, can help us locate the string on the heap, so we use this function to do so. And the drop function is called for the string when it is out of scope. So when the program ends, or when the scope of the string ends, the heap memory will be cleaned. So the value stored on the heap together with the variable that points to the heap memory will both be removed. So let us try this example now. Oh, let me see. I have to change the quotation mark. Oh, here again. Oh, I see. So let me try to run it. Okay, you can see A, B, C right here. So A, B, C is a string on the heap, and I can use this variable to help us locate the memory on the heap, and then I can just use this variable to help me print out the content stored on the heap. So this mechanism is provided by Rust so that I don't need to handle the treatment of extracting the content from a heap explicitly. I can just use the variable to locate the string content directly. Okay. So we can take a look at the documentation about the string in Rust. Now let us see. String here is shown here, and we can use the from method to convert the string literal to heap allocated memory. Okay. So if I want to add something more on the string, we have to turn the string to be mutable first, and then we can use the push method and the push string method. Okay. So that is the meaning of a string on the heap allocated memory. A string has three components when it is stored on the stack. We have a pointer, the length, and the capacity. So this variable called myString is actually storing these three pieces of information: pointer, length, and capacity. PDR is the pointer to the string on the heap. LEN is the length of the string. Capacity here is the total number of memory that is received for the string from the allocator. So let us see this diagram. My string here is actually storing these three things: pointer, length, and capacity. And when we have a pointer, it can point to the allocated part on the heap. Okay, so this heap has this piece of information, A, B, and C. That means the string has 3 characters, and each of the characters would have an index. Okay, so the pointer would just point to the very first element on the string, which is indicated by index 0. Okay, so my string here is representing these 3 pieces of information. And let us consider the following code. I have a string here, and then I can print the string out, and then I can do the assignment of the first string to another variable. And when I do the printing of the second one, what would happen? Let us see. If we assign the string variable to another variable, the stack would have one more variable, which is this situation, my string followed by my string 2 on top of the stack. The new variable would point to the same heap location, so we would have 2 variables pointing to the same part on the heap memory. It is less costly to point to the same heap location than to create a deep copy of the heap data. So the diagram would be like this. 2 variables would point to the same piece of data on the heap. And when both variables are out of scope, they would just free the same memory on the heap using the drop function, which will cause the double free error. So this seems to be quite ideal, but when it comes to handling the real operations, we would have the error called double free error, because when the second variable is out of scope, it is going to be removed as well as the data on the heap. And then for the first variable here, when it is out of scope, it will be removed, and it will also try to remove the original memory that is already removed by the upper member on the stack, which is my string 2. So in this situation, we will have the double free error because we have already freed this heap memory already when the second attempt is made. Okay. So Rust just treats the original variable as invalid when the new assignment is done, in order to avoid the double free error. The original variable would not use the drop function to free the memory since it is already invalid. Double free error can be avoided. So the programming in Rust would try to remove this variable, so that this variable will no longer be existent, and when it is not existent, it won't try to free the memory that is already freed by the variable on top of the stack. Okay. So effectively, the pointer would just appear in the second variable. That means the data on the first variable is moved, but not copied to another variable, so that the value on the heap has exactly one owner now. So we only keep one owner at a time to keep track of the memory on this heap. Okay. So let us see the result of running this part of the code. Okay, you can see that both strings are A, B, C. Okay, so here movement has already taken place, so my string will no longer be existent when my string 2 is already assigned. That means this situation will be like this one. When the assignment is complete on line number 16, okay, the original variable called my string will be gone. That means the heap allocated memory will be moved from my string to my string 2. That's why I can print out my string 2, but not my string after this assignment. Let me see if it is the case or not. So you'll see that I have a compile time error. the compile time error is like this. Borrow of moved value, my string. Value already borrowed here after move. So you see that this action has already moved the value on the heap from this variable to another one. And this variable no longer points to the string already. Okay? That means the value is moved. Okay? So that is something like this diagram. When the movement has been completed, the original variable can no longer be used because it doesn't point to any memory on the heap already. Okay? And let us talk about the way to make a deep copy. Since we know that the movement would occur when we assign a variable to another one, if we want to keep a deep copy, we have to use the clone method so that we have two pieces of the same content on the heap. Okay? So if we use the clone method, the heap would have two separate pieces of data with the same content. So let us see how we can achieve this thing. Okay, you can see that my string 2 is assigned by this method, my string.clone. Clone here is to create a separate memory on the heap. So of course my string 2 can show ABC. And how about my string now? You can see that it is allowed now because we have two pieces of separate memory on the heap. So even though the assignment is done, because of the use of the clone method, there are two pieces of data on the heap. Each of them is referred to by a separate variable. Okay? So you can see that after the assignment of my string 2, I can still get my string back. Okay? So let us talk about another topic. Strings can be mutated actually. Since the value on the heap stay on the heap, not on the stack, the values on the stack cannot be varied, but the data on the heap can be varied. How can we do so? We already know that we can use the push string method to make the string mutable. The idea is like this. Of course, we have to turn the variable to be a mutable one by using mut keyword, and then I can use push string method so that the string can be elongated. So let me see the result of this code snippet. You can see A, B, C, D, E, F right here. Because this push string method is going to add some content at the back of the original string on the heap, okay? And then let's talk about the ownership about functions. When the values stored on the stack and on the heap are passed to the function as the arguments, the same principle would apply. Principle means the ownership principles. During the passing of the stack value, a copy is made and is passed. During the passing of a heap value, the function would own the heap value, and the original variable that owned the heap value becomes invalid because of the movement. Okay. The drop function would clean the heap variable when they are out of scope. That is the same as the previous case. And when the values need to be returned to the calling function, movement will also take place, and the value will be moved to the calling function. So when we have a return value, the return value would also be put to the calling function. So we can also move the return value to other variables. So let us see this example. This example is quite long. I have A, which is a certain integer, B is a heap allocated string, and then I want to call a function called do something on integer, which is this one. So I just print the value passed to the function. So when this passing occurs, I would have to make a new copy so that the copy is put into the function. So this 1, 2, 3 will be copied and put to the function. Okay. And if I want to handle a string that is passed to the function, B will be moved into the function. That means this string will be moved to the function, and this B will no longer help us locate the allocated memory on the heap. Okay. So for this function, we will do the movement so that the string on the heap will be moved into the function. Since A is still on the stack, printing is still allowed. So I already mentioned that 1, 2, 3 will be copied to the function. So this function will just get a copy of A. So A is not moved into the function and A can be called. But B cannot be called because it is already embedded after the movement into the function called do something on string. That's why we cannot print out B. And the string initially inside the function is moved out to the calling function. So return a string here is a function. So I just want to move the string in the function to the outside. So I don't have a semicolon here, because if I put a semicolon here, it means I have a certain statement rather than an expression to be returned. Okay. So when we return a string here, the value will be moved to C. So this string content XYZ will be moved to C. Okay. So let us just see the result by running the program. And before I do so, I just try to see if I'm able to print the result of B after the movement, which should not be allowed. Okay. Borrow of moved value B. Borrow here means taking the reference of a variable that is stored on the heap. So you see, B is already moved into the function, so I can no longer print out B because this B is already invalid after the movement. Okay. So let me try to play with the code. 1, 2, 3 means this part which is obtained from A here. Even though the value is passed to the function, we just pass a copy of this stack value into the function. So this A still exists. Okay. 1, 2, 3 is obtained by the do something on integer function. Okay. So this function is going to just print out the value obtained from the argument, and the argument is just obtained by copying the original value of A into the function parameter. Okay. So I will have 1, 2, 3. And then I will do this do something function on string. Okay. So for string here, I would just have ABC as the answer. ABC now is already moved into the function, so B will no longer exist. Okay. And then I print the value of A again here, because this A is still existent. I haven't really moved this value into the function, because for stack values or for the primitive types, copying can be quite straightforward on the stack. And let us see. The final thing to do is this one. Return a string. So I can get XYZ as the answer. Why? Because this XYZ originally is stored in the function, and when I call this function, I want to return the string to the outside world, which is stored in a variable called C. And the string called XYZ will be moved into C. That's why I can print out this value of C, which is a value that was originally in the function called return a string. Okay. Now let's talk about another concept called references. If we don't want to move a heap value into the function when we pass a value into the function, we can pass the reference to the heap value to the function. Now we already noticed that for this function do something on string, when I call this function, this string will be moved into the function so that I cannot access this value any longer. So if I want to access this value, even though I used a function to process it, I can have an idea by using the references. When we do the passing of the references, the function does not really own the variable, as the function takes the reference to the heap value. So in this case, when I put the reference into the parameter, the function would not own the variable. It just has the reference that points to the value on the heap. Okay. What is a reference? A reference is actually the address of the variable that points to the heap data. So the reference would help us locate the content of the heap data. A pointer does not own the heap data. The reference is helping us to point to the heap value as long as the value still exists on the heap. Okay. So a pointer does not really own the heap data either. The action of taking a reference is called borrowing. So we already saw this phrase here. Borrow of moved value. The word borrow here means something like here. The action of taking a reference is called borrowing. So B can no longer have the string here because B is trying to borrow the moved value. So the original value is already moved into the function, and when B wants to access this variable, it is no longer allowed. So that is called borrowing. And the ampersand symbol means that we take the reference of the variable or of a type. Okay, so let us see an example. Okay, let us see this example now. I have a string here, and then I can do the show uppercase function by passing the reference to this string. Okay, so the function accepts a reference to a string, and I would return a string. So the string would be s dot to uppercase. That means I want to change all the letters to uppercase letters. And the value will be returned because there is no semicolon at the end. So this part is an expression. And this expression will try to be put here, okay, which is shown on the terminal by using the print line macro, okay. And after calling this function, the original string can still be printed out because I haven't really moved that string into the function called show uppercase. So let us see the result. Okay, you can see ABC here. ABC is the result coming from the function. And I'm also able to print the original string back because the function doesn't really own the variable called my string. The function just borrows the string, okay, by using the ampersand symbol. So the function just does some borrowing, okay. It doesn't really possess the content on the heap, okay. So the idea is like this. When we do the S here, the S would point to my string. This S would point to my string, which is pointing to the heap allocated memory, okay. So S would point to my string, and my string has a pointer that points to the heap allocated memory. So this is called borrowing, okay. So S would just try to obtain my string, which is already a borrow of the allocated memory on the heap, okay. And we can talk about mutable references now. If we just borrow a value, we can't change it. So here, I just borrow a value, and I can't change the content of it. So here I just return the changed value, but this to uppercase method doesn't really change the original string on the heap, okay? If we really want to change a value after borrowing, we need a mutable reference. That means the function which obtains a mutable reference can change the value. And mutable references are indicated by &mut in calling the function and in declaring the parameter type. We have to notice something. No two variables can mutate the data at the same time. So we have only one mutable reference at a particular time. So let us play with this program. Okay, this program is like this. I have a string here, and then I do a function called pushLetter, so that I want to push a character into the original string. And then, in this situation, I want to do the mutation. That means I want to have a mutable reference called ch. Okay, and this ch would point to a part of memory on the heap, which corresponds to the string called abc, okay? And I push some new letter to the reference, and this reference is able to help me change the content on the heap as well. So when I print my string here, it is just that I have a letter D at the end. But we have to notice something here. The function still does not own the heap string because this is only a reference that is taken by the function. The function just borrows the string on the heap. And the function just borrows the variable, of course, and the function can change the value of the variable. So by using &mut keyword, the function can change the content on the heap, but the function doesn't own the value on the heap. So let us try to play with the program. Okay, you can see A, B, C, D here, printed here. That means the function is able to add a character at the end. And of course the function doesn't really own the value on the heap. That's why I can still print it out after calling the function. That is the meaning of mutable references, okay? We can see an important point here. There can be more than one immutable reference in a scope, and multiple immutable references are allowed because they just borrow the value. These references cannot change the value. So when we have immutable references in a scope, we can have a number of immutable references at the same time in the same scope, because all of those immutable references won't change the data content. That's why they can coexist in the same scope, okay? But there can be only one mutable reference to a value in the same scope at a time. No two mutable references are allowed. In this situation, Rust can prevent data races in this way. We cannot have two mutable references at the same time in the same scope. Otherwise, Rust doesn't know which variable can mutate the value on the heap, okay? When an immutable reference wants to use the value, it does not expect that its value can be changed by a mutable reference. So it means that we cannot have both mutable and immutable references together in the same scope, because the immutable reference doesn't want the mutable reference to change the content when this immutable reference wants to use the value, okay? And for Rust, we have to take care of a situation called dangling references. Rust wants to make sure that the data would go out of scope after the reference to the data is invalid. That is the major idea of the ownership mechanism. In technical terms, the lifetime of the value must be at least as long as the lifetime of the reference, okay? And we will discuss the word called lifetimes in other chapters, but now I can show you an example that discusses the dangling references. Okay, this function is like this. I have a variable It is obtaining the value from a function called showString, and I want to print the value obtained from the showString in the next line. So what does the function do? The function would want to return a reference to a string. And in this function, there is a mutable reference to a string on the heap memory, okay? And the function wants to mutate the content of the string on the heap memory. And it wants to add def after abc. And then the function wants to return the reference to that x, which is defined in the function itself, okay? But you can see that this part would fail. What does it mean by that? When this reference to x is going to be returned to the outside world, this reference to x is already gone when this assignment happens, okay? So when the function ends, this reference to x, which is the content inside the function, will no longer be existent. That means this value of a is actually unable to get this reference to x, which is in the function content, okay? So x is defined inside the function, of course, and when the function ends, the heap value of x is also dropped, and the reference to x becomes dangled. That means the return value here will be dangled. It is not existent when it is going to be assigned to a. When x goes out of scope, the function would also end, and the function ends so that the reference to x is also gone. That's why a cannot obtain the value from the function. To solve the problem, we just return the string and let the calling function take ownership of the string. So I can just use string here. And let me try. Yes, it can compile. So the value of x can be returned to the function, and the value of a can just take ownership of the return value of the showString function. So we can see that this content defined in the function can be moved to the outside world by using the ownership mechanism, okay? Okay, you can see that A, B, C, D, F can be printed out by using string, but not string references, okay? Because the movement can take place. The return value of the showString method is moved to A. And then I'm going to talk about a slice type in Rust. A slice is a continuous portion of the elements in a collection, and a slice is just a reference. It cannot take ownership, so a slice is a reference. Okay, this is something we have to remember. The size of a slice is not known at compile time. In order to specify a slice, we need to remember the position of the pointer and the length of the slice. Slices can be used to borrow a portion of a string or an array, as a slice does not take ownership. So a slice is just a reference, so it can just borrow some content on the heap allocated memory, okay? So let us take an example of a slice, which is called string slice. A string slice is a reference to part of a string. We can specify the starting and ending points to extract from a string. The string slice is in the form of %s and then start and end indices. Here, %s is the reference to a string s. The slice will include the starting position indicated by start and the character just before the ending position indicated by end. Start to end, and this end index will not be included. We just include the index just before this end value, okay? The smallest starting position is index 0, and of course the largest ending position is the length of the string, okay? If we don't give the start, then the slice will just start from index 0, and if we don't give the end, then the slice would go to the far end. That is quite natural. And if both the end and the end are not given, then the whole string is included, okay? So let us play with this example. Now I have a string called str, which is pointing to a string on the heap allocated memory, and then I can get the size of the string by using the len method. Okay, so I take a string, and then a string can help me return the length. Okay, and then I have two variables here, part 1 and part 2. Part 1 here is actually a string slice that helps me get the first half of the string content, which is ABC. And part 2 is helping me to get the second part of the string content. So we can see I have to use ampersand and then str. str means the variable that I want to indicate the string. And 0 here means the very beginning, which is representing the letter A. Length divided by 2 is 3 because I have 6 as the length. So 6 divided by 2 is 3. So I will have 0 to 3. 0 to 3 just means 0, 1, and 2 because 3 is not included. We just include the index just before 3. Okay. So for part 2 here, I would start with 3 and I will end before 6. So I will have 3, 4, 5 for the indices. That's why I can get the second part. And you can see that the inferred data type by the Rust analyzer would show me that, oh, part 1 and part 2 are both string slices because I just take the references to part of a string on the heap allocated memory. Okay. So let me play with it. Okay, you can see A, B, C, and D, E, F coming out. And of course, the two string slices don't possess the string on the heap allocated memory. These two variables, part 1 and part 2, will just borrow the string. Okay? So the diagram is like this. The string is like that one. It has a pointer that is pointing to the heap allocated memory. And part 1 is going to point to the first part of the string. And part 2 is pointing to the second half of the string. To be more precise, part 1 points to index 0 of the heap allocated memory, and part 2 is pointing to index 3 of the heap allocated memory. So the pointer would try to point to the start of your part of your string on the heap allocated memory. Okay? And then we can talk about string literals. String literals are also string slices. The variable that stores the string literal is a string slice. This string slice is the reference to the string literal in the library. Therefore, a string literal is immutable, and the string slice is an immutable reference. Now let's take a look at the following example. I have a string literal here called ABCDE. And you can see that I provide a string literal by using a pair of double quotation marks. Okay, so we have a string literal, and the string literal has a variable, and this variable is of the string slice type. That means I want to point to the memory on the binary. Okay, the binary will store the string literal, which is this one, and this variable is pointing to the binary file that stores the string literal ABCDE. Okay, so by using the reference to a string on the binary, I can print out indices 2 and 3 respectively. That means I have C and D. Because 4 is representing character E, I have to stop before character E. That's why I will stop at D. Okay, let me play with it. Okay, I have C and D coming out. Because this, my string variable, is giving me a string slice, and the string slice is just the part stored in the binary file. Okay? And then let's talk about the array slice. An array slice is of course a type of slice that takes the reference to part of an array, indicated by the starting and ending positions, as usual. The array slice would store the first element to point to, plus the length of the slice. So what does it mean by that? Let us take an example right now. I have an array right now, and my slice here is a reference to part of my array. So I want to take a reference to the array, and the starting point is index 1, so I will have this one. And 4 is 1.9, so I will just take out 6.1, 7.8, and 3.5. Okay, so my slice here would just refer to these three floating point numbers. So my slice is just having these three numbers, and when I call my slice index 1, it just points to 7.8, which is actually the second element in the part indicated by the array slice. Okay, so let me play with it now. Okay, let me play with it. Okay, you can see 7.8 coming out. And this is just because my slice here is actually capturing these three values. Okay, and these three values can be referred to by using the indices. Index 0 of my slice would point to 6.1, index 1 would point to 7.8, and index 2 would point to 3.5. That's why I would have 7.8 as the answer to my slice index 1. So we have already talked about so many things about ownership, references, and slices. Okay. Now let's take a look at some examples of ownership in Rust. The first one is like this. I have a string called S and a string called T. Both are stored on the heap allocated memory. And then I want to concatenate T to S and want to show the first 4 characters of S, which is the concatenated version. So how can I do it? Let me show you my way first. So suppose I have a string called S and I have to make it mutable because I want to change the content of it. That's why I have to make it mutable. And then I have another string which is put on the heap allocated memory again, and this variable called T doesn't have to be mutable because I just want to change the value of S but not the value of T. That's why I can make use of the reference to T to help me change the content of S. So the way to change the content is to use the push string method. Now I can pass the reference to T to the method called push string, and the value of the string S will be changed by this method. And since I just used the reference to T, the variable T doesn't have to be mutable. Now since I want to print out the first 4 characters of S, which is the concatenated version, I just want to indicate the bytes involved. And we know that for Rust, each character needs 1 byte. That's why I want to show the first 4 bytes. That's why I can use period 4 to indicate bytes 0, 1, 2, and 3. So I would just print out A, B, C, D, which is meaning the first 4 characters of the concatenated string. Okay, so let me see the result. Okay, you can see A, B, C, D coming out. That's why I can print out the first 4 characters after the concatenation using the push string method, which takes a reference to a certain string on the heap allocated memory. Okay. And then we can take a look at another example. We are given a string called S and the start and end indices. And then I want to pass all of them into a function that returns the portion of the string with start and end indices inclusive. That means I want to show a certain portion of a string indicated by the start and end indices. And after calling the function, I want to print back the original string. That means I don't need to mutate the original string called s, and I can still do my task. So is there any way to do so? Yes, it is possible. The idea is to make use of the reference to the string. So let me show you my way to do it. So suppose now I have a string called s, and since I want to print the original string back, I don't need to make it mutable. I can make use of the reference to this string on the heap allocated memory to do the task. And I want to indicate the indices to start and end the copying, which will be done by the function that I'm going to write. So I'm going to write a function called getPortion, and the result will be stored in the variable called section. And you can see that this getPortion method function just uses the reference to the string on the heap allocated memory. That's why I have an ampersand. And of course I have to use the start and end indices in my function. And after calling the function, I can print out the variable called section as well as the variable called s, which is not changed by the getPortion function. So I'm going to print out the section variable and the s variable. So now I'm going to write the getPortion function for you. So I have to use this signature. Some string here is just accepting a string slice. This is consistent with my function call here. And the initial variable means the start, and the ending variable means the end. And we have to notice something here. We want to use the usize data type instead of i32 or u32, because for string slices, they don't use i32 or u32. So this is the reason why we have to use usize as the data type, because for using the indices, Rust disallows the use of i32 or u32. And of course the function return type has to be a string slice, which is consistent with the variable here. Okay. Okay, you can see that I can just return a portion of the string passed to the function, and the starting position is of course called initial, and the ending position is called ending plus 1. So it means that I'm able to print out the character indicated by the ending variable. So I have to use 2 dots to represent that I want to make a range from my string slice. So let us see the result. Okay, you can see day has come out. So for index 2, it means that I want to print out the 3rd character. And for 8, I want to say more characters from character D. So 2, 3, 4, 5, 6, 7, 8. So you can see that I can include the space after the character S. That's why you can see that the answer is day is, and of course we have to include the space after the character S. Okay. So we have to include both the starting index and the ending index. Okay. And of course I'm able to print out the original content of the string called S, because I haven't really changed it in the course of my program execution. Okay. Now let's see another situation. We want to override the function that accepts a string, and the function appends the length at the end of the accepted string and then return the altered string. And the altered string is printed after calling the function. So let me show you the way to call the function first, and then I'm going to make the function for you. Now I have a string called s, which is a mutable one because I want to append something to it after the function call that I'm going to make for you. And I want to do the changing of the string by using the change string function. And this function needs a mutable reference. So I have to use ampersand followed by mut to indicate that the parameter here is actually a mutable reference. Of course, I have to print the mutated string afterwards. And now I'm going to write the change string function for you. Now the function doesn't return anything. That's why I don't need to indicate the return type of the function. And you can see that the change string function inputs a mutable reference to a string which is stored on the heap allocated memory. And let me continue. Now I want to get the length of the string which is obtained by the mutable reference, and I put it in the variable called L. Okay. Now I want to do some action that I will shadow the original variable called length. So I'm going to change the length from an integer to a string. So I'm going to tell you the way to do so. Now the key idea is like this. I want to change the length, which is an integer, to a string by using the to_string method, which helps me to return a certain string which is stored on the heap allocated memory. So the length here is already shadowing the previous length variable, which was an integer, but now the length variable becomes a string due to the shadowing by using the to_string method. And now you can see that I want to use the pushString method so that I can take the reference of the variable called length and the string passed to the change string method will be changed to another one by adding some further string which is obtained by a reference to it. So you can see the result after I have run it. At the beginning I have a string called s, which is having the content called ABCDEF, and then I can call the change string function so that I'm going to add the length, which is an integer, to be converted into a string. So you will see that I will have ABCDEF6 as the answer. So let me play with it. Okay, you can see ABCDEF6 has come out. The meaning is like this one. The length is 6, which is originally an integer, and after doing the shadowing action, it has turned to a string, and this string can be concatenated to the original variable s. So you can see 6 has been part of the original string. Okay, so ABCDEF6 has come out. So that is the idea of using shadowing to do the concatenation of a string by a number originally to become a string. Okay. So we have already seen 3 examples of ownership in Rust. The first one involves the use of the reference of a certain content on the heap allocated memory. And the second one involves writing a function that uses the reference to a variable on the heap allocated memory. And we can also see the use of string slices in the function definition. Okay. Finally, we have another example that involves the use of shadowing to help me change the nature of the variable type. And that changed variable will be used in the upcoming processes of doing the concatenation of a string by using the reference to that shadowed variable. Now let's take a look at structs. Struct here means a structure. A structure is a user-defined type that is composed of a number of primitive types or heap allocated types. So we can say that a structure is a complex type. So we will try to set up a structure and create instances from a structure. Each pair of the data types and the data names is called a field of a struct. And we can end each field with a comma even for the last pair. And we will show a demonstration that describes the way to set up a field together with a key value pair. Okay. An instance of a struct will consist of data types and their corresponding values. So the key value pairs will be stored in a certain instance. And if we want to access the value of a key, we can use a dot to do so. So we will demonstrate all these things in some examples later. So we can see a way to create a structure and an instance or a number of instances. The instance can be mutable or immutable. It doesn't matter. We can have these possible ways to create our instances. Notice that when an instance is mutable, it means that all the fields of an instance are also mutable. So let us see the way to create an instance. Now we can see that I have a structure like this one. Struct followed by the structure name. And we have to use the upper camel case notation for structs. Okay, so I have a field here. Field is name, field is age, and field is on study leave. So these are the fields, and the fields would have a certain data type called string for the first one called name, and age will be U32. Age is a primitive type, okay, and is on study leave is also a primitive type. So I would like to use a Boolean data type. So I say BOOL as the type, okay. So I contain the field and its corresponding data type in a pair of curly brackets, okay. So when I call the struct to make an instance, I can do something like this. Let Peter equals student, followed by the key value pairs. The first key is the name. The value is a string on the heap allocated memory. And the second key is age, which is 17, which of course follows the U32 data type. Okay. And the third key is on study leave, which is a Boolean variable. That's why I can say true. So I have a certain instance called Peter. And Peter is now immutable because I haven't used any keyword like mut to tell Rust that it is a mutable instance. Okay. So we can use the instance.key to access the value. So when I say Peter.age, I can go to the instance called Peter, and then I can get the field corresponding to this instance, and then I can get the value back. So I will have 17 later on when I play with it. And now I can create a mutable instance by using mut before the variable name. So suppose I have a variable called John, And John is of course a student instance, so I use the student struct again to create another instance which is now mutable. So since John is mutable, all the fields in John can be mutated using the dot notation. What does this mean by this one? I can show you an example. John.age equals 18, so I can change the key value pair of this mutable instance after I have already set up this instance. Okay, so I will have 18 later on. So let me play with it. Apart from the warnings that tells me that I didn't use all of the variables, I can have 17 printed out and 18 printed out respectively. Okay, so we can see the way to get the value of a key, and we can change the value if the instance is a mutable one. Okay, and then let me tell you something about the struct update syntax. We can use the previous instances to make our new instances, and we will see an example like this one. Notice that if a heap allocated value of one instance is updated to another instance, the previous heap allocated value becomes invalid because the movement has already taken place between the two instances. Okay, this is a bit abstract. That's why I have a certain example to help you understand the situation. Okay, this example is quite long. So suppose I have the struct as usual, which is the same as the previous one. Then I have a Peter instance, which is an immutable instance. And then I create another instance called John. And you can see that I have something special here. Age is using the Peter's age. So I would have 17 for the age of John, actually. Peter.age refers to the age of Peter, of course. So this value would be obtained from another instance. And of course I can have another name. And here, another field follows Peter's field. And of course I can do similar things as the first part. This key called is on study leave is just using the same value as that of Peter. Okay, and when I print the John's age, I would have 17, which is the same as that of Peter. And now I have another instance called Raymond, and Raymond has only a distinct name, and other key value pairs would follow those of John. Okay, so the remaining two key value pairs, like the age and the is on study leave variable, would follow those of John. So you can see that Raymond's Boolean variable would be the same as that of John. Okay, so let us play with this code. Okay, let us see. John's age would be 17, of course, because it just follows Peter's age. And Raymond.is on study leave is the same as John's.is on study leave, which is true, of course. Raymond's name is of course Raymond because I haven't used other instances content to help me set the name of Raymond. You see, I have used another heap allocated memory to represent the name of Raymond. Okay. And then I will talk about a property called fieldInit shorthand form. What does it mean by that? Let's see. If we make a function to create an instance by passing the values of the fields, the function parameter names can be the same as the field names. So we will see this example very quickly. And we have to notice something more. The standard format trait can be used by the standard types, but not for user-defined types like the structs and enums. We have already learned structs shortly, and enums will be discussed later. All the types can derive the format debug trait. Therefore, the structs and enum instances can be printed out. So we will try to derive the debug trait, and we will have other sections to talk about the debug trait, as well as the derivation of the debug trait. So let us play with this example. Okay, now I have a struct as usual, and before I declare a struct, I have to say derive debug here. The derive attribute here is actually helping me to implement the debug trait, which is a trait provided by Rust. We put the attribute above the struct declaration so that I can use this notation or this notation to print out the struct fields. So I will try to print out the struct fields like this one here. When I have a hash sign here, the printing will be one key value pair on one line. Okay. So Raymond here is a student that is obtained by a function called getStudent. Okay. For the getStudent function, I have to pass a string and a certain integer, and then I will return a student type. And the return value would be a student instance that uses the name here, the age here, and the is on study leave key here. Okay, so this key value pair is an additional key value pair to be put into the return value of this function. And name and age here are just copying from the function parameter list. Okay. Name here refers to the name here, which is obtained by the function argument, and age here is just this age, and this age is just obtained by this function argument. Okay. So name here and age here will not need to be repeated on the these two lines in the return value of this function. Okay, I can just use name to represent the function parameter in the parameter list. Okay, so let me play with the function. Okay, you can see that I can use the notation here to obtain the key value pairs of the Raymond variable. Okay, so Raymond is of student type, and the content of this student is shown here, one line by one line. One key value pair is on one line because I've already added the hash sign here. If I don't add the hash sign here, I would have all the key value pairs on one line. So let me check this situation now. Okay, you can see that all the key value pairs are put on one line if I don't include the hash sign. Okay. So when we derive the debug trait, we are able to use this notation: a colon followed by a question mark, or a colon followed by a hash sign followed by a question mark. Okay. Of course, we don't always need to use the derive debug trait here. We can implement our own display trait on structs and enums to adjust the format of text printing, so we can have our way to print out the content of a struct instance And the display trait will be discussed in other chapters, okay? So we don't always need to use this approach to print the content of an instance. We can have our own implementation of the way to print the content out. And then let's talk about tuple structs. A tuple struct is actually a struct that has no field names included. Only the field types are included in the declaration. So here we have an example. So I have a structure called chess position, and I don't say any name to indicate the name of the keys in this structure. I just say the data type of the first parameter and the data type of the second parameter, okay? Tuple structs are useful when we want to create instances of tuples of the same compound type, and when we have no need to give names to each element of the tuple. So we can see such an example right here. Okay, I have a struct like this, chess position. The first position is in the form of letters, and the second parameter is in the form of numbers. So I can do something like this. Knight is at this position on the chessboard, and the pawn is on this chess position, okay? So I can print out knight.0 to get g back, and I can print out pawn 0.1 here to indicate the value of 2. So we can use parentheses to surround the data types to indicate a tuple struct, okay? So let us see the result. Okay, you can get G, which is knight.0, and 2 for pawn 0.1, okay? So we don't need to say that it is meaning the column and row number, okay? We can be pretty sure about the chess position. That's why we don't always need to say the keys explicitly, okay? And then we can talk about unit-like structs or unit structs. It is a struct with no values provided in the declaration. It is useful when we want to implement a trait on a type that has no fields. So a struct doesn't always have key value pairs. We can just have a name followed by a semicolon to provide a unit struct, okay? This struct is useful when we want to provide some traits on this struct. So possibly we will have some chances to see this kind of application later on. And then if we want to make some methods for a structure, how can we do so? We can use the implement keyword to implement the methods for a struct. The keyword is impl, okay? So methods are created for structs or enums and trait objects so that an instance of these user-defined types can perform some operations on itself. Method parameters are similar to those of functions, except that the first parameter must be self, ampersand self or ampersand small letter self in shorthand form, okay? So we can have this data type or this data type in shorthand form. Okay, so we will see some examples later on. Ampersand self here means that the method would borrow the instance. We don't want the method to take ownership of the instance, so we just take the address of that instance on the heap allocated memory, okay? We can have more than one implementation block for a struct. So we already know the methods, and how about associated functions? All the functions in the implementation block without using ampersand self are called associated functions. And the functions without ampersand self as the first parameter are often used to make constructors. So we use self type as the return data type. So let's see an example about the use of methods and associated functions. So suppose I have a vehicle structure here. I have 3 key value pairs, and I already made a number of instances of a structure. This is called my car, and this is called my taxi. And for my car, I just use the usual way of creating an instance by declaring all the key value pairs explicitly. And of course, I can print the information about this instance by using some functions that I will describe later on. Okay, I have a years past method, and I have also a describe method. And here, my taxi is created using a constructor. So I can have the structure and then the method. Yes. Oh, sorry. It is a function because this function doesn't have &self as the first parameter. Okay, so taxi here is a function. Okay, and I can use the taxi function to create an instance. So we can treat the taxi function as a constructor. Okay, so the return value will be self, which is in capital letter S, and the value passed to the function parameter list will be used as the content of the instance. Okay, and we can see that I have also got a function, and actually it is a method called is newer. So it is a method that uses a reference to other instances. So when I want to use the reference of the instance itself, I would say &self. If I want to use another instance of the same type, I can use &vehicle. So &vehicle is a reference to another vehicle instance. Okay. So here I use impl to do the implementation block. So this one is the entire implementation block of the structure called vehicle. Okay. So I have a method called years past, and the first parameter is self : &self. So it is actually the long form of &self here. Okay, and you have to notice that this S has to be in capital letter to describe the data type of self, which is just meaning the vehicle type. Okay, and the shorthand form uses the small letter s. Okay, and self here is meaning the reference passed to the method. Okay, I can say self.vehicleType, self.color. So when I get an instance, I can go back to check the key value pairs of that instance so that I can get these two values out. And of course, for the isNewer method, I can get the instances by using the two references, and then self refers to the instance that calls this method, and the other variable refers to another instance that is passed to the function. Okay? So let me play with this whole program now. Okay, you can see that I have some answers coming out. Used for how many years? My car has already used 4 years, because I can put 2024 into the function. Sorry, this is a method. So the method will help me get the current year, and the current year is going to interact with the self.year. So I do current minus self.year. Self.year means 2020 because my car has a year of 2020. So I will have 4 as the answer. 2024 minus 2020 to get 4. Okay. when I call the describe method, I will just print out this vehicle type as well as the color of that particular instance. Okay, since it is my car that calls the method, the information of my car will be printed out by the describe method. Okay, and for this one, my taxi.vehicle type. So I have the taxi first, and then I can go to the vehicle type. So I will get taxi, of course. That is quite trivial because it just takes out the instance and then the key value pair of that instance. Here I just want to tell you that I can use the constructor to create an instance. Okay, and this is the newer method. So which car is newer, my car or my taxi? So we can go to the function, the method. Self.year is my car's year 2020, and my taxi's year is 2018. So we can see that my car is a bit younger than my taxi, so I will have my car being younger. That's why I will have 2020 larger than 2018. That's why I will have true coming out, because it is a Boolean expression. And I will just return the Boolean expression which is true to the outside world. Okay. So we have already learned a lot of things about structs, and we can add some methods or functions into structs, and we are also able to create our own structures together with some instances from those structures. Now let's take a look at this example about structs in Rust. We have two students and their marks in the recent two tests, and we want to find out the average marks of the two tests for each student. And for each of the students, we have to find out the higher of the marks from the two tests. And I want to show the higher average marks of the two students as well. So it seems like the steps are quite complicated, but I'm going to show you step by step. So the first step is to show the main function so that I can design the way to call the functions that I'm going to write. So I want to make a certain instance from a student's struct, and the way to create that instance is to use the new method that I'm going to write. Okay, I will also create a certain instance called John, which is of student type, and of course I want to use the new function to call it, and the numbers at the end of the string which represents the name are actually the marks for the recent two tests. Okay. Because I want to show the average marks for each of the students, I have to write a method called average so that the two instances can call this method to find out the average marks for each of them. I want to make a method called show higher marks so that the larger of the two values of the marks will be shown for us. Same for John, I want to show which one of the marks for John is the higher one. Okay, I want to write a function for the student struct, which is called higher average. So I want to see which student has a better average mark. So I want to pass the references to both Peter and John to this function, and then I'm going to find out which one of the students has a higher average. So we can see so many structures, and methods to produce. So let us try to start with the structure first. Of course, when you see the main function, you see that I have to include a string followed by a mark and another mark. That's why I have to say U32 for the marks and string for the name, okay? And then I want to add some methods to this structure. That's why I want to write the implementation block for this student structure. So the first function to make is the new function, okay? Now the new function is going to create a type of self. So self here starts with a capital letter, and this self type means the student type, okay? And of course, I just make use of the structure definition to help me produce the instance by putting all the fields of my structure into the return data type, okay? Which is just self. Of course, this self refers to the student structure. Here we have already used the field init shorthand form, so that I just put the parameter names into the self type shown here, so that the first place would refer to the name, and the second place refers to the first mark, and the third place would refer to the second mark. And then I can just implement the average function. Now, since we have two integers and the average of the two integers can be a decimal number, I have to use f64 as the return data type of the average function. And you can see that when I have the parameter to be self, which is a small letter s here, I have to use the ampersand capital letter S to represent the self data type, which refers to an instance of the student structure, okay? So when we have the self data type being the input of the function here, it means that we have a method to produce. And you can see that I want to turn the mark 1 and mark 2 into decimal numbers of f64 type. And then of course I have to also turn the 2 here to be a decimal number. So I have a decimal number divided by a decimal number. So of course the data type of the answer would be f64, okay? So that is the reason why we have to convert the type of mark 1 and mark 2 to f64, and then I want to convert 2 to be f64 as well, in order to do the averaging that involves a decimal number. And the third function to do is the show higher marks. So I want to pass the instance reference to this function. So this function is actually a method, okay? So this one is the shorthand form of the long one here, okay? So I can just use ampersand self to replace the whole part shown here, okay? Okay, you can see that the first placeholder would be to put the name of a certain struct instance, and the second placeholder is going to put the result coming from the highest function, which takes self as the instance to consider. So here I have a new method called highest. So I'm going to write this method for you now. So of course, the highest function is actually a method because you can see that I have passed the reference to a certain struct instance into it. And of course, the highest method would return a certain integer in U32 form. So the highest method is quite easy to understand. I want to compare Mark 1 and Mark 2 for a certain student instance. This is represented by the self variable here. And if the first mark is larger than or equal to the second mark, of course the highest mark is Mark 1. Otherwise I would say the highest mark is Mark 2. And I just return Mark 1 or Mark 2 to this position. And this value will be printed out on this string being the second placeholder position, okay? And finally, I have to include a function called highest average, which is shown here. Highest average. So now I'm going to implement this function. The highest average function would return a certain decimal number. That's why the return type is F64, which is quite easy to understand. And I have to pass the references of two instances to the function. So S1 refers to a certain instance of student type, and S2 refers to another reference to a student instance, okay? Both are references. I don't need to really do the movement of the student instances into the function. I just need to take the references to help me finish the task. Now the implementation is quite easy. I just want to compare the average marks of student 1 and student 2. If student 1 gives me a higher average, I just print out the average mark for student 1. Otherwise, I print out the average of student 2. That is so easy to understand. And the entire implementation block is complete. So let me try to run the program. Let me see the problem. Yes, the average function here is actually a method. That's why I have to include the parentheses at the end. So let me try to run the program again, and we can check the average method again. So I have to pass the reference to a struct instance into the function. I would like to return a decimal number. That's why it is a method, and for the method I really need to put the parentheses at the end. So let me try to play with the program again. Okay, you can see the result coming out. So for Peter, the average mark would be 83 plus 32, and the answer would be divided by 2 to get 87.5 marks. And for John, the average mark would be 91 plus 86, and the sum is divided by 2 to get 88.5. And you can see that Peter's highest mark is 92, because I can call the highest function to help me get the highest mark for a particular instance. Okay. And of course, John's highest mark is 91 because you can see that 91 is actually larger than 86. And for Peter, 92 is larger than 83. So these two answers are correct. And then I want to show the highest average of Peter and John. And you can see that Peter's average is 87.5, but John has an average of 88.5. That's why I'm able to print out John's average, because John has a higher average than Peter. Okay, so that is the end of the program that can help me to achieve all of these goals. Now let's talk about enumerations or enums. Enumerations are a type of listing all possible variants. An enum instance can only pick exactly one of the variants. When we create an enum instance, we use the enumeration name as the namespace. Then we add 2 colons followed by the variant to denote the variant for that instance. We have to use upper camel case notation when we name the enums and its variants. Upper camel case notation means that the first letter is a capital letter, and when we want to combine other words together to form your name, all the first characters of your words have to be uppercase letters. Okay, so we can see this example. Vehicle starts with capital letter V, and motorcycle would start with capital M, of course. Motor car would start with M, and the C here would also be a capital letter, because I join motor and car together. And truck is of course just one word, then we just use the uppercase letter for the first letter, okay? So if we want to make an instance that has exactly one of the variants, then we can use vehicle : motor car to represent this variant. Okay, the variant will be motor car for my truck, for my car. Okay, and for my truck here, I would have vehicle : truck. So I'm able to pick up all the 3 variants by using 3 assignments. Okay, and we can also add more data to the variant directly. The data can be in the form of a tuple or a structure. So let us see this example. I have an enum called student. A student can have different kinds of identity. The student can be a primary school student, a middle school student, or a high school student. For a primary school student, there is a name for the student and the age. For the middle school student, the student also has a name in the form of a string together with the age. And for high school student, I want to include a struct as the content. Name, age, and is on leave variables are all put on the declaration of a structure. Okay, so the first 2 variants would have tuples as the information. Okay, tuple here and tuple here. But for high school students, I will have a struct instead. Okay, so let me play with the code now. Okay, Susan here is a student, which is a primary school student. So the name is a string, and of course the age is given here. Of course I can print the content of Susan later. And for David, he is a middle school student, so I have to show the variant together with the tuple struct that contains the information pertaining to this variant. Okay, and for Nick is a high school student, so I need to declare a structure to indicate the key value pairs pertaining to Nick. Okay, and of course I can print the content of Nick. So let me try to play with the code. Okay, apart from the warnings, I can see that Susan has this answer. Primary variant with the name Susan and age 10. For David, he is a middle school student. The name is David and the age is 13. And for Nick, I will have a structure coming out. Name equals Nick, age equals 7, and is on leave equals true. So I can have tuples or structures to represent the further content of a particular variant. Okay. Same as variables, enum instances can be declared as mutable by using the mute keyword. So if I add net mute Susan, Susan is a mutable instance, okay? And for enum, there is a certain special enumeration called option enum. To handle the concept of null values in Rust, we have to use the option enum. We use option T to declare an option enum, okay? T here means a generic data type T that can be some variant or non-variant, okay? By using the option enum, we can specify a value that can possibly be null. If the value is null, we can use the non-variant. So, more specifically, the option enum has this format, some T or none. So the variant here means that there is a value of type T, which is a generic data type. And if the value is not present, I will just say none. Okay. Option is already included in the prelude. That's why we can use it directly without taking it into the scope. Okay. So let me try to play with this code. Now I have A, B, C, and D. If the value comes from the sum T variant, the generic data type can be inferred. So X is a character. That's why the Rust analyzer can infer CHAR, which is the character type. Okay. And since I have sum to represent the variant of an option enum, I can have option char being inferred here. And for 54 here, it is an integer, so the default integer type is i32. That's why B would have the inferred type as option i32. Okay. For letter C here, it is of option string type because you can see that I have a sum variant and the content of the value surrounded by the sum variant is a string. Okay. If the value comes from the non-variant, the generic type must be annotated in the declaration because the non-variant can happen in all data types. So if I have a certain variable that is having a non-variant, I must type the concrete type explicitly to the editor so that the option enum will infer the data type correctly. Okay, none here can mean that the original data is a string or is a certain integer and so on. With just the word none, we cannot know the data type that should be inferred. Okay, that's why I have to say it is a Boolean variable, but now the value is none, which is a variant of the option enum. Okay. Note that option T is not the same as T alone. There are different data types in Rust. So option T can mean that the value is present or is not present. If it is not present, I would just say that it is none by having the none variant as the answer. The data in a concrete type T must be valid. We don't check whether it is null or not. That is quite natural. When we say A equals 1, 1 has to be valid. However, data in the option T can be null. We have to check for the possibility when we write code in Rust. So if there is a value which can be null. We have to surround this value by the option enum. So the introduction of option T implies that we are safe to use values declared in the generic data type, because they must not be null, okay? Generic data type here. So if the value can be null, we have to wrap it with the option enum. That is the major idea of using the option enum, okay? And then I would like to tell you one more commonly used enum called ordering enum. There are 3 variants in the ordering enum: less, equal, or greater. They can describe the result when 2 values are compared. And since ordering enum is not in the prelude, we have to bring it to the current scope. The idea is to use the use keyword followed by standard : CMP : ordering. So the module called CMP is storing the ordering enum. So let us see how we can use the ordering enum. Okay, I have a function here that returns a type called ordering. So this ordering is the ordering enum. So I want to compare 2 integers. And if a is less than b, I would return this variant called ordering : next. Else, if a is larger than b, I would return a variant called ordering : greater, which is just another variant, okay? Else, I would just return a variant called ordering : equal, okay? Now when I use the compare numbers function, I have to use 2 numbers. Num1 is 10, num2 is 5. So what will we get? Since 10 is larger than 5, I would have greater. So when I have the variant being greater to return from the compare numbers function, I would just print out num1 is greater than num2. So you can see that I don't have a semicolon at the end. That's why the variant will be returned. So I have to match the result, which is the answer coming from the compare numbers function, okay? So if the result is ordering : next, I would do something. If it is ordering : greater, I would do something. If it is ordering : equal, I would do something else. So let us see the result. Of course, you will get num1 is greater than num2, because the function returns ordering : greater variant, okay? So we have already discussed the ordering enum, the option enum, and the general way of creating an enum, together with the instances generated from the enum type. Now let's take a look at the example about enumerations in Rust. Now, there are a number of peripherals to recycle. We have a keyboard, a mouse, and a printer. And the number of years of each of them has been used are also known. If the suggested lifetime of the devices are also given, we can write a program to determine which of the devices should be recycled. So let's take a look at the implementation of this program. We have to set up the enumeration first. So for the peripheral enum, we have a keyboard variant first, and the keyboard variant would have 2 values bound to it. The keyboard type, which is a string, and the years used, which is an i32 value. And then I'm going to set up a mouse variant. Since a mouse is a simple device, we can just indicate the number of years it has been used. So I just need to include the integer type in a pair of round brackets. So for a mouse, we don't have a variable name attached to the number of years used because it is already known that this value is representing the number of years used. And then I can set up the printer variant. And for a printer, there are so many things to consider. The printer type, as well as its dimensions, together with the number of years used. So we have a number of values attached to the printer variant, and each of them has the name given to the variable. And then I can set up the function that is going to check whether each of the devices is getting too old, and the device should be recycled or not. So you can see the function signature as follows. I need to pass the reference to a peripheral enum instance into the function, and then I can also include the minimum number of years that the peripheral device can use, and I'm going to check whether the peripheral device is too old, which is having a number of years used that is larger than the minimum years. And this function is going to give me a Boolean value to indicate that whether that particular device is to be recycled or not. Now you can see that the Rust analyzer is able to give me the corresponding values bound to the keyboard variant. But since I just want to check the number of years used, the keyboard type can be ignored. To ignore a certain value, I can use two periods to help me do so. So for the first possible type of enum variant, which is a keyboard, I have to indicate this keyboard variant by including the enum name followed by 2 colons, and then I give the variant name. And you can see that I want to just check the number of years used. That's why I can ignore other values bound to the variant. So I can use 2 periods to indicate that all other values are ignored in my current code, okay? And of course I have to check whether the number of years used is actually larger than or equal to the minimum years of a certain device. If that device is already too old, I can just return true as the Boolean value. And of course I have to include all the other possible variants so that the match keyword is able to consider all the possible variants. That's why the program isn't complete yet. I have to include the other 2 types of variants. And we can see something here. We have an asterisk here. The asterisk is going to help me dereference a pointer to get the value of the number of years used by this particular instance. So this asterisk is going to do the dereferencing for me, okay? Since I got the peripheral instance address, I can use the dereferencing tool to help me get the corresponding value of that particular instance, okay? Now we can take a look at this variant. The variant only contains an unnamed value, which is of type I32. So I can put this value to be x, and then I can dereference that value to do the comparison. So after I have got the reference to a certain peripheral instance, I can check for its variant type, and then I can dereference that value attached to the mouse variant to do the comparison. Okay, for the printer variant, I just need to check for the number of years used. That's why I can also use the to periods to help me ignore the rest of the values attached to the printer variant. And of course, I can do the comparison again by doing the dereferencing action with the help of an asterisk, so that from the peripheral instance, I can take out the value of the number of years used from this address. Okay. Now I'm going to use the isToOld function to help me do the comparison. Now you can see that the Rust analyzer has already helped me to include a number of values attached to the variant, so I can just fill in each of them. Okay, you can see that I have already filled in a lot of pieces of information for a particular printer instance called my printer. Okay, so I can continue to do the rest of my peripherals. Okay, I've already finished my keyboard instance. Okay, I have also completed my mouse instance, which corresponds to the mouse variant, and 2 here is just meaning the number of years used already, as defined by the enum declaration. Okay. So how can I call the isToOld function? Let us see. Okay, this is the first function call, isToOld, followed by the reference to a certain instance called my keyboard. That's why I have an ampersand here to indicate that I want to take the reference. And the second argument here means the number of years used. And you can see that the Rust analyzer is able to help me understand the position of the function arguments. The first one is about the device, and the second one is about the number of years, which is a minimum number of years. So for the second function call, I put my printer into it. Of course, I put a reference to my printer into it, and then the number of years to be used as a minimum is 4 years. Okay, I'll also include the third function call. So I want to check for my mouse, and I want to see that whether that mouse has already been used for more than 1 year. If the first instance has to be recycled, the recycle1 variable will become true. Then I can print out something. I just say that I want to recycle the keyboard. And I can do similar operations for the remaining two variables. For the second variable, I want to recycle the printer. And for the third variable, I want to recycle the mouse. So let us see if I'm able to play with the program to check whether each of the devices has to be recycled. Okay, you can see that I can have a chance to recycle the keyboard and recycle the mouse. Why? Because we can see that for the keyboard first, the number of years used is 3, and the number of years that a keyboard can be used is 3 years. So the number of years used is exactly equal to the minimum number of years that it can be used. So it means that the keyboard is already old enough to be recycled. And how about the mouse? For the mouse, the number of years used is 2, and the minimum number of years to use is 1 year. That means the mouse is already too old. That means the mouse can also be recycled. But how about the printer? Let us see. The printer has been used for just 3 years only, but the minimum number of years that it can be used is 4. That means the printer is still too young to be recycled. That's why the second variable here would just return false. And if it is false, I don't need to print out this statement to indicate that the printer has to be recycled. Okay. So you can see that there are some warnings here. Since I haven't used a number of values attached to the enum variants, I have this kind of warning. So it doesn't matter for our discussion. That's why I can leave these warnings as they are. Okay. So the program is complete. I'm able to set up my printer, keyboard, and mouse, and I can check whether each of them has to be recycled based on the number of years used by each of them and the number of years that it can be used. And the reason I have to use the ampersand is that I want to just pick up the reference to the instances so that the isTooOld function isn't able to capture or own the instance. So in principle, if I want to print out the content of the instance after the function call, it is possible. Now let's take a look at an example of using option enum. We want to write a program to check whether a person's name, age, and identification number are all filled in or not. If something is not filled in, we want to specify this piece of data. So before I do so, I have to create a structure first, and the structure has a number of fields that rely on the option enum. So the person struct has a number of fields, and since a person may not fill in all the pieces of information, it is possible that a particular field has no content. That's why I can use an option enum to indicate that a particular field can have nothing inside. And of course, it is possible to have something inside, but it is also possible that nothing is inside it. So this is the reason why I have to use the option enum to indicate all the fields. A person may not provide all the values of the fields. That's why each of the fields can be none. So now I can set up the function to check whether each of the fields is filled or not. I want to pass a reference to a certain person instance so that the function doesn't need to really own the instance. Okay, let us see the first part of the check field function. So if someone's name is actually present, the sum variant will become occupied, and the value of x is going to store the name obtained by the person variant, okay? And if it is really possible to get the name from the person, I can just say that the name is filled and the value of that name is represented by the variable x. So when we use the if-let expression, we can really pick up the content from the instance, okay? And since the name for a certain person is represented by the heap allocated memory, I can just need the reference of that particular memory on the heap to do the checking, okay? That's why I don't need to really move the name from the person instance to the check field function, okay? No movement of string is involved. String here means the heap allocated memory representing the name field of the person instance, okay? How about checking the age? I can have a similar idea. Okay, for age, you can see that I don't really need to include the ampersand symbol, because for an age, it is stored on the stack, and for the stack, we can implement the copy trait so that the check field function can really own the age. Okay. So I have to say again, it is not a function that owns the integer, but the sum variant here is able to own the integer. So I don't need to really use the ampersand symbol to indicate that the address of the someone's age is to be put to the sum variant, okay? And of course, if the age is really not none, the value can be obtained here and printed out. Otherwise, I just say the age is not filled. Now, let me handle the ID number. Okay, for the ID number, it is a string. You can see that it is a string, so it is put on the heap allocated memory. That's why I have to really use the reference to the person called someone, and I can use the address to help me indicate the ID number of that person. Okay, so for this person, I can get the ID number if it is not none. So if it can be captured by the sum variant, it means that I can just get the value of the ID number and I can put it into Z. And I can also print it out after the comparison is done. And we can really get the ID number from that person called someone. So if that expression is able to do the comparison for me directly, if it is present, I mean if the ID number is present, I can put it into Z. Otherwise, I can do something else. That means if the sum variant is not successful, I can do something else. Okay. So let me go to the main function to see how I can call all these functions and instructions. Okay, I can call the check field function in this way. I have a certain instance called Peter from a person struct, and you can see that for each of the fields here, it can be some or none. So it is possible that Peter hasn't filled in the ID number, but he has filled in the age together with the name, okay? And I can just use the check field function by putting the reference to the Peter instance, okay? And someone here is actually the Peter for now. The Peter instance is replacing the someone parameter to become the argument of the function, okay? And of course, I just need to use the address of Peter so that the check field function doesn't really own the Peter instance. Since the function just wants to read the instance, it is not necessary for the function to really take ownership of the instance. That's why I can use an ampersand to represent the reference to a certain instance. So let me try to play with the program. Okay, you can see that the name is filled because I have a string content surrounded by the sum variant, and I'm able to pick up the name, which is stored on the heap allocated memory, and it is stored in X in the check field function. And same for the age here. Since the age is stored on the stack, I don't need to use the ampersand to really take the reference to a certain variable on the stack. That's why the sum variant is able to own the age, which is owning the copied version of the age from the instance, okay? And for ID number here, we see that it is none. That's why I cannot go to this arm by telling us the identification number. Instead, I can just say that the identification number is not filled because it is none here, but not some, okay? So we can see that the program is able to handle the option enum quite successfully. We have to indicate that whether the sum or none variant of the option enum is used. Now, let's talk about the match expression. The match expression can return the first pattern that matches the enumeration. Upcoming patterns that appear later on are not checked, even though they could also be matched. The patterns here can include literal values, variables, wildcard characters, and so on. And in using the match keyword on an enum instance, all the possible variants will be checked. An arm has a pattern to match and the code to execute if the pattern is matched. They are separated by a certain arrow operator. The arrow is created by using an equal sign followed by a larger than sign. A certain enumeration can be in this format. Enum, and then I give a data type called direction, and for the direction, there are 4 possible directions: east, south, west, and north. That means a direction can have any one of the variants, okay? So here my program tries to match a certain variant. So if the variant is equal to direction east, direction south, direction west, direction north, then I will do something, okay? So each part is called an arm, and the arms are connected by using a comma, even for the last arm, okay? And in the operation to do for each match, I can say the direction number. So for east, it will be 1, for south, it will be 2, and so on. So the code to execute if the pattern is matched is put inside the curly brackets for a given arm, okay? If there is one line to execute only, the curly braces can be removed. That means for just one single action, we don't need to use the curly brackets, okay? So let me try to play with it now. Okay, you can see something like this one. enum direction, and the direction has a number of variants: east, south, west, and north. Okay, and for each of the possible arms, I have to tell the computer what to do for each possible arm. Okay, so my direction is actually direction south, so I have just one possible variant for my direction variable. Okay, so let me try to play with it. You can see that apart from the warnings that tells me that I haven't used all the variants, I can show direction number 2 because my direction here is meaning the south direction. Okay, so the variant is south. Okay, the variant of the direction enumeration is south. So I will just go to this branch to execute the content in this pair of curly brackets. Okay. And if we forgot to provide the arm corresponding to any one of the variants, the program cannot compile. That means when we use the match expression for an enum instance, like this one, my direction, I have to put all the cases for all the possible variants. Okay, so if I forgot any one of them, for example, if I forgot the north variant, is it possible to compile? You can see no, because I have a missing arm. So the variant called north is not yet handled. Okay. So we have to consider all the possible arms to consider all the variants. Okay. This is a property of the match expression for enum instance. Okay. And then we have to notice something. This is a situation when we use the match with patterns that bind to other values. If an enum instance binds to other values in a tuple or a struct, the pattern matching can consider those values too. So let us see this example. Suppose my enum variants would also bind to some tuples or some structs. So if I do the matching below, the tuple content or the struct contents can also be considered. So for example, in this example here, primary A, B. So primary A means the name in the string format, and B for primary means the age in I32 data type. So A, B can refer to any value that is of the corresponding data type for A and B respectively. Okay. Same for middle school student. X and Y can just refer to the name string and the age integer. Okay. And for high school here, high school variant follows a struct. Okay. So I can just pick up the name, the age, and is on leave Boolean variable for high school student. And for the high school student, you can see that I can show the content of this struct contained in the high school variant. So the name can be printed out as well as the age. And I can also see whether the student in high school is on leave now or not. If the student is on leave, I can just print something like this. Okay. So it means that the tuple struct and the ordinary struct content can be used in our matching. So let me try to play with it now. Okay, you can see something like this one. A and B are not used in the branch, so I will have some kind of warning. Same for X and Y for the middle variant. And for high school variant, the name, the age, and is on leave Boolean variable are all used. That's why I don't have the warnings coming out. So let me try to see the result. The student has the name, the age, and its on leave variable being true because this student is a high school student. Now you can see that the statement here, Nick is 17 years old, so I have really matched a high school student with the match expression. Okay, so I just print out the name and age. Also, I will also notice that the student is on leave now because the is on leave variable is actually true for this instance. Okay. And then let's talk about another situation, which is called matching with the option T enum type. When we want to match an instance with the option T enum type, we just apply the same principles to the option T enum type. So let us see an example. I have A, which is coming from a variant of the option enum, and B is of course another variant from the option enum. And then I pass these two option instances to a function called checkChar. So if I put A into the function, A is actually sum x. It means that I will go to this particular branch to really print out something. And for B, since it is none, the matching will just go to this branch to handle the situation when the value is actually none. So let me try to play with it now. Now let me just compile and run the program. Okay, for checkChar A, I will get we got X because I really put a variant of the option enum called sum x into the function, and when I see that a sum is matched, I will just pick up the character called sumChar in this branch, and then sumChar is actually the character x. That's why I can see we got x on the first line, okay? And for the second function call here, the value of none is put into x. That's why when we want to match x, I will get the second branch. So I will say we got nothing because I really got a none variant of the option enum, okay? And then we can use the catch-all patterns and the underscore to see what would happen if we want to use them properly. So if we want to use the catch-all value later on, we can use other keyword. So what does it mean by this one? Let us see this example. Now I have x equals 2 and I want to match x with these three branches. If x is 0, I do something. If it is 1, I do something. So what else can I do for other values? If you want to handle the other values, I can use other. And then for this branch, I do something. And this other will be used in our upcoming operation for this particular branch, okay? So of course, we have to notice that each branch would end with a comma, even for the last branch, okay? So let me try to play with this program now. You see, since x is equal to 2, it is not going to pass the first branch or the second branch. Then I will just go to this branch. And other here is meaning the value of 2, which is obtained from x, okay? So I would get 2 here for other. Of course, if I change the value of x to 9, I will get 9 as the answer. So other here means the value other than 0 or 1, and the value called other will be used in our upcoming operations, okay? What about if we don't want to use the catch-all value later on? If that's the case, I can use an underscore to replace the keyword called other. Then in the branch corresponding to the catch-all character, I don't really use the caught value. I can just have a unit type as the answer, meaning that I do nothing. So let me try to play with this situation. Okay, if x is 2, I will just do nothing. You see, nothing has happened because I just return a unit type or a unit value, meaning that I do nothing. Of course, if x is 0, I will just print out I got 0. Okay, I will get I got 0 when I put x to be 0, because the first branch is met. Okay. So we have to remember to put other or the underscore in the final arm, otherwise other arms will not be ever matched. So other and the underscore correspond to all other situations. So if they are put on the first arm must be correct. That's why I have to put other or the underscore in the final arm so that all other situations can be checked before I go to the final arm. Okay? And then I'm going to talk about the if-let syntax. The if-let syntax can help us to match one pattern, and other matches are not checked exhaustively. And when we use the if-let expression, the pattern is put on the left of the equal sign, and the value to be matched is put on the right-hand side of the equal sign. So let us see this example. I have the my direction, which is equal to a variant called west from the direction enum. And if let is shown here, okay, if let direction west equals my direction, that means the pattern to be matched is put on the right hand side, and the pattern is put on the left hand side. The pattern is the direction west variant, okay. So if my direction is having this variant, then I can do something by printing this sentence. If it is not the case, I can just do something else. And for the if-let expression, the else part is optional. We don't always need to include the else part for if-let expression, okay? So of course, the enum direction is in this format again. I have the 4 variants, and each of the variants may be matched using the if-let expression, okay? So let me try to play with it now. Now we can see something like this one. The pattern is on the left, and the value to be matched is on the right. If this match works, I will do this sentence. So let me see if it is the case or not. You see, I got this sentence, I got the west direction, because the instance is really talking about the west variant of direction enum. If I change it to other variants, I will get this sentence coming out. East, for example. I got a direction other than the west, okay? So you can see that if that expression is able to do the matching, and if I don't include the else part, the program can still compile. This happens because the else part is optional. So let me see. Okay, you can see nothing coming out, because I really did nothing for the else part. And you can see that the else part is optional. I can still do the thing even though I don't include the else part. So for the if-let expression, I don't need to always include the else part. The program will just end quietly, okay? So For the enum type, we can create our variants, and then we can use the match expression to see whether I can get any one of the enum variants or not. Okay, if an enum variant is found, I do something else, I have to do something else. And remember that I have to check all the enum variants when I use the match expression. Now, let's talk about the further pattern matching techniques. First, I would like to talk about the places that allow matching to be done. So let's talk about the keyword called match expression. And the idea of using the match expression is rather simple. The left-hand side of the arrow operator is a pattern, and the right-hand side of it is an expression. So the general idea of using the match keyword is like this. We want to match a value, so that I would like to see whether the value would match with a certain pattern. If I can match this pattern, I would do this expression. If I can match with another pattern, I will do another expression. Okay. But when we want to use the match keyword, we have to check all the possible cases of the value. The idea is like this. Let us see this example. Now I have a value called x, which is a Boolean variable. Okay, so now the value of x is false, and I have to match x with all the possibilities of this Boolean variable. So I have to consider all the possible cases of this variable, which can be true or false. That's why I have to put these two branches together. If I just put any one of these branches without considering the other one, my program cannot compile. So let us see that example. Okay, let us see this example. Now you can see that both true and false are already considered in the matching shown here. Okay, so let me see if it is possible for me to play with it. Of course, I can play with it. X is false, so I can match the value of x with the second branch shown here. Okay. So how about the situation when I just comment out one of the two branches? Let's try now. So suppose I comment out the true arm, and let me try to save the program. And you can see that I have a situation like this one. Missing match arm, true not covered. So you can see that I just have the false arm, but not the true arm. In this case, the possible values of x cannot be exhausted. That's why I will have the compile time error. Okay, non-exhaustive patterns, true not covered. That's why I have to put all the possible cases of x in the match pattern. Otherwise, I'm not able to compile. So we have to understand this situation by checking all the possible cases of your value. Okay. And the other one to talk about is the if-let and else-if-let arrangement. The conditional if-let and else-if-let expressions do the destructuring to match the pattern on an arm. If the matching fails, we just do nothing. If the matching is correct, I'm able to do the thing considered by my arms. That means we can do the matching and assignment on one line only. So let us see what will happen later on with an example. The pattern is on the left-hand side of the equal operator, and the variable is on the right-hand side. Notice that if that expression doesn't really check all the possible cases of our matching. So let me play with this example. Okay, now I have a variable called set, which is an option enum, and the value of it is sum4. So there is a value inside the sum variant. And let us go to the if-let expression shown here. If let sum j equals z, then I do something. the meaning of here is like this. I have to match the value of Z with this pattern. So I have to see whether the variable is actually having this particular pattern, which is a sum variant. And if it is a sum variant, I can just pick up the value inside the sum variant to be printed in this arm, okay? And you can see that I don't need to check for the none case here. Even though Z can possibly be none, I mean the none variant in the option enum, I don't need to use the other ways to just check that possibility. So in this situation, I just need to avoid the need to exhaustively check all the possible cases. Okay, so let me play with the program. Okay, I can get the number 4 because the sum variant would have a value of 4 inside. And this value of j is already shown here, okay. That means I don't need to check for all other possible cases of the matching. So even though Z can be none, I don't need to check it out. If we don't use the if let and else if let expressions, then the code will be a bit longer because we have to consider all the possible cases. So let me see this example. Okay, this one is like this. I have a value of Z. Z is an option enum, and then I want to match the option enum with these two branches, sum and a certain catch-all character. The catch-all character means that other possible variants that I haven't considered in the previous branches will all be considered in this final arm, okay? So if Z is a sum variant, I can just pick up the value contained in that variant, and this value can be printed out. Or if this first arm isn't met, I have to consider this situation as well, and I just return a unit type as the final answer. So let us see this example now. Of course, I can get number 4 because the value of Z is able to match the first pattern, okay? So how about if I say none here? Oh, sorry, I forgot to really specify the option enum here, because when I say none here, I have to use the correct data type for my option enum. Okay, you can see that I just return nothing, and the nothing is represented by the unit type shown here, okay. So we can see this situation quite clearly now, okay. Okay, let us see another situation. We can have another example that involves the use of else if let expression. So if I just use the else if let expression here, I can have more arms to consider. So let us play with this example. Okay, let us see this example. Now I have a none variant here for S. That's why I have to explicitly set up the data type for S, which is an option enum whose value is expected to be I32. And then I have a T variable here. T is just sum A. A here is a character. And of course, the character type can be inferred by the Rust analyzer, okay? So I'm able to check for the pattern of S first. So if S is equal to sum J j can be printed out. Else, if let sum k equals t, here sum k is going to pick up the letter contained, or the character contained in the variable t, which is wrapped in an option enum. Else, I do something else. So it is possible for me to check for more than one case by using the if let expression together with the else if let expression. Okay, so let us see the answer to this code snippet. Of course, I will have got letter A, which is just the second one. Okay, I'm able to do the else if let expression because it is clear that t is actually having a character inside the sum variant. Okay, but for the first possible arm, s is actually none. That's why I cannot get the sum variant from the s variable. Okay, and of course I'm not able to run this one because when the upper branch is already executed, I'm not able to go further. Okay, now let's see another example which uses the while let expression. The conditional while let expression here does the destructuring to match the pattern on an arm. So if the matching fails, the while let loop will stop. So let us see this example to see how we can stop the loop if we use the while let expression. Now let us see this example. So my optional value here is a sum variant with a value of 0 inside. That's why the Rust analyzer can help us infer the data type of the my optional variable. And this my optional variable is a mutable variable. Okay, so I'm able to change the value of it later on. And then I can use the while let expression to match the value of my optional variable with the pattern on the left hand side. So if my optional is of some variant, then I can do something indicated by the curly brackets here. Okay, so I just pick up the value of I. That means I'm able to do the assignment of variable I in the while let expression. Okay, so if I is smaller than 4, I can say that that number is smaller than 4, and then I update my optional variable to get another value, which is also a sum variant, but now the value of the sum variant is now I plus 1. That means I increase the value of the sum variant by 1. If that is not the case, I just say that the looping is finished, and then I set up my optional variable to be none, which is another variant of the option enum. So let us see the example. Okay, you can see that I have 4 sentences which indicate the value of I, and I have also get another sentence called looping finished. So initially I is 0, and then I can do this printing because 0 is smaller than 4. And here the assignment and the comparison are both done in just one line. Okay, that is the meaning of using the while let expression. After printing a certain sentence, I change the value of the sum variant to be 1. And then I can go back to the while let loop again to see the value of my optional variable, which is now 1. And then 1 is smaller than 4, I can print it out. And then I can increase the value of sum 1 to sum 2, and then I can continue the looping again until I have this situation. 4 is not smaller than 4. Then I would just say that looping finished, and my optional value becomes none. That's why the printing would just end with the sentence called looping finished. Okay. And when my optional variable is now none, you can see that the first line here fails. That's why my optional variable is no longer having the sum variant. Instead, I have a none variant. That's why when this sentence is printed out, looping finished, I'm no longer able to go into the while loop to do the further comparisons. Okay. And let us see an example of using the for loop to do the pattern matching. The value just after the for keyword is a pattern. So let us see this example. We have a for loop here. So this is the pattern for us to match. So the idea of this code snippet is like this. I want to match the content of my array one by one to see whether I can pick the content of the tuple contained in the array individually. Okay, so let me play with the code now. Now I want to just execute the program. Okay, you can see 1, 3, and 5, 4 coming out. So the first operation of this for loop is to pick up this tuple, which is 1 and 3 contained, and the first value is matched to x, and the second value is matched to y. That's why 1 and 3 can be printed out individually. And when I go to the second element of the array, I can pick up this tuple, which contains 5 and 4. And of course, 5 is matched with x, and 4 is matched with y. That's why I can print out 5 and 4 individually in the second line. Okay. Now let's talk about the let statement. The left-hand side of the assignment is the pattern that is going to match an expression on the right-hand side. So when we do the assignment of a variable, it is actually doing pattern matching. The idea is like this: let pattern equals expression. So I want to save the value in the expression into a variable which is now acting as the pattern. Okay. So let me play with this program now. Now I want to let m and n be t and v. That means I'm going to have an expression on the right hand side, and m and n are going to be matched with the expression on the right hand side. So t will be matched with m and v will be matched with n. And of course I'm able to print out the values of m and n respectively because of the pattern matching by using the let keyword. Okay. So let me play with it. Of course I can print out the two letters t and v respectively because the matching is done successfully. Okay. We can also do pattern matching with function parameters. So the function parameters are the patterns to match with the actual arguments passed to the function. So let's try to play with this example. I have a function here, and the function here is going to allow a tuple to be passed into it, and the actual argument value will be matched with the patterns on the function parameter. Okay, that's why you're able to print out I, j, and k in the answer. So let us see the example. Okay, you can see this program. I have a function to show the tuple content, and the tuple content is passed in terms of a reference. Okay, so I just use the reference to a tuple, so the function doesn't really take ownership of the tuple. Okay, so when I do the matching here, you can see that the character type here represents I, the character here represents J, and the character type here represents K. And A, B, C is able to be matched one by one. So A is matched with I, B is matched with J, C is matched with K, of course. So I'm able to print out I, J, and K as the answer. So let me play with it. The chars are I, J, and K. So this part is also doing the pattern matching. Okay. And then I'm going to discuss a little bit of the terms called refutable and irrefutable patterns. If a pattern can match for any possible value, then the pattern is irrefutable. What does it mean by this one? let us see this example. Let a equals 1. Okay, so a must be 1 and a must be I32. And we are pretty sure that a is able to be matched to a predetermined value of predetermined data type. Okay, that is called irrefutable, because we have no doubt about the data type and the possible value of a. Okay. On the other hand, if a pattern can fail to match for some possible value, then the pattern is refutable. What does it mean by that? Let us see this example. Let x equals sum 26. It means that the data type of x is an option enum of an I32 type. Okay, but when we have an option enum, it is possible that x can also be none. So even though the data type is already determined for the variable x, the value that is allowed for x can vary, or it is quite uncertain yet. That's why we can say that the pattern is now refutable. That's why I can understand the meaning of the word refutable and irrefutable. Okay. So why do we need to understand the meaning of the word irrefutable and refutable? Here is the reason. Function parameters and let statement and for loop only accept irrefutable patterns. That means for these three types of situations, we can only use the irrefutable pattern. That means the value of a cannot be an option enum. Okay. But for if let, while let statements, we can use the refutable patterns. Okay. That means for these two expressions, if let and while let, the value that is to be matched can be an option enum. Okay. And for the if and while statements, they are supposed to handle possible values. If irrefutable patterns are assigned to them, it would result in warning. So the program can still be run, but you will see some warning for if and while expressions. Okay. That's why it's better for us to use irrefutable patterns for if and while expressions. Okay. The compiler can remind us of the refutable and irrefutable patterns that we have used. So we don't need to remember all these things by rote learning. The compiler can help us check for the patterns that we have used. Okay. And let us talk about the pattern syntax. Pattern syntax has a number of possibilities. The first one is having multiple patterns in one arm. So what does it mean by that? If we have multiple patterns to match, we can use a pipe to separate the multiple patterns. So you can see that here I have a pipe. That means the variant can be direction west or direction north. So if either of them is matched, I can go to this branch. Otherwise, I will do something else. Okay. So let us play with this program. Okay, you can see that my direction here is enum variant, which is east in my case, okay, coming from the direction. And if the value of my direction is actually west or north, I mean the variant is west or north, I can do this sentence. Otherwise, I have to do something else. Okay. So let us see the answer. Of course, for east here, I'm not able to match the first arm. That's why I will go to the else part to do the rest. Okay, you can see that I got a direction other than west or north because I have the east direction as the value of my direction. So when I use the let statement, I'm able to see that I may not able to go to the first arm. That's why I will go to the second arm. Okay. Okay, how can we match a range of values? We can use the ... equals to indicate the inclusive range to match. That means we have the start and then we have an end, and the end will also be included in our comparison. That means the boundaries are also included. So when we use the dot equals range comparison, we have to make sure that only integers and characters can be used for the range operator indicated by the dot and equal sign, because their inclusive range can be evaluated unambiguously. Unambiguously is important, okay? The meaning of the word unambiguous is explained in the following example. Okay, let us see this example. Now I have a value of x which is equal to 4, and of course the data type can be inferred for us already, and we have to match the value of x with two possible arms, 1 to 3 here. 1 and 3 are the boundaries, and the boundaries are all included in the comparison. So you can see that for 1 to 3 and for integers, we can only have 1, 2, and 3 as the possible values for this arm to be considered. So if the value is 1, 2, or 3, we will say the value is small. Otherwise, I will say the value is large. Remember that this is a catch-all character, meaning the other possible values of an integer. Because x now an integer, this branch is able to consider all other possible values of an integer. So let us play with this program. Okay, you can see that when I have 4, I will go to the second branch to print out another statement called none, maybe. And you can see that for this branch, we are pretty sure that the values to match are 1, 2, and 3. That is called unambiguously. Okay. And the other situation that can help us do the matching unambiguously is the case of handling characters. So let us see the following example now. Okay, we have another example. Now I have a letter which is character 6, and when I use the single quotation marks, I'm able to infer the character type already, okay? So I have to match the character with any one of these 3 branches, which can exhaustively consider all the possible cases for the letters, okay? So if the letter is A to M, I mean small letter A to small letter M inclusively, I will say it is the first half of the characters to be matched. If the letter is between N and Z inclusively, I will say it is a second branch. If I have other letters to be found, I will go to the third arm to say that, oh, this is not a lowercase letter, okay? So of course I will go to the final branch because I'm not able to put 6 into any of the 2 previous arms because 6 is not a letter at all, okay? So for the inclusive range shown here, we can be sure that the first arm can consider A, B, C, D up to M. And for the second branch, I'm sure that I can consider N, O, P, Q up to Z. Okay, so this is the meaning of exhaustive comparison, as well as the unambiguous specification of the letters. Okay, that's why we can use the dot equals range operator to mention the integers and letters, because we are pretty sure about the values contained between the boundaries. Okay, so let us play with the program now. Of course, I will have not lowercase letters here because I will go to the final arm. Okay. Okay, now let's talk about destructuring. We can destructure a structure. Okay, what does it mean by that? That means I'm able to pick up the individual values in my struct. Let us see this example. We can destructure a struct instance by matching its fields. So I can pick up the fields and get the value of the fields. Okay. Now let us see this example. I have a struct here, and I have an instance of the struct, which is called my student, and my student is of course a student struct. I have two key value pairs, and then I can destructure a struct by using some name and some age variables. So I want to set up some name and some age to be the content of my struct instance. So I can match the name and age fields of my student struct instance. So how can we do so? Let us play with it. Let student is of course a struct type, and the name here is going to be some name obtained by my student instance. And for the age, I will pick up the age content of my student instance, and the age will be saved in the some age variable. Okay, that's why I can print out some age and some name on the next line, because I've already destructured the struct instance by using this approach, which is just a let keyword followed by the structure declaration, which has some name and some age being the values obtained after the destructuring process. Okay, so that was play with the program. Okay, you can see John here, 18 years old. That means some age and some name can both be destructured from my student instance. Okay. You may say that it is quite long to say name, some name, and age, some age. Is there a possible way to shorten the code? Yes. There is a shorthand form of matching the fields in the struct instance. We just need to include the field names as the variables to store the destructured field values. So let us see this example now. Let student name age equals my student. So name and age are just the field names of the structure, and when I use the field names of the structure, I can do the destructuring, and the field names can be used in the upcoming operations. Okay, so let us play with this code. Okay, I have a structure here. The structure is having two pieces of information, name and age. And of course, I have a struct instance, and the instance will be pretty much the same as before. And I can do the destructuring by using this instruction. Let student is of course the struct type, and name is of course the same name here, and age is of course the same age here. That means I can use the field names to do the destructuring in a more compact way. Okay, equals my student here means that I do the destructuring. So the string and the integer will be obtained by the name and age variables respectively, so that you can see name and age right here after the destructuring process. Okay. Of course, you can still see John 18 years old, because I have used the shorthand form of destructuring a struct instance. Okay. A struct instance can match with another struct instance with the literal values as part of the struct pattern. It is a bit abstract. Let us see this example. Now I have a structure again, which is of course the student again. And now I have a certain student called my student. I've already given the name and age to this my student struct instance. And then I can match this instance with a structure inside one of the arms. So if the struct instance is having this structure pattern, I'm able to do the following statement. Otherwise, I will give an unit type as the output of the match expression. So let us see the first arm in detail. Student name string which is an inferred data type, age 18 here. So it means that if my student is having the age of 18, I can say that I got an 18-year-old student. And the name doesn't matter here because I don't need to match with the name. If you want to match a particular student with a particular name, of course, you can just pick up the name inside the student condition here, okay? So for my case now, I just need to match with 18, which is the age. So a student of age 18 is enough for me to execute the first arm, okay? The name doesn't matter. So let me play with the program now. Of course, I can get this sentence because I'm able to get a struct instance with the same age as 18. Okay, I got an 18-year-old student. That is the meaning of the matching of a struct instance with a certain struct instance. Okay. By using the same principle, we can really destructure an enumeration. So let us see an example about destructuring an enum. Now, let us see this example now. We have an enum definition here. The enum type is called student, and this student has two possible variants, which is a primary student and a middle school student. Okay, and for both variants, there are two values to follow. The first value is of string type, and the second value is of the integer type i32. That means the first parameter is the name, and the second parameter is the age. Okay. Now I have a middle school student being the value of Peter. So I have a variant shown here, and the value of this variant is like this. I have a Peter string and 19 as the age. Okay. So I'm able to match this enum variant with the following two arms. Okay. Since I have two possible variants of my enum data type, I have to consider both possible variants exhaustively. Okay. If Peter is a primary school student, I can print out this sentence. Or if the student is a middle school student, regardless of the age and the name, I can print out the second line shown here. Okay. So for both arms, the name and the age don't matter, but I can just print out the name and the age as well. Okay. So let us see this example now, and I'm going to play with it. Of course, you can see Peter is 19 years old in middle school, because Peter is really a middle school student, and you can see that the name, which is in the form of a string, and the age in the integer format can both be obtained. Okay, so that I can see Peter and 19 here. Okay, that is the meaning of destructuring an enum instance. Okay, we can destructure a struct instance and the tuple together. We use the same principle as destructuring a struct instance and an enum instance. Okay, so let us see this example of doing tuples in addition to structs. Okay, let us see this example. The tuple consists of a tuple and a struct. So what does it mean by that? Let us see. Now, I have a tuple here. The tuple is quite long. And the first element of the tuple is really a tuple, hour, minute. And the second element of the tuple is really a struct. Okay. And I'm able to do the destructuring by putting the values coming from the first element of my tuple to the first element of the tuple in the pattern, okay, for hour and minute. And of course, I'm also able to pick up the second element of the tuple, which is a struct instance, to match with the second pattern, okay. So of course, I can pick up Terry as the string, which is put in info1, and 19 to be put in info2, okay. And of course, I can match the fields of my structure. So age would go to info2, and name will go to info1. There is no ambiguity in this destructuring assignment. And of course, I can just print out info1, info2, hour and minute respectively in the second part of the program, because the assignment here is done appropriately. I mean, the destructuring is done appropriately for both the tuple and the struct instance, okay? So let me play with the program. Terry of age 19 entered the record at 12:34, okay. That means I can pick up the hour, minute, together with the name, which is known as info1, and age, which is known as info2, okay. Of course, this assignment is achieved by using an equal sign here, okay. In some situations, we can ignore the values in the pattern. How can we do so? The first one is to use a wildcard pattern to ignore the whole value. The underscore in the pattern can act as a wildcard character, meaning that the underscore can mean anything. We already showed the use of the underscore character to represent anything. So I'm going to demonstrate it again later on. The technique here is quite useful when we are required to use the fixed number of parameters in a function, but we don't want to use all of them in our implementation. So let us see this example to illustrate this purpose. Now I have a function called showValue, and you can see that for the first parameter here, I use a wildcard character. It means that the function can ignore the first argument. And of course, the second argument has a name called age, and the type has to be i32. That means when I pass a certain string to the showValue function, the string here can be ignored. That means the first parameter can be ignored in the function operation. So you can see that the function is just using the second parameter, which is the age, and the first one can be ignored. So even though I pass the name into the first parameter, the function does nothing to handle the first parameter, okay? So let me play with the program. The age of the person is 30. That means I don't need to handle the string in the first part of the function argument, okay? We can also ignore parts of a value by using the wildcard character. Sometimes we don't need to mind the part of the exact values when we operate on them. And the following example would show that situation. We just need to care about whether a tuple has the sum variant and a non-variant. The value bound to the sum variant don't really matter. So let us see this example now. Now I have a tuple, okay. The tuple has two option enum variants. One is sum3 and the other one is none. So sum here has a number of 3. So the data type can be specified as i32, okay. And since I have a none variant here, I really need to explicitly show the data type for the second option, okay, which corresponds to the none variant, okay. And then I'm going to match this my tuple with these 3 arms. So we can see the first arm. I just need to have a sum variant and non-variant respectively for the first element and the second element of my tuple. And the value contained in the sum variance doesn't matter. That's why I can use a wildcard character to represent this value that I don't really care. And of course, I can do similar things on the second arm. If the first value is a non-variant, and at the same time the second value is a sum variant regardless of the value bound to it, I will do this operation. And if these two arms fail, I will do the rest. That's why I have a wildcard character here to represent the remaining possible cases of the sum variants and the non-variants for my tuple. Okay, so you can see that when I need to execute the third arm, I will have a situation like this one. Both entries are either sum or none. That means I will have sum or none. Okay, so let us see the result of this program. So you can see that the tuple has the second value being none. That's why I will have the second entry is none. That means I will just go to the first arm, okay? And I don't need to pick up the value of the sum variant because I used the wildcard character to indicate that I don't care about this value, okay? Let us see another example that doesn't care about some of the values in a tuple because we don't just use them. Now we have a tuple here. A tuple has 4 letters, A, B, C, and D, and I want to match my tuple with the branch shown here. I have only one branch, that is already enough. Why? Let us see the reason. I have char 1, and then a wildcard character, and then char 2, and then a wildcard character again. So we can see that we have already got 4 character placeholders. Char 1, wildcard character, char 2, and wildcard character again. So we are already able to see that B and D won't be used. I just pick up A and C in the program. And since I have already exhausted all the 4 possible places of my tuple, one arm is already enough to indicate all the possible cases, okay? So let us play with the program. First is A, third is C. That means I don't need to care about the second character and the final character, which is also the 4th character. Okay. We can also ignore unused variables by using the wildcard character. We might create a variable that will be used in future, but not now. We can name the variable with an underscore at the beginning of the name to avoid the compiler warning of the unused variables. So let us see a simple example. If I want to say the temperature is 25 degrees Celsius, I can say that temperature equals 25, but I use a wildcard character beforehand. That means the compiler would treat it as an unused variable. Okay. And the compiler won't give me warning about the unused variable, okay? But when we use the wildcard character to represent an unused variable, we have to notice something. The variable would still bind to the value, and the string is moved to the variable with the underscore, even though it is not used further. Therefore, the original variable cannot be accessed. And I'm going to illustrate this idea with the use of the following example. The following code does not compile because the value originally bound to my name is now bound to underscore saved underscore name. So let us see this example now. Now I have a variable called my name, okay, and you can see that I want to move my name to an unused variable called saved name, and of course I have to put an underscore before my saved name, okay. So you can see that I'm able to do the movement so that my name can no longer be printed, because you can see the compiler error here. Borrow of moved value, my name. So my name is already gone. I mean, the value originally that can be accessed by the my name variable is now gone to the unused variable called underscore saved underscore name. That's why my name here is no longer able to be used. The movement can still occur even though the variable is not used. Okay, this is the idea of this sentence. Okay. When we do pattern matching, we can ignore the remaining parts of a value. How can we do so? We can use two periods to represent the parts that can be missed out, as long as the parts to be missed out must be clear enough to be recognized by the compiler. So let us see this example now. We are able to ignore some of the values as long as the values to be ignored are clear enough. Now I have a tuple that has 5 integers, okay, and I want to match the whole tuple with this only arm here. You see I have a number of patterns to match: first, fourth, and fifth. And how about the second and the third? They are already able to be represented clearly by means of the two periods here, okay. I can ignore some unused values in my upcoming operations because I put the two periods between the first one and the second to last one. Okay, it is already good enough for the compiler to recognize that these two periods would represent the missing parts, which are the second and the third values of the tuple. Okay, that's why I can use first, fourth, and fifth variables to just obtain 67, 83, and 86 respectively. Okay, and by using the two periods here, we are already able to remove the second and the third because the meaning of the values to be ignored is already clear enough. So let me play with it. Okay, I can get day 1 as 67, day 4 as 83, and day 5 as 86. And we don't need to handle day 2 and day 3 because I don't ever give the name to match. Okay. We cannot use the two periods twice in an expression because it will result in ambiguous representation of the things that are missed out. So let us see this example now. I have the same 5 numbers here. If I put the pattern as follows: 2 periods, h3, 2 periods, and h5. It is not clear enough by the compiler to distinguish the particular values you want to pick up. The first 2 periods here can actually mean 67 only, or 67 and 78 actually, right? And of course, h5 here is already representing the last value, which is clear enough. But how about the second pairs of periods here? Is h3 representing the second or the third element? I'm not sure. If there's h3 here represents the second element, then the second pairs of dots would represent 62 and 83. But if the h3 is representing the third element, then the second pair of periods would just be able to represent 83. So you can see that the matching isn't clear enough by the compiler. That's why the compiler can not ever compile, okay? And in the same situation here. Does the 2 periods here represent 67 only, or 67 and 78 altogether? It is not clear enough, okay? So let me play with the program now. Okay, let us see the error here. The 2 periods can only be used once per tuple pattern. Yes, that is the major reason. And we can see that it is not clear enough for the compiler to distinguish the particular values you want to ignore if you have more than one pair of two periods at the same time, okay? Now we can go to another part called match guards. A match guard is really an if condition after the pattern on an arm. It can serve as further screening. This additional condition can use the variables introduced in the pattern, and the match guards can solve the shadowing problem with the match expressions. The outer variable is used again in an arm. However, the match expression becomes a new scope and shadows the outer variable, so the outer variable cannot be compared in the arms. So that is the situation when I don't use the match guards. So I will explain the meaning of a match guard with a further example later. Let us see the effect if I don't consider the use of match guards. Now I have a variable called b, which is having some m here. Of course, it is an option in enum, and the variant is sum, and I have a character here called c, which is a letter p here, okay? And I want to match b with the three possible arms. So if b is equal to sum y, I want to print out got the letter corresponding to the value here, which is y. And if I get sum c here, I want to print out I got the character corresponding to letter p here, okay? So c here is actually meaning the variable in the outer scope of the match expression, okay? So I would like to use the outer c in my matching arm, but it is not possible in Rust by just doing this simple referral. And the reason is like this. This new c already shadows the outer c. So this is a new c which already shadows the outer c. So this c is different from the outer c already. And in this situation, c would become m now because the new c matches with b. What does it mean by this one? The first arm says that I need to match with letter y, but now c is a pattern to be matched. So you can see that b is actually having a value of m in the sum variant. So c would become m. So I will get m instead of the p, which I intend to match, okay? And of course, I'm not able to go to the third arm because b is not none. But since b can be none, according to the option data type, I must include the final arm to indicate that I have considered the situation that the value of b can be none. Okay, so let us go to the program and let me play with it. Okay, you will see got m when c is passed. So when I use some c here, I'm not able to get the outer c because this outer c is already shadowed by the inner c in the match expression, okay? The shadowing has already done. And I will get m because I'm able to match with b whose value is sum with a value of m, okay? And of course, I'm also able to print out the original value of c is p. And you can see that the shadowing has occurred because the outer c is still p, and the inner c is already out of scope after going through this line, and when I go to the new line, the inner c is already gone. That's why I will just show the outer c content, okay? That is the meaning of shadowing, and that's the situation why we can use the match guard so that I can still use the outer c without shadowing. In order to let us use the outer variable in the match expression, we can introduce a match guard. And by using a match guard, we can link the outer variables to the scope to the match expression. So let us see this program now. Okay, we have this example now. I is equal to sum m. M is a character, and j is a character which is P. So P here is a irrefutable pattern, while I is a refutable pattern, okay? And I want to match I, which is an irrefutable pattern. If I is equal to some Y, I would go to the first arm, and of course, I is some M but not some Y. I'm not able to go to the first arm. And let us go to the second arm. Some K. Okay, this K is a variable to be obtained by the matching, and I have a match guard here. If K equals J, what is J? J is the outer variable outside the match expression. So here J is still character P. So the meaning of the second statement is like this. If K equals J is the match guard that can link to the outer variable. In this situation, J is not yet shadowed. I can use the outer J here in the arm to be matched. So J means character P. So this entire statement is like this one. If I can see that the outer variable J is matched, now K is equal to P. That means if some P is present, I will go to the second arm. So this J means the outer variable J, and I can use the outer variable without shadowing to be put in the arm. So K here means the letter P. So I have the first arm as letter Y, and the second arm becomes some P, okay? So I have P and Y for the first two arms. So if I have some P, which is indicated by the letter J, I'm going to print out the second line. If the value of I here is representing other values, like none or the sum variant with other letters, I will go to the third line. And of course, I'm also able to print out the original variable of J to indicate that I can still use the original variable outside the match expression. So let us play with the program. Okay, you can see that I have this sentence coming out. My I was some M, which is this one. Because I is having a value of some M, which cannot match with the first arm of some Y and the second arm of some P. Okay, I will just go to the third arm to indicate that I get another variant of some M. Okay, and of course J is not yet shadowed, but because I have already used the match guard to help me avoid the shadowing effect of J, you can see that the value of J is still P. Okay. But when we use the match guards, we can to understand something. The match guard doesn't check for all possible cases that can happen within the match guard. That means this one is able to match some possible cases, but not all possible cases, and the compiler doesn't warn us of ignoring other possible cases of this match guard checking. Okay. Now let's go to another pattern matching called multiple patterns. We can use a pipe to separate the values that are allowed on a match. Okay, so a pipe means logical OR in this case. So a pipe is just a vertical line, okay, that is found on the keyboard. So if this arm goes to 2, 3, or 4, I will do the statement following this arm, okay, so that is a major idea. So let me play with the code now. Now I have a number which is equal to 8, which is an integer, of course. I want to match this integer with the following arms. Okay, I have 4 arms right here. If the number is 1, I do something. If the number is 2 or 3 or 4, I do something else. So a pipe here means logical OR. I can do this kind of logical OR operation on the 3 integers. And then I can also do another pattern matching called period equals. So this operator provides matching with an inclusive range. And only the characters and integers can use the inclusive range, of course, because the middle values are certain, of course. That is the use of the range operator. So when the number is 5, 6, 7, or 8, I will do this statement. Of course, an integer can mean a lot of numbers, maybe 9, maybe minus 10, and so on. So for this integer type, I have to really consider all other possible values of an integer. That's why I have to have the check all character at the end to indicate that I can get something else. Okay, so let me play with the code now. I have number 8. That's why I will go to the third branch or third arm, so that I will have 8 being hit to the third arm. Okay, because I have an inclusive range by using the range operator shown here. Okay. The final thing to talk about is the add bindings, which is this one. We can use an add operator here. We can bind a value to a variable when we do the matching. Therefore, the saving and the matching are done in one pattern. Let's see an example right here. I can do the matching, and the matching can be done here, which is obtained by matching it with an inclusive range. And at the same time, I can save the value obtained by the matching to the variable called saved number. Okay, so let me play with it. Now let's just go to the terminal to play with it now. Okay, let me try again. Okay, I can got 9 as the answer. So the saved number here is able to help me save the matched number. Okay, since it is in this range, I'm able to get my number and save my number into the saved number variable, and I can use this variable to operate further in the current arm. Okay, so that is the meaning of the add binding here. I bind the obtained number into another variable. That's why I can do saving and matching in one line only. Okay, so we have already talked about so many things about matching, and we can utilize these techniques to help us do the matching more effectively. Now let's talk about error handling in Rust. There are 2 types of errors in Rust. The first one is called unrecoverable error. So if a program faces some problems and there is nothing to do, we can make the code panic by executing the panic macro. And in addition, we can call the panic macro explicitly. And when the panic macro is called, the error is unrecoverable. That means when we have started the panic macro, the error will just end the program, and we can have no other ways to handle the error any further. And if the panic macro is called, the program will show an error message. The program will unwind and also clear up the stack and quit. Okay, so this is the meaning of having the panic macro to be called. Everything will stop actually, it means that. Okay. When we do the unrecoverable errors, the error message can show the location of the code where the panic macro is triggered. So we can see this example now. So I just call the panic macro, and I want to say that the program panics when the panic macro is called. So what would happen? Let us try this program now. Okay, let us see this program. We call the panic macro. The panic macro is PANIC followed by the exclamation mark. Let me play with it now. Okay, you can see that I have something coming out. The thread called main really panicked at line number 2, column number 5. So I can locate the panic macro, and the error message coming from the panic macro comes out here. The program panics. And you can also see that I have a sentence like this one. We can run with Rust backtrace equals 1 to display the backtrace. So this is the meaning of this sentence here. We can type something like this one. Rust backtrace equals 1 cargo run to see the backtrace and spot the source of the unrecoverable error. So let us try this instruction now. Okay, you can see the detailed message of the error triggered by the panic macro. So let us see the message. We can find out here. The main.rs file really triggered the unrecoverable error. And we can pick up this line number, which is line number 2. So we can see that the backtrace is able to help me really locate the position that makes the panic macro work. And then let us try this example now to see more properties about the panic macro. The program here wants to demonstrate something like this one. After calling the panic macro, the remaining code is not executed even though we have some more code remaining after the panic macro. So let us play with it now. Okay, I want to see the effect of base equals 0 and exponent also equals 0, which is giving me an indeterminate form of the exponentiation. So I want to really specify the situation by doing the unrecoverable error by using the panic macro. So if I enter the base and exponent without any problems, I'm able to get the power of a base. So in principle, I can go to this line by showing the value of the power. But if both the base and the exponent are 0, I should do the panic macro here, and I won't be able to go to this line. So let me try to play with this program. Okay, you can see that the message is called indeterminate form, shown here, because I set both the base and the exponent to be 0. So 0 to the power of 0 is undefined, or we call it an indeterminate form in mathematics. That means I can do the panic macro here, and you don't see this line coming out. Okay, I don't print the answer because I don't really want this answer to happen. How about if the base and the exponent are not both 0? Let us try it now. Now you can see that the base is now 2 and the exponent is now 3. So in principle, I won't go to this if condition. So I'm not able to go to the panic macro. Instead, I will be able to print out 2 to the power of 3 to get 8. So let us see the result. Okay, you can see 8 coming out. So if the panic macro is called, I can't go to this line. On the other hand, if the panic macro is not called, I can go to this line. So I want to show you that after calling the panic macro, the remaining code is not able to be run. Okay? Now, let's talk about the other type of error called recoverable error. If we don't want the program to stop in case of error, like the previous cases before, we can make use of the recoverable error type called result enum type, and we can handle this error and let the user make some changes so the program can work again. That means when we see errors, we don't always just stop the program by showing a panic message. Okay, we can handle the error and make the program continue. So we can handle this kind of recoverable error. So the result enum type is in the prelude already. We can just use it directly. We don't need to bring it to the prelude explicitly. And there are two variants to use for the result enum type. One is called OK, followed by a generic data type, and ERR, followed by the error type. Okay. T and E are the generic data types for the return value and for the error respectively. So in general, we can treat OK and as the variants of the result enum. Okay. And the result enum is specified by T and E. Both are the generic data types for the return value and for the error. Okay. So I'm going to show you an example of checking a variable of the result type. So I'm going to use the remove file function in Rust, which will return a result type value. So this is a built-in function called remove file. So if this file exists, the Rust program is able to remove this file from the directories. On the other hand, if the file that you want to remove doesn't really exist, the error will come out, and we will go to this arm to show the panic message. So this is the major idea of using the remove file function. And this remove file function comes from the standard .file stream here. Okay, so we have to use the use keyword to bring this function to the scope. So let me try to play with it now. Okay, of course you can see that I don't have the file called hello.txt. Okay, I don't have this file. So you can expect that when I want to use the remove file function, I'm not able to go to the OK variant. Okay, so if the OK variant is found, I would get the file handle of this file. Okay, on the other hand, if the file doesn't really exist, I will go to the arm, and I'm able to get the error variable of error type, and I will go to show the panic message by calling the panic macro. Okay, so let us try to run this program. Okay, you can see something like this one. Problem removing the file, which is this sentence coming from the panic macro. And the error message is like this one. The file is not found, and the message is like this one. No such file or directory. Okay. Of course, I don't have this file. That is why I will have this kind of message coming out. So that is the demonstration of the result type for the possible errors coming from this remove file function. Okay. And you can see that the inferred data type of my file result is like this one. It is a result enum, and if the file is found, I will have a unit type, which means the file handle. On the other hand, if the file cannot be removed, I will have the error type, which is type for Rust. You can see this message coming from the Rust analyzer. Okay, so we can get the error type, and you can see that the error value here can have different reasons for the failure of the function that we used. Okay, so we can really match different types of errors to our different actions to handle these errors. The reason of the failure will be stored in the bound value inside the variant. In this example here, it will be the error value, okay, which is the value bound to the variant, okay? And we can use the kind method, which I will show you later, to return an enum of various reasons for us to match. So for the error kinds, there are 40 error kinds, and we can just read the documentation to see the possible types of errors. Okay, you can see there are so many types of errors that can be found for Rust. Of course, we can always check the documentation to understand each of these variants to handle your different types of errors accordingly. And you can just click on the button here to show all the possible error kinds as well. Okay. So let me play with this example. I'm also going to use the remove file function in Rust to see the problem that I can face by using the error.kind method. Okay, so this error value is the value bound to the variant, and I can get this error.kind method to really find the possible error kind based on the enumerations that can be contained in the error kind enum. Okay, so suppose I want to remove a file that is not existent again. So the greeting file result will give me OK or okay, and this greeting file variable is going to store the result coming from the match expression. I want to match the previous variable with the two possible types of variants, OK or If I'm able to remove the file called hello.txt, I just return the file handle. If not, I'm able to go to the variant to find out the specific error kind by using the kind method. So if the error kind is just not found, which is the very first one here, I'm able to do the panic macro in this way by showing the error information. On the other hand, if there is other possible types of error kind, I will go to the other error arm, and I'm able to show other problem with the file. This variant here is going to store the other types of error kind that is other than the not found variant. Okay, so the other error here will try to explain to me the reason other than the not found error. Okay, so let me play with it now. Okay, if we want to use the error kind variant, we have to bring it to the scope by using the standard IO error kind. Of course, when I want to use the remove file function, I really want to bring it to the scope by using standard.filestream. Okay, so let me play with it now. Okay, you can see problem deleting the file. So I will go to the variant, and from the variant I will go to match the error kind, and I can see that I can match the first arm, which tells me that the file is not found because the error.kind really returns the not found variant. Okay, so I will go to this branch, and I'm able to show the error, which is this sentence. Okay, not found, no such file or directory. So we can use the error.count method to really find out the specific source of your error. Okay, let us talk about another two very important keywords to use: unwrap and expect. Other than using the match keyword as before, right here, we can use the unwrap and expect methods as its shorthand form. So I don't need to do the OK and variants explicitly. I can use the unwrap or expect methods. So what is the meaning of the unwrap method? It will be like this one. If the result returns the OK variant, then the method just returns the value inside the OK variant as usual. That means when you use the unwrap keyword, I can handle this one automatically for the OK variant. On the other hand, if the result returns the variant, then the method will just run the default panic macro. So the default panic macro will be shown up. So let us see this example now. Okay, I want to remove a file that is not existent. And when I use the unwrap function, I will go to the variant. And the variant will just help me trigger the default panic macro. So let us see the result now. Okay, you can see that we got the error value, and the error message will be like this one. The error content is shown up here, and the whole thing is called the unwrap message. Okay, so this is the unwrap message that is shown up for the error variant that I found from the program. Okay, and the other one is called the expect method. If the result returns the OK variant, then the method will just return the value inside the OK variant that is quite natural. On the other hand, if the result returns the error variant, then the method would show our predefined panic error message. That means we can write our own error message when we use the expect method, rather than just using the default panic macro when we use the unwrap method. So let us see this example. Here I use the expect method to show the particular error message. Okay, hello.text can't be deleted. So let me play with it now. Okay, let us play with it very quickly. And you can see that the inferred data type for the remove file function is result type, which can be a generic data type of an unit type, or the error type, okay, for the error. Okay, you can see that user-defined error message has come out, which is the same as this one. And of course, the error message would also give me the reason for the failure of the remove file function, okay. The file is not found, okay. So you can see that the unwrap and expect methods would just differ in the result arising from the error variant. It is more helpful to use the expect method to show the user-defined error message for better error tracking. That means it is better to use the expect function to specify our own error message like this one, so that we can feel a bit easier to keep track of the error sources, okay? And for recoverable errors, we can really propagate the errors. So what does it mean by the error propagation in Rust? Let us see the meaning here. If a function fails to execute, we can just propagate the errors back to the calling function. So what is the calling function? The calling function is just the function that calls the failed function. So we have a function which calls the failed function, and that first function is called the calling function. Then the calling function can handle this error from us. So we just propagate the error back to the calling function, and the calling function handles the error for us. And the called function doesn't need to handle the error. So the propagation is achieved by returning the error value to the calling function. That is the major idea of the error propagation. So I will have an example here, which is this long one. And before I play with this long one, I want to show you some details about this example. So the main function is like this one. I want to get the grade, which can only be allowed for grade A, grade B, and grade C. If I'm not able to get either of these three grades, I would just say the wrong grade is entered. This function can only allow A, B, C as the grade to go further in your upcoming operations. If you entered A, B, or C, then I will say OK variant has come out. Otherwise, I will use the error variant, and I will also say the error message. Okay. So you can see that the check grade function has the result type of char, and this one, which is meaning the static lifetime of the string slice. Okay. So this one here, ampersand single quotation mark followed by static, means that the lifetime of the parameter is until the end of the program. And we will talk about lifetime in other chapters later on, but not now, because this concept is a bit difficult for us to understand now. It is also a property of Rust that is quite important in Rust. So I just want to say that the error will be in terms of string slice. That is already good enough to understand the program. And you can see that the error type is now a string slice, which is having the lifetime until the end of the program. And we just want to match the result with the OK or variant. So if I get OK, that means the grade is A, B, or C. I'll just go to this arm to do something here. On the other hand, if the grade is not A, B, or C, I will get the error value bound to the variant, and I will go to this arm to print out the error. Okay. And I also check for other grades which would be other than A, B, or C. So I chose F as the value to be passed to the function. And I will repeat the same checking for the obtained grade. Okay. Before I play with the program, let us go to these descriptions. If the obtained grade is OK, the calling function, which is the main function, will use the value in the OK variant. So, which is the calling function. The main function calls the check grade function. So, the main function is known as the calling function, while the check grade function is the called function. Okay. So, if the obtained grade is the calling function, which is the main function, will handle the error by using the value in the variant. So check grade program just returns an variant, and the calling function, which is the main function, will try to handle the error shown here, okay, by using this arm and this arm. Okay, so that is the meaning of propagating the error to the calling function, which is the main function in my case. Okay, so let me play with the program. Okay, so let me play with the program now, because I already explained the reasoning of this code snippet. So for the first case, I got B. B is allowed because it is one of the grades that can become OK. Okay, so I will get result B. So I will just get the value called B as the return value for the OK variant. Okay, and I will just pick up the value obtained to print it out here. So for grade F, which is not allowed, I will go to the variant and I will go to this arm. So I will print out the error value here. The error value would be this string slice called wrong grade specified in the check grade function. So this error will be handled by the calling function called main. Okay, even though it is coming from the called function, which is the check grade function in this case. Okay, and you will see that this kind of matching is a bit long. So there is a way to shorten the matching. We use the question mark operator. So this is a shorthand form of performing error propagation by using the question mark operator to do the matching. So what does it mean by the question mark? If the matching of the function return value gives us the OK variant, the value inside the OK variant will be returned and the program will continue. That is quite natural. When we get the OK variant, then we can go to the further parts. On the other hand, if the matching gives us the variant, the value will be returned to the calling function, and the calling function can handle the value for us. Okay. Since we need the function to perform pattern matching, the function can return a value of result type of option type. So the function that we use the question mark operator has to return either the result type or the option type, so that it is possible for Rust to handle both cases, either the OK one or the one, or the some one or none one for option enum. Okay, so we can use the question mark operator after a matching function call when the return value of it is result or enum type. So we will see this example later. There are some differences between using the match expression and using the question mark operator. the error values coming from the question mark operator would be handled by the from function defined in the from trait of the standard library. And this from method would convert the error value to the type of the error value defined in the function. Let us go to the documentation about the from trait. So we can see the from trait here, and in the from trait, there is a from function for the from trait, and the from function is going to convert a certain generic data type to the self type. Self type here means the type that calls the from function. So we will go to the example to see what's happening for the question mark operator. So this is the example for us to use. The following example can help us explain the from method. For example, when the check price function is called, which is this function, the from method would convert the error value, which is in a string slice format, to the string slice format of static lifetime, which is the error type for the function call. Okay. And the function call would return a result type, okay, which is allowed. As long as the return type for the function is result or enum, we can use the question mark operator to help us handle the error propagation issue. So let us see the content further. The check price function would return an error message if the value to be put into the function is less than $500. So I will have this string slice as the error message. And this error message, or the error value, would be propagated to the calling function, which is the discount function here. So you see that the discount function would call the check price function, and the check price function is now followed by a question mark. So the calling function of the check price function is now the discount function, and the discount function is able to handle the error. Okay. So if the check price function returns the error having a value of a string slice, the question mark operator is able to convert the string slice type to the string slice of static lifetime, as shown here, which is the return type of the error part of the check price function being called. Okay. And the main function is just doing the display of the price that can have the discount. Okay. So for $600, it is more than $500, so it is possible to get the discount. Okay, the discount would be just 90% of the original price. Okay, if the value is $400, it is not possible to get the discount because I will get the error message, and the error value would be propagated to the discount function, and the discount function would just return OK value, or the variant propagated from the check price function. Okay, so you can see that the discount function has just one OK value to return, because if the discount function has already received the variant from the called function, which is the check price function, the discount function will just return the variant, which is converted to the string slice of static lifetime. Okay, that's why we don't need to specify the variant, because the variant will be propagated from the check price function to the discount function, and the discount function can just return that particular variant, okay, which is in the called function. Okay, so let us play with the program. Now we can see that the check price is quite easy to understand, and the discount function calls the check price function, which uses the question mark operator to do the pattern matching for the result variant from the check price function return value. Okay, I get the price variable, and if the price is okay, I will return the okay variant, And if the price is not okay, which is less than $500, I will just return the variant coming from the called function. Okay, so that is the major idea of the main function here. The main function just calls the discount function, which can return OK here for the 90% of the original price, or the variant coming from the check price function. Okay, so let me play with the program. Okay, for the first situation, which is $600, when I call the discount function, I'm able to call the check price function first, and the check price function shows that it is okay because the amount is not less than $500. Then I will have this okay value coming out to the price value, which is just a value of F64 type coming from the result type. Okay, and I just convert the price to 90% of it to become the OK variant that will be returned by the discount function. Okay, so you see the net price here is having the data type of result type. Okay, and the error type is of a string size type. Okay, and then I can match the net price to OK or variants. If it is OK, I just show the net price as $540. On the other hand, if the discount isn't allowed to be handled, I will show the error, which is this sentence. This sentence comes from error here, and also the E here. The E here would be the error message coming from the check price function. Okay, so you can see that Rust is able to propagate the error from the called function to the calling function, and the calling function can return the result type to the main program to handle further. Okay, so we have already talked about so many things about the error handling. Remember, we have two types of errors, unrecoverable one and the recoverable one. So we have different ways to handle these two types of errors. Okay. Now, for this part, I'm going to discuss the vectors, strings, and hash maps. First, we talk about vectors. As opposed to arrays and tuples, vectors can allow us to change the size at runtime. Okay, runtime is important. For arrays and tuples, the size is already fixed at compile time. And in the vectors, all the entries must be of the same data type. Okay, this is quite important in Rust. And the elements of a vector are stored in the contiguous part of the memory. So they are joined together in the memory location. So we cannot separately put the elements of a vector in random locations of your memory. Okay, and a vector is stored on the heap of your memory part. Okay, and vectors are immutable by default. That means once the vector is produced, we are not allowed to change the content of it. And if we create an empty vector, type annotation is required because the compiler cannot infer the data type of the vector from the non-existent entries. That is quite sensible. It is just like the option enum. For option enum, if we have none, we have to really specify the type of the option value. Okay, we apply the same principle to vectors as well. And there are two ways to declare a vector. One of them needs type annotation, and we can use the new method to do the declaration. An empty vector will be created if we use the new method, like this one. We say let v followed by the data type, and then we can see the data type is vec followed by I32, and I32 is enclosed by a pair of angle brackets. Okay, and then we say equals vec : new. So the new method is going to give me an empty vector, and the content of the vector will all be I32 type, okay? The other way doesn't really need to declare the data type, because the data type can be inferred by the vec macro. So we have VEC followed by the exclamation mark, which is a macro. So how can we use a macro to set up a vector? We can have this example. Let V equals VEC exclamation mark, and then I can put the values of the same data type into a pair of square brackets, okay? Of course, we have to end the declaration with a semicolon. Same for the first method to create an empty vector, okay? And then we can also update the vector after it has been already set up. Of course, a vector is immutable by default. We have to make it mutable when we declare it, okay? And we can add values to the end of the vector by using the push method. And this operation lengthens the vector. That means the length of the vector will be increased when we use the push method to enter some new content into the original vector, which is a mutable one, okay? And we can print the vector content using this pattern or this pattern, which are called the formatter. Colon followed by the question mark, or colon hash followed by the question mark. So we can use these two formatters to print out the content of a vector. When we use these two formatters, we don't need to use the debug trait to print the content out. That means I can just use these two formatters without saying that I have to derive the debug trait. So let us see this example. I have an empty vector created by using the new method, and then I push two numbers into the vector, which is a mutable one, of course. I use the push method to do so. And since you can see that both numbers are integers by default, Rust will treat them as I32. And then I can just use this formatter, colon followed by a question mark, to print out the content of a mutable vector. So let me see this example now. Okay, let us play with the program. Okay, you can see 36 and 52, which are the values being pushed to the mutable vector, okay? And you can see that the data type of this vector can be inferred because both are integers, and for integers, the data type is set as I32 by default. That's why the Rust analyzer can give me this inferred data type, okay? Also, we can read the elements from a vector. The way is to use the index of an element to read an element. We can get the reference to an element in a certain vector. That means we don't need to really move the vector into a variable when we just do the indexing, because I can just take the reference to an element in a vector. So let us see this example. I have a vector now, and this vector is produced by using the vec macro, okay? And then I want to pick up the second element. In this situation, I can use the ampersand A1 to indicate the second position. So we remember that for Rust, the index would start with 0. That's why for the second element, I need to use 1 to specify it, okay? And you can see that the data type is ampersand I32. That means I want to take a reference to an I32 value. And then I can print this second variable out. So let me play with the program. Okay, you can see that the data type of the second variable here can also be inferred when I use the ampersand A1 here, because ampersand means the reference, and 1 here means the second element, which is in I32 by default. That's why I can use the Rust analyzer to infer the data type of the second variable for me. So let me play with the program. So you can see that I can get 2 here, because 2 is actually the second element of the vector called A, okay. In addition, we can use the get method for vectors to read the elements. So I'm going to show you an example by using the get method. And before I do so, I have to say something more about the get method. The get method would accept an index, and it would return an option value of %t. That means I would take the reference of a certain value as the content of my option enum variant, okay? So we can use the match expression to check the returned value, because when I use the match expression, I can check the option enum content. And the use of option %t means that the reference to a generic type can be some or none. That means the reference here can help me refer to a value of some or none, okay? That is quite natural because the possible variants of the option enum are some and none, okay? Let me play with the program now. Okay, you can see the program is here. I have a vector here, and I want to get the first element, okay? So I can use get 0. The get method would help me get the content, and I can just use the get method followed by index 0. So you can see the get method content here. The get method would help me return an option enum whose content is the address of the content of my array. So that you can see an ampersand symbol here to mean that I have option %i32 here, which is the data type of the first variable that is wrapped in the option enum, okay? And since I have an option enum quantity, this quantity can be some or none. That means I have to really check all these two possibilities. So if this variable called first helps me to get the sum variant, I can just use the value called first to do the printing. So I can print the value here on this particular arm, okay? And of course, the first variable here would have a data type of %i32. That means it is a reference to a certain integer, okay? And on the other hand, if the match gives me none, I would just do this arm to print a sentence saying that I don't get the first element, okay? So let me play with the program now. Of course, I can get the first one is 8 here, because when I use index 0, 0 means the first element. Okay, so I'm able to get this one out. So let me see if it is possible to infer the data type of the first variable. Okay, you can see that this data type can also be inferred. That means I don't need to really specify the data type because the data type can be inferred for me, okay? And we can notice something here. The get method can handle the error when the element is not found. If the value is none, that is the return value, Rust doesn't panic. However, the index method would just panic. That means when I use the get method to really get a non-existent value of the element from a vector, the get method can help me handle the error, but for the index method, which is the first one, it is possible to panic if I'm trying to access a certain location that is not allowed for me to access, okay? So you can use the get method or the index method like this one, okay? And then we can use the for loop to access the elements of a vector. The idea is to use a for loop to iterate over the elements directly. And we can use a variable to remember the reference to an element. What does it mean by that? We will show you an example to describe it. when we just want to read the element, the for loop really doesn't need to take ownership of the vector. That means we can use the ampersand operator to get the reference to the vector. So how can we get the reference of a vector? I can go to this example. I have a vector here, and then I want to access the elements one by one. I mean, I don't need to really own the elements, but I just want to print them out by taking the reference of them. And when I use the for I in ampersand x syntax, I'm able to get the reference to each of the elements, and then I can do the printing of each of the elements by using the print line macro. Okay, so let me see the result by running this code snippet. Okay, you can see that the vector type can be inferred, and the reference to the elements of a vector can also be inferred. So let me play with the program. Okay, you can see that the values in a vector can be printed one by one. Okay, by using the reference to the vector elements. Okay. Now we can also change the elements of a vector using a for loop. That means the elements in the vector can be changed when I do the iteration. To allow the changes of the element values, I have to make the vector mutable. That is quite natural and sensible. That's why when we go to this example later on, we see that the vector is mutable. And if we want to change the values of an element, we need to dereference a variable to obtain the value pointed by the reference. So I will show you the meaning of the dereferencing here later on when I do the example. So let's go to this example. We have a vector, and I want to pick up the elements one by one. And since I just want to access the elements, I don't really need to take ownership of the whole vector. That's why I can just take a reference to the vector, which is a mutable one. And here we can do the dereferencing. The reference operator here is just an asterisk. So this asterisk is helping me to dereference the variable called I, which originally points to each of the elements of a vector. So when I do asterisk I, I'm able to pick up the values one by one. Okay, and after I've picked up the values, I'm able to multiply each of them by 2, and the value of the vector can be updated one by one. And then of course I can just do the ordinary printing of the updated vector, and I can just take the immutable reference because I just do the printing. I don't need to change the content of the vector. So let me play with the program now. So let me play with the program. Okay, you can see that all the numbers in the vector are multiplied by 2. Okay, so you can see 90, 194, 72, and 82. All of which are the doubles of the values in the original vector. Okay, since here I just want to do the printing, I can take the immutable reference to the vector. Okay, and you can see that the data types for I and Y can both be inferred by the Rust analyzer. Okay, and actually we can store multiple types of values in a vector. As I said earlier, the vectors can place data of the same data type. In order to help me put different types into a vector, we can wrap the different types in an enum. So let us say this example. Here I have an enum called snack. So the snack has 2 types. One is the chocolate and the other one is the nuts. Okay. And for chocolate I have 2 values, which means the flavor and the number of pieces respectively. And for nuts I have a value following it. This number is meaning the number of grams of the nuts. So you have 2 variants of the snack enum. And I can put these 2 enum variants into a vector. So you can see that I can use snack nuts and snack chocolate to really put two different types into the same vector. And of course, if you want to get the value stored in each of the variants, you can use the match expression as before. Okay. So let me try to play with the program. Okay, you can see that the program can be executed even though there is no operation in the main function to really play with the vector. Okay, we can see that the values are not used because I don't do anything on the vector. That's why I will get these warnings. But you can see that at least the program is able to compile. Okay, that means this approach of storing the values of different types in the same vector is feasible by using an enum to wrap those numbers or values. Okay. It is not easy to show the content of the enum instance for now. We need to learn the display trait to do so. So this is an enum that is defined by me, and for user-defined enums, it is not easy to do the display of the contents, except I use the display trait myself, which is a trait for Rust. So we will talk about the display trait in detail later on. Now we are going to talk about strings after finishing the vector part. What is a string? A string here is a mutable, growable, owned, UTF-8 coded string type. String is provided by the standard library already, so we can use string type very easily or very conveniently. Note that the string here starts with a capital letter S, okay? So it is a type provided by the standard library, okay? And we have to notice that the string is stored on the heap allocated part of the memory, okay? And a string is encoded with UTF-8. The content can be any other characters from other languages. So since a string is encoded with UTF-8, the characters can vary. It is not always English. It can be other languages as well. And let us show the way to create a new string. An empty string can be created using the new method. Okay, so the string type has a new method to help us create a string. The idea is to use this syntax, let mut s equals string new. So this s is pointing to the heap allocated memory that stores the string, okay? And if I want to change the content of the heap allocated memory, I can use the mut keyword, okay? And to create a string with content, there are two ways. The first approach that I showed you here is to create a string with no content. But if we want to have some content in the string, there are two ways to do so. The first way is to convert a string literal to string by using the toString method. So here, let us go to the documentation to see how it can be done. Okay, we have the toString trait, which contains a toString method, and this method is going to help me convert a string literal, which is actually a reference to the part in the binary file, and I can just use this address to turn it to a string type, which is put in the heap allocated memory, okay? So let us go to the tutorial notes again. So this is the example that I'm going to show you. I have a string literal, and the string literal can be converted to the string type stored on heap by using the toString method. Okay, and then I can print the string by using the printline macro. So let me play with it now. Okay, you can see that this is a string slice. So I have the inferred type being $str. That means it is a string slice type. And then when I use the toString method, I'm able to get a string that is stored on the heap allocated memory. Okay, so you can see that the variable s is a string type, which is already inferred for me by the Rust analyzer. Okay, so let me play with it to see whether I'm able to print the content of the string, which is on the heap allocated memory. Okay. Yes, I'm able to print hello world, which is a string with capital letter S, which is put on the heap allocated memory. Okay. And the second way to add some content to a string is to use the string from function. So how can we do so? We can use string : from, and then I put a string slice so that the value of s here would become a string which is put in the heap allocated memory. So let me play with the program. Okay, you can see that s is inferred as string type. Okay, that is natural because the string from method is able to turn a string slice into a string. Okay, you can see that the from method is able to turn a string slice into a string. That's why I always emphasize the data type. Okay, so let me play with the program. Of course, I'm able to print out hello world, which is a string, okay, which is already put in the heap allocated memory. Okay. And is there any method to update a string? Yes, it is possible to do so. We can append a string. That means we can put something more at the end of a given string. We can use the push string method to join a string slice. So the idea is like this. I have a string first. The string is already put in the heap allocated memory. Of course, when I want to change the content of a string, I have to make it mutable by putting the mut keyword before the variable name. And then I can use the push string method to really put the string slice to the back of the original heap allocated string part. Okay, and then I can print a new content. So let me play with the program. So let me play with it. I should be able to see A, B, C, D, E, F, G, H, I, J. Yes, you can see all the letters have come out because I have used the push string method. Okay. So when we use the push string method, a string slice doesn't move to the string that caused the method, and the string slice is still valid after being used by the method. That means in this example, FGHIJ isn't really moved to the variable called S. And I can show you another example more clearly to see this movement issue. Okay, I have a string called B, and I have a string slice called D, and then I want to elongate the content of the heap allocated string by using the push string method, and then I'm able to print both B and D. So even though D is already used in the push string method, because this method doesn't really take ownership of the string which is put in the parentheses, I can still print out the content of D separately. Okay, so D is not really moved to the variable B. Okay, so let me play with the program. Okay, you can see that the string is elongated and the original string slice is still present. That means the string slice isn't moved to the variable B. Okay, and the second way to update the string is to append a character. We can use the push method to do so, and the string that calls the method doesn't take ownership of the character. Same as before, when I use the push method, the string on the heap doesn't take ownership of the character that I used in the push method. Okay, so let me see this example now. Okay, you can see that I have a variable called x, which is a mutable string on the heap, and I have a variable called my char, which is y, and I can push y into the string, which is put in the heap, and then the character can still be printed out separately because the x here doesn't take ownership of my char. So let me see the program. Okay, you can see that the y is pushed into the string on the heap allocated memory, but the y here can still be separately printed out because this y doesn't move to x. That's why y is still separate, okay? To update a string, we can also do concatenation with the plus sign. We can use the plus operator to join the strings. We just need the reference to a string to achieve a concatenation. Okay, so we will see this meaning later on. And after the movement, in this example, S1 is moved to S3, while S2 is still valid as we just used its reference. What does it mean by this sentence? Let's play with the program here. Okay, I have S1, which is hello, and S2, which is world, and I can have S3 here. S3 is like this. I want to update S1 by adding the content referenced by S2. That means I have ampersand S2 here, so that I can put world after hello, and S3 will become a new string, and we can understand something that I described on the tutorial notes. S1 is gone because it has already moved to S3, but S2 is still present after the operation because S2 has just taken the reference when the concatenation is done by using the plus operator, okay? And of course, I'm not able to print S1 because S1 is already gone and it is already moved to S3, but I'm still able to print S2, so let me see if it is the case or not. Okay, when I want to run the program, you can see that borrow of moved value S1 is present. That means S1 is already moved to S3 and it is already gone, and I'm not able to get the content of it after the movement. That means you can see that the value is borrowed here after move. So in this case, I'm not able to print out the content of S1. But S2 is not really affected because S2 is just taking the reference of itself to combine with S1 to make S3. So let me play with the program. Okay, you can see hello world here. Hello world is actually the content of S3, obtained by moving S1 and using the reference to S2, okay? And of course, S2 can be printed out separately, okay? Also, we can use the format macro to do concatenation. The advantage of using the macro is that ownership of each string remains unchanged. So here for using the plus operator, S1 has to be moved to the new variable called S3. On the other hand, if I use the format macro, even S1 can still exist after the concatenation. So let me play with this program now. Okay, you can see I have 3 strings already. All of them are allocated on the heap. And I can use the format macro here, format exclamation mark, to put the contents of the 3 strings to make another string called T4. And you can see that I have to use a pair of curly brackets to enclose the string variable names. And after that, you will be able to see that I'm able to print out T4, which is obtained by joining all the 3 strings together to form a new one. And after printing the T4, I'm still able to print out T1, T2, and T3 separately because the format macro doesn't really take ownership of those strings. Okay. So let me play with it now. Okay, you can see the concatenated one here, as well as the separate content of the strings. Okay. And now let's talk about the indexing in a string. The indexing in a string is quite tricky in Rust. We have to take care of it quite seriously. The idea is like this. Don't use index to obtain a character from the heap allocated string. Unlike other languages, we are not able to use the index of a character to get the character from a string. A character can occupy a varying number of bytes depending on the written language. Also, we don't know the return type of the indexing operation: byte, character, grapheme, cluster, or string slice. So it means that in view of Rust, the index method of a string isn't clear enough. As we said already, we can put characters of different languages into a string in Rust. And for different characters, the length required for each character can be different. So suppose we have 3 bytes for a character, like the Chinese character. If I just pick up one particular index, I'm not able to show the Chinese character fully. Okay. That's why it is not possible for me to use an index to locate the character in some languages. And when I use the index method, it is not clear enough about the operation. When I use the index method, am I going to take the byte or the character itself? Or am I going to just take the grapheme cluster? Or I just want to take the string slice? So the thing to obtain from the index method isn't clear enough in Rust. So to avoid all these problems, we have to use a range instead to clearly slice the characters of the language we want to output. So the indexing issue is specific to particular languages. So for characters which is in English type, UTF-8 coding needs 1 byte, so we need 1 byte to indicate a character in English. So let us see this example, which has an English sentence in the form of a string slice. And if I want to pick up a particular character, we have to use start and end before syntax. So here I take the reference to this string slice, and then I want to take index 1 and end before index 3. So it means that I would take index 1 and index 2. So it seems like I'm able to get EL as the answer. So let me see if it's the case or not. So let me see. Okay, you can see EL here, meaning the index 2 and index 3. Index 1 and index 2, which means the second and the third characters. Okay, so you can see that both R1 and R2 are string slices. So I can do the slicing by using the start and the index just before the end for English. Okay. How about other examples? If I use a Chinese character, I need 3 bytes to store a Chinese character in Rust, because for UTF-8 coding, a Chinese character needs 3 bytes. So here I have 2 Chinese characters. So if I want to pick up the second character, I need to use index 3, 4, and 5. Okay, so 0, 1, and 2 refer to the first character, and 3, 4, and 5 would refer to the second character. That's why I have to say 3 period 6 to indicate the starting index and the index just before the end. Okay. Okay, let's see this example. Okay, you can see the second character has come out, because index 3, 4, and 5 would refer to the second character, while index 1, 2, and 3, 0, 1, and 2 would refer to the first character. Okay. And is it possible to iterate over a string? Yes, we can do so in Rust. But for Rust, it wants to be specific of the type to come out. That means if I want to iterate over a string, you want to get the bytes or the characters out after the iteration, you have to specify the thing you want to get clearly. So we can take the characters of a string by using the chars method so that the characters can be picked correctly. So let me see this example. I have a string slice and I want to use the chars method to pick up each of the characters. When I do the iteration using the for loop, okay. Okay, you can see that X is in char type, okay. That is already inferred for me, because the chars method is going to take out the characters one by one, okay. And then let me play with the program. So you can see A, B, C, D, E, okay. Because I used the print line macro, it is possible for me to change the line after printing each of the characters out, okay. On the other hand, if I want to show the bytes, I can use the bytes method. So let me see this example. I have a string slice and I want to print out the corresponding bytes for each of the characters. So let me see this example now. Okay, you can see U8 has come out because it is able to give me an integer of 8 bits, okay. So I'm able to get the bytes corresponding to each of the characters. Okay, you can see 112, 113, and 114, 115, and 116 here. So all these are the bytes corresponding to each of the characters using the UTF-8 coding, okay. And now we are going to talk about hash maps. A hash map is able to help us store the key value pairs, and we need to call it by using the use keyword, because the hash map feature isn't available in the prelude. That means I want to use standard collections and hash map to get the hash map before I can use it, okay. So how can I make a hash map? I can use the new function to create an empty hash map. And then we use the insert method to put a key value pair into the hash map. The idea is like this. I have to make a hash map by using the hash map new method. And since I want to insert something into this hash map, I need to make it mutable by using the mute keyword. And then I can use the insert method to insert a key followed by a value. Okay, so this key would have this value. So my idea is to say that Peter is of age 14 and John is of age 17. That's why I can insert these two key value pairs one by one, okay? And let's see how we can access the elements in the hash map. The first way is to loop over the hash map. And when we want to loop over the hash map, we can use the key value pattern to do the matching. And the for loop doesn't need to take ownership of the hash map. Therefore, we just need the reference to the hash map. And let us see this example now. Okay, I have to say standard, collections, and hash map before I really use the hash map. And then I make a new hash map, which is an empty one, and I insert two key value pairs. K is meaning key, and V is meaning value, okay? So when I use the insert method, you can see that I have to care about the key and the value, okay? And then I can obtain the content of the hash map by using the for loop. So I want to take the reference to the hash map, and then I can match the content of the hash map with a tuple whose values are key and value respectively, and then I can print the content of the key and the value one by one. So let me play with the program now. So the first content is Peter is 14 years old, and the second content says that John is 17 years old. So that means I'm able to use the print line macro to help me get the key and value of each of the content in the hash map, okay? And of course, I just need to use the reference to a hash map to do the printing. And the for loop doesn't need to take ownership of the whole hash map, okay? The second way to loop over the hash map is to use the get method. So the get method would receive a key and returns option &v type, where v is the value, and the reference to a value is wrapped by the option enum. So you can see that I have a reference to a value, and this reference to a value is wrapped in an option enum. And when I want to really get the content of a hash map, I have to do something more, and I'm going to use an example to show all the upcoming steps as well. So let us understand the methods to use first. We have to use the copied method, which can return a value of option t. So you see that I'm able to use the copied method to remove the ampersand. That means I'm able to get the concrete type, not the reference to a concrete type, okay? So the copied method would try to get the value of the variable initially obtained by the get method. And now the value obtained is wrapped by the option enum, okay? We still have the option enum to wrap the content, which is now just the content but not the reference to a content, okay? And after that we can use the unwrap all method. Usually we put a 0 in this method, so by doing so we can take either the value out of the option enum, or I can set to the default value of 0 if the copied method returns none. So this one is able to handle the two situations, whether the value can be taken out of the option enum or the option enum just gives me none, okay? So I can use this example to illustrate these methods mentioned, okay? Now let us read this example in more detail. I have a hash map, which is a new one, and then I can insert two key value pairs as usual. And then you can see something here. I have a name called Peter, which is a string on the heap allocated memory. And if I want to get the age corresponding to Peter, how can I do so? I can have something like this. Student, which is the hash map, followed by the get method, and the get method needs to use the reference to the name, and then I use the copied method, and then I use the unwrap all method, and the default value is set as 0 if the value cannot be obtained by the hash map, which contains my desired key value pair, okay? So I have to use the get method, and you can see that the get method needs the reference to a key, okay? K here means the key, and my key here is actually the name, okay? And the copy method is able to help me get the option t type, and for the get method I'm able to get the option &v type, okay? The value. V here means the value, and t here means the generic data type, okay? And the unwrap all is able to get the value of t back, okay? If I want to use the default value in case of the none variant, I can use 0 as the answer, so the age would become 0, okay? So let me play with the program. Okay, you can see 14 coming out. That means I'm able to use Peter to find the corresponding age of Peter by using these operations, okay? So we can just remember the sequence of using the get method for hash maps. That means I'm able to remember the get method, followed by the copied method, followed by the unwrap all method, okay? So from the key, I'm able to get the corresponding value, okay? And we have to notice something. The hash map can own the strings. The reason is like this. Strings don't implement the copy trait. Therefore, a hash map takes ownership of the strings passed to it and does not clone the strings. So here, I have an example to illustrate this situation. So I have some strings here, and the strings will be inserted into the hash map. And after the insertion of the strings into the hash map, the strings would become non-existent because those variables are already moved. So the content of the strings is already moved to the hash map. That's why these two variables no longer own the two strings. That's why I'm unable to print the field name and field value out. So let me play with the program now. Okay, you can see that I have two strings, and the two strings will be moved to the hash map because hash map is located on the heap rather than on the stack. And for heap allocated memory, we would use the ownership mechanism. So you can see that if I want to print out the strings after the insertion, I'm unable to do so. You can see the reason. Borrow of moved value, and the value borrowed here after move. That means the value is already moved to the map, which is a hash map, of course. So I'm not able to print the string content out. Same for the second string here. So I can compile the program, but I'm not able to really show the variables after the movement, okay? On the other hand, stack allocated values are still valid after being assigned to a hash map. It is valid because the stack allocated values can implement the copy trait, and the variable doesn't need to be owned by the hash map. That's why for stack allocated memories like numbers or integers, the insertion doesn't take ownership of the variables. Let me play with this example now. Here I have a string and a certain integer, and when I create a hash map by inserting the string and the integer, you can see that the string is moved to the hash map, but the number is not moved to the hash map. I can still print the content of the max here after the insertion, because when I do the insertion of a certain piece of memory on the stack allocated memory, I can use the copy trait, which is already done for me automatically. That means the value can be copied to the hash map without any movement involved. So it is possible for me to print the max variable after the insertion. So let me see the result now. Okay, after the insertion, I'm still able to print the value contained in the max variable, because there is a copying action to the hash map rather than a movement involved. Okay. So as I discussed the copy trait, it is a bit difficult for us to reason it now. That's why we will discuss the copy trait in future. And now we are going to talk about the way to update a hash map. Update here means that I have already got a key value pair, and I'm now going to change the value corresponding to a certain key. So the value can be overwritten by the newer one given the key. So we have a key, and then we can change the value of that key. It is achieved by reassigning the value of an existing key. So it is just doing the reassignment. So let us see this example now. Okay, you can see that I have 3 insertions. The first one involves the string called taxi and the color of this taxi being red in string. And I have another key value pair about bus and yellow. So I have a yellow bus and a red taxi. And for this third insertion, I have a taxi again, but now the value is green. So in this situation, I'm able to overwrite the original string whose content is red. So the value of the taxi here is now green rather than red. So I'm just doing the reassignment. So I'm able to print the key value pairs of the hash map. So you can see 2 key value pairs coming out rather than 3. Okay, you can see the bus is yellow and the taxi is green rather than red at the beginning because of the reassignment of the value corresponding to a certain key. Okay. In addition, we can add a key value pair if the key is not present. And if the key value pair is already present, then we just do nothing. That means if I just repeat the same key value pair, it means that I do nothing. And if there is no such key value pair before, and if you add a key value pair, it is just doing ordinary insertion, okay? And here I have a method to discuss, which is called the entry method. It can check for the key and return an enum of type entry, which is in uppercase at the beginning, okay? And the value of the entry type does not exist. And I will show an example about this entry method after explaining another method that I will use as well. The or insert method here would put the value in parentheses to link to the key if the value doesn't exist. And if the value exists for the key, then we do nothing. That means if we have already got a key, but no value, I can put a value corresponding to that key by using the or insert method. And if the value exists already, the or insert method would just return the mutable reference to the original value. And if the value does not exist, the or insert method will just return the mutable reference of the new value added, okay? So let us see this example now. Okay, I have now got an insertion here, okay, and entry here is going to do something for me. By using the entry method, I'm able to get the given key's corresponding entry in the map. So when I have David here as the key, I'm able to check for the corresponding key and see if this key exists or not. Of course, I have a key called David already, and when I see this key, let us see if the value of the key corresponding to David is equal to 16. So we can use the or insert method. If the value doesn't exist, I just put 16. If the value already exists, I just do nothing, okay? Ensures the value is in the entry, okay? And how about the third row here? When I use the entry method for this particular key called Peter, we can see that it is not present in the hash map. So when it is not present in the hash map, I would just try to insert this new key to the hash map. And since this key isn't present in the hash map, I also need to give a value corresponding to this new key. So if it is the case, I can insert 17 as the answer to the value, okay? So let us play with the program to see what will happen. Okay, you can see Peter 17, David 16. So David is already present and the value is already present as well. So the or insert method here just does nothing. Okay, but for Peter isn't present in the original hash map. That's why when the Peter here isn't present, I have to insert this new key together with the new value by using the or insert method. Okay. So this is the meaning of the entry method and the or insert method. And we can go to another part called updating a value based on its old value. So when we want to update a value, we need to dereference a variable and change the value. So the idea is like this. Let us see this example now. So this example is a bit long. So I have already inserted 3 key value pairs to the hash map. Okay. And I want to do something on the values corresponding to the hash map. So I have some students here, and their GPA are stored in the values, okay? And I want to do the capping of the GPA. So if the GPA of a certain student is already larger than 4, I'll just make it 4 as the highest possible GPA. How can I do so? I can take a mutable reference to do the editing. Since I want to just take the GPA, I don't care about the name, and I can use a wildcard character to represent the name that I'm not going to use. And for GPA here, it has to be mutated after the operation that I'm going to do. That's why the results hash map has to be a mutable one, okay? And then I can just take the mutable reference to the hash map to do the change of the values of the GPA, which are these 3 numbers, okay? And if I want to get the content of the value, I have to do the dereferencing by taking an asterisk before the variable name called GPA. So if the value of GPA is larger than 4, I just change it to 4.0. And of course, I have to use the asterisk before the GPA variable name so that I can do the dereferencing, and then I can get the value one by one. Okay. Since I used the mutable reference to a hash map, the result here would also be a mutable reference to the values and to the keys respectively. But for keys here, I don't really need to care about the keys. That's why I use a wildcard character. Okay. So you will expect that the GPA of Anna will become 4 rather than 4.21 anymore after the capping evaluation. So let me play with the program now. Now you'll see that David is still 3.64, Peter is still 3.39, but Anna has become 4.0 instead of 4.31. That means I can take a mutable reference and then I can do the dereferencing to really change the content of a value corresponding to a certain key. Okay. So this part has already talked about 3 things: the vectors, the strings on the heap allocated memory, together with the hash map, which is also stored on the heap. Okay. And we are able to create them, change the content of them after creation, and we can also print the content of each of them. Now let's talk about the packages, crates, and modules in Rust. So I'm going to talk about a number of definitions, and then I will show you some examples of handling packages, crates, and modules in Rust. So we are going to talk about the meaning of a crate in Rust first. It is actually the smallest amount of Rust code that a compiler can consider at a time. And a source code file is already treated as a crate. So when we have a source code file like the main.rs file, that source code file is already a crate in Rust. And a crate can contain multiple modules, and these modules can be placed in different files as well. So I will show you some examples of modules and the handling of the modules in different files later on. And a crate has 2 forms actually. There are 2 types of crates: binary crate and library crate. And I will also show you these 2 different types of crates for you later on. And a binary crate is actually the program that can be compiled to become an executable file. And the binary crate has the main function inside to control the outcome of the result of an executable file. That means we can execute the binary crate so that that particular source code file is able to be compiled to make an executable file for us to run. And this binary crate has the main function inside to control the thing that we can do for the program. And we have another term called a library crate. A library crate doesn't have the main function, so it cannot be compiled. And a library crate can store the functionality that can be shared with other projects. So I will show you an example of the library crate as well. So we have to notice something here. A crate would usually mean the library crate. So when we talk about the crate, it usually means the library crate, but not the binary crate. And a package is something like this. A package is a collection of crates, and it can have multiple binary crates and at most one library crate. Okay, so we can have many binary crates, but we have only one library crate. And a package has at least one crate. It can be the binary crate or the library crate. And a package has the cargo.toml file, and this file contains the information of the building up of the crates. And how about the word called crate root? A crate root is really the source file that the Rust compiler starts from. And a crate root is also the root module of the crate. The crate root of a binary crate is stored in the main.rs file, which is stored in the src folder, which means the source code folder. And the binary crate has the same name as the package. So I will show you some examples to illustrate this idea. If the package has the lib.rs file in the source code folder, then this file is the library crate root, and the package has a library crate that has the same name as the package. So I will also show you some examples about this statement. The example is here. For example, we create a package by using this sentence, cargo new my project, which is something we usually do to create a new project. In this situation, the name called my project, which is this part, is already the name of the package that we have created. That means this is the package name, my project is the package name, and if this package has the main.rs file contained in the source code folder, then the package has a binary crate called my project. That's why we will say that the binary crate has the same name as the package. Because the package is my project, the binary crate would also have the same name called my project. And this file is actually called the binary crate root as well. If the package has the lib.rs inside source code folder, then the package has a library crate called my project, which is just meaning this sentence. The package has the library crate that has the same name as the package, okay? And this file is also called the library crate root, okay? And then we talk about modules. A module is actually a collection of items like functions, structs, enums, trait, and so on, and even other modules. So a module is a collection of so many things. When these constructs are grouped in modules, they are easier to be reused. Also, constructs with relations can be grouped together to maintain readability. A module and its items are private by default. That means they are private, except that we declare them as public, so that the outside world cannot access the details of a private module. If the module needs to be used by the outside world, we have to make it public. Okay, we will show some examples to indicate the way to make a module public. To make a certain item public, we can use pub, which is a keyword to indicate that an item becomes public, and we put pub before the item name. Okay, we use the mod followed by the item name to declare a module, and the module can contain other modules inside. And after grouping the modules and their items, we have a module tree, and we will show some module trees later on. So this is a simple example. In the main.rs file, I have these things to be executed later. We have a module, which is called outer module, and inside the outer module, I have a public module called public inner. And inside this module called public inner, I have a function, which is a public one called public function. And the function is just doing a print line statement, okay? And in the main function, I just need to declare the path to locate the public function so that the public function can be executed for me. The idea is to use the module names. First, I need to say the outer module, and in the outer module, I need to use the public inner module, and I can also use the public function inside the public inner module. So I have such a way to really find out the function that I want to use. So we can see that the program would go into the function layer by layer, from the outer module to the inner public module and to the final function called public function. And the modules are listed in this example. And inside the crate, we can use a relative path to access the function. So it is actually a relative path to locate the function. We add 2 colons to separate the item names. So the item names, which are the outer module, public inner module, and the public function, are separated by the 2 colons. And this is actually a relative path that we will discuss in more detail later. So let me try to play with this program first. So let me try to run this program first. Okay, you can see something like this one. You can see that I can really print the statement inside the print line macro. Okay. I can play again here. Now the whole sentence is now joined in one line only. Okay. So the idea is to obtain the outer module and then the public inner module, and inside this public inner module I can go to the public function. So all these things are achieved by this relative path. Okay, that is the major idea. And we can also see something here. The outer module is the same file as the main function. I mean, this outer module is put in the same file as the main function, so they are put in the main.rs file. Okay. So in this situation, we can say that the main function is a sibling of the outer module. And in this situation, the outer module is visible to the main function. Therefore, we have no need to declare the outer module as public. Okay. We can see that we don't need to use pub before the mod keyword when I say the outer module, just because the main function is able to see this module already. I don't really need to make it public. And when I put the module and the main function together in the same file called main.rs, they are siblings of each other. That's why I don't need to use the public keyword called pub before the module keyword called mod. And let us talk about the module tree for this example. The module tree is the tree like this one. It can show the modules layer by layer, and we can use the parent, child, and sibling to describe the relationship between the modules and items. So this is the crate, which is the highest level of the module, okay? And below this module, we have the public inner module. And in the public inner module, we have a public function that is called here, okay? That's why we can say that the public function is actually the child of the public inner module, and the public inner module is actually the child of the crate module, okay? And of course, you can say it in another direction. The crate module is the parent module of the public inner module, and the public function is actually having a parent called public inner module, okay? And let's talk about private items. If an item is private, we cannot access it. So I'm going to show you a similar example that involves an attempt to play with a private item. Okay, for this example, you can see that I want to play with the private function. But the private function here isn't a public one. That's why you can see the error coming out. This is a private function, and I have to really make it public before I can really execute the program. So that is the reason why we will see an error coming here, even though I can really pick up the private function by using the parent module before the private function name, okay? So we can see this example here. An item in the parent module cannot use the private items in the child modules, but items in the child modules, be it private or public, can use the items in the parent module. To allow a parent to use an item in the child module, that item has to be set as public. So we can understand this relationship quite easily. The parent module cannot use the private items, but the child modules can use the parent. That is the major idea. So this is something we have to remember. And let's talk about another section which involves the paths that relate to an item. In order to locate an item, we can use a relative path or an absolute path. Okay, so we already showed the path like this one, which is a relative path. And I'm going to show you some further examples of the relative paths and the absolute paths. What is a relative path? The Rust book has this definition. A relative path starts from the current module and use self, super, or an identifier of the current module. And we already know the meaning of a relative path already, which is the example shown here. We go from the top layer and then into the inner layer and then into the final layer that we want to achieve. And we have this example that shows the relative path for us. In the main.rs file, I can have this relationship. And when I call the outer module, I can also call the public inner module, which is a public one. And I can go to the public function, which is actually a function which is already declared as public. So that is the original example that we met already. So how about the absolute path? We can refer to the Rust book again. It says an absolute path is the full path starting from the crate root. And for the code from an external crate, it begins with the crate name. And for the code from the current crate, it starts with the word crate. So let us see an example of an absolute path. In the main.rs file, we can have the following code here. When we use the relative path, we can just say outer module as the beginning of the path. But when we want to use the absolute path, we have to use crate root as the beginning. So every path would start from the crate root, as it says here. Okay. So in this example, we just use the crate root to start our path. That is the meaning of using the absolute path. So let me try to play with it. Okay, we can see that the absolute path is actually able to help me locate the public function, which is a public one already declared here. So let me try to play with the program. Okay, you can see that the sentence can come out. That means the printline macro can be executed. So I'm able to locate the public function by using the absolute path that starts with the crate root. Okay. And now we are going to talk about the super keyword. If a path wants to use an item in a parent module, we can use the super keyword followed by the item name to refer it from a child module item. So let's see this example. This is a bit long. In the main.rs file, we have the following code. The main function here wants to do something like this one. I want to get the parent module And in the parent module, I want to get the child module, which is actually a module inside the public module, the module called parent module. And in the child module, I want to call the child function. And the child function is something like this. I say something here by using the print line macro. And after saying something using a print line macro, I want to call the parent function that is inside the parent module. So in this situation, the child module has to use the keyword super followed by 2 colons to access the parent function. So we can use the keyword super to access the parent function. That is the meaning of using the super keyword by a child module to call the function from the parent module. So let me try to play with the code first. Okay, now you can see that I'm able to get no errors from the code. And you can see that the relative path is like this one. Parent module, and then to the child module, and then to the child function that wants to use a function from the parent module. Okay, so let me try to play with the program. Okay, you can see something like this one. When I call the child function, I can first execute the printline macro inside the child function. Okay, and after that, I can call the parent function by using the super keyword. That's why I can see another printline macro coming out that refers to the parent function. Okay. And then we talk about a section called public struct. We can make a structure public and some of its fields public too. That means we can make some fields only to become public and other fields can remain private. If some of the fields are private, we have to make a public associated function to make an instance. That means we cannot just use a public struct alone to make a certain instance. We have to use an associated function that we create ourselves to make a certain instance because some of the fields are private. We can test the program which is stored as library.rs or lib.rs in src folder, which is the source code folder. So for this example, I'm going to use the library file called lib.rs, which is also stored in the src folder. So now let me try to play with the thing first, and I can say that the binary create word is just the file name called packages create modules. Okay, so this is the binary create root, and inside this create root I want to build up something. In this situation, I really need to create a certain file called lib.rs inside the src folder. And now let me try to copy the code to the lib.rs file first. Okay, they are already copied. And let me see if I'm able to save it. Yes, I cannot find any errors. And in the main.rs file, I need to do something like this one. I want to go to the binary create, which is called packages create modules. And when I go to the binary create, I want to go to the use account function, which is this one. Okay. And this one requires the use of bank account, which is an account type. Okay. So for the account here, we have a bank account, which is a struct inside the module called account. Okay. So I go to the module and then I go to the struct, and then I use the new method that I create to really set up a certain bank account instance. And then I can show the information of this bank account on this line. And I can also do some action on this my account instance. Okay, so we can see the code as follows. I have a structure, and this account number field is public, but another one called private pin isn't public. And I want to implement some methods for my bank account struct. That's why I can have a new function to help me create a certain bank account instance. Okay, this is the way we create a certain instance because some of the fields are private. Okay, and then I have a method called deposit, and then I can also have a method called private process transactions. Okay, which is a private function because I don't see the word pub before the keyword fn. Okay, so when I call the deposit function, which is a public one, I will call the private function as well. Okay, so I can set up my account by providing the account number and the PIN, and then I can show the account number together with doing the depositing action. Okay, so let me try to play with the program from the main.rs file. I save it, and then I can really run the whole program. Okay, you can see that the account number can be shown up here. Okay, the account number is just the account number from the instance. Okay, and then I can also show the PIN by saying something beforehand. And if we want to do the showing up of the PIN, we have to call the deposit method. And in the deposit method, I can show something here, depositing something, which is $100. Okay, and then I can show some private function content. I say processing transaction with the PIN, which is the value for the particular instance. Okay, so you can see that I can use the use keyword to go to the public function, and the public function is able to use the module which has a struct inside and the implementation block for that struct as well. Okay, and we will talk about the keyword called use in more detail later on. We have another situation that can use the public enum. That is quite similar to the way we use the public structs. When we declare an enum public, all the variants are public. So unlike a struct, when we say a struct is public, we can make some of the fields private. But for an enum that is public, all the variants are public. That is something we have to remember. And let us go to this example. I use the same binary crate root. That means I use the same file name. Okay, called packages create modules, and inside it I have some code for the lib.rs file, and after that I can try to call the function that is inside the library.rs file. You can see that I can have no errors coming from the library.rs file. And let me continue with the main.rs file. Okay, you can see that I have no errors for the main.rs function as well. So let us check the library.rs file. I want to make a module, and the module contains a public enum, and the enum has 3 variants called red, yellow, and green. Okay, and we can take a look at the function that is called in the main file. The function is like this. I want to call the enum variant. Traffic facility is from the module, so I call the module first, and then I go to the enum, and then I go to the variant. So I can say that the upper light will be red, the middle light will be yellow, and the lower light will be green. So I just use these variables to really store the variants, okay? And let us check the main function. Okay, so when I want to use the library.rs file, I need to locate the module together with the enum. I need to locate the function which is called makeTrafficLight, and you can see that I can use the keyword called use, and then I go to the binary crate called packages create modules, and then I can go to the function directly, which is this function. And this function is able to use the module because the module is a sibling of the function called makeTrafficLight. Okay, and when I use this module, I'm able to use the enum called TrafficLight, which is a public enum. That's why I can use it directly by using the module name followed by 2 colons, followed by the enum name, followed by the variant. Okay. So let us see the execution. Okay, you can see that I can really call the makeTrafficLight function, which is stored in the lib.rs file instead of on the main.rs file. So you can see that the variants can be printed out by using the printLine macro. Okay. Now we can talk about the use keyword that we already demonstrated a little bit. We can bring the public items into the current scope so that we can use them directly. And both the relative and absolute paths can be used. So when we use the use keyword, we can use them for the relative path and the absolute path. Okay. So let us see this example. In the main.rs, I have these things. And you can see in the middle that I have a sentence called use, outer module, public inner, public function. So we can use this relative path to really locate the public function so that it can be used in the upcoming main function. So you can see that the main function just calls the public function directly without using the relative path that we showed beforehand. So the relative path is able to be replaced by the use keyword, which is put on top of the main function. Okay, so before the main function executes any new code, the main function is already able to recognize the public function because we have already used the use keyword to bring this function to the current scope. So let us see this example by running it now. Okay, we can see that we have no errors coming out. That means the relative path is able to help me locate the public function, which can be used directly by the main method because the main method has already understood that the function is already brought to the current scope. Okay? So let me play with it. Okay, you can see that this sentence has been printed out. That means the use keyword is able to help me bring this public function to the current scope. Okay. Let us see another example that uses the absolute path, which is actually similar to this previous one. The main difference is that I just used the binary crate as the beginning. That means I use the absolute path instead of the relative path for the previous example. Okay, so let me try to play with the program. Okay, you can see that the statement can be shown up here. That means I can use the absolute path to locate the public function. Okay. Now, let's see the way of using the keyword use in an idiomatic way. When we bring a function into the current scope, the path stops at the module that contains the function. It is clearer in this way to show the source of the function. So this is a bit abstract. I'm going to use an example to show you the idea. In the following example, we see that the public function comes from the inner module. So the idea is to use the relative path in this way. Outer module, and then followed by the public inner. And I don't bring the public function into the current scope immediately. Instead, I can use the public inner followed by the public function, so people can understand that this public function comes from this public inner module. Okay. So this is the way of using the keyword use idiomatically. Okay. So let me see this example by running it for you. Okay, you can see that there is no problem with the code. And we can use this longer line to really tell people that this function called public function comes from a module called public inner, sorry. So let me play with it now. Okay, you can see that the statement has come out as usual, okay? So that means we can use the relative path in this way to show the shorter path that we can manipulate it further to show the public function, which is inside the public inner module. And in this way, the source of the public function is clearer than before. When we see the previous example, we don't really know the source of the public function, but in another way, like this one, we can see that, oh, it is coming from the module called public inner. Okay. Now, let's talk about another section about splitting the modules into different files. In order to show the long code more clearly, we can try to separate the code into several files other than using just the main.rs file or the lib.rs file all the time. After we separate the long code into different files, we need to make sure that they can be joined again in the main.rs file. The joining can be achieved by using the use keyword and the correct paths that indicate the function locations correctly. The overall effect of the joining is that we can make sure that all the code is linked again, as if all the code is from a single file, which is the main.rs file. So let's see an example that doesn't have the lib.rs file involved at the beginning. Suppose we already have a project called My School. I already prepared it here. Okay, My School is here, and I already posted the code here. The code is as follows. It is only in the main.rs file, but not in the lib.rs file. So this example involves just one main file, okay? So in the main file, I have a module called school, and in the module, I have a module called teacher and a module called clerk. And for each of these modules, there are some functions for each of the teacher or clerk modules. And in the same file, I have the main function, and before I have the main function, I have to bring the teacher and clerk modules to the current scope. And I can do it in a single row by using the curly brackets to embrace all my modules that I need to use before I go to the main function. Okay, so I say use school, teacher, clerk. That means I go to the school module, and then I bring the teacher module and the clerk module together into the current scope. Okay, and in the main function, I can just use the functions for the teacher and the functions for the clerk. Okay. In order to split this long code, I can have an idea like this one. I can split the code into the following files. The binary crate name is the same as the project name, so the binary crate name is my school. And the module tree is as follows. I have my school crate, and under it I have a source file folder. And in the source file folder, I have the main.rs file, and then the school.rs file. That helps me store the information of the school. And also I have a folder called school. And in the school folder, I have the teacher.rs and the class.rs file. And we have to notice something when we build up this module tree. The module name must be the same as the source file name. So the module name called my school is the same as the project name, which is also the source file name. Okay, the source file name is my school, which is the same as the module name here. Okay. And also, when a source file calls other modules stored in other source files, we make a folder and put the source files to be called into this folder. So we are talking about this school folder. In this example, the school folder would represent the outer module in the original main.rs file. So this folder is actually representing the outer module, which is this one. So I can use a file to represent the module. And in this module, I have 2 further modules. Okay. So let me try to put the code into different files according to this module tree. So the first file is called the school.rs. I need to make a new file in the source code folder. And in this source code file, I can just have 2 lines. So I'm going to bring the teacher module and the class module into the school.rs file. And the second one to do is the teacher.rs file. I also need to make a new file in the source code folder. And then I also need to make a file for the class. So I have to make a class.rs file. And then I can copy these lines to the class.rs file. So you can see that the functions for the teacher and for the class can be included in these 2 files. And these 2 files can be called by the school.rs file, which has already contained the module for the teacher and for the class. And then I can go back to the main.rs file to do the rest. You can see some error coming up because I haven't really created the folder to store the teacher.rs and class.rs files. Now I need to really move the 2 files into a school folder. Okay, you can see that there is no error coming up. The reason is that I have already put the school folder into my module tree, and for the school folder there are 2 files. So this school here refers to this folder actually. Okay, and in this folder there are 2 modules to use, and in the module tree I have a school.rs file that contains the teacher module and the class module, and they would just refer to these 2 rs files for the class and for the teacher. Okay, and I can just use school teacher class to really bring the teacher.rs file and the class.rs file into the module tree, and I can just use these functions of the class and of the teacher directly. Okay, so the main function is like this. I can go to the teacher module that is already brought by the school.rs file, and when the teacher module is brought to the current scope, I can just use the functions for the teacher. That's why I can do the teach and prepare lesson functions for the teacher. And the same for the clerk, I can do the write docs function and the contact schools function shown in the clerk.rs file. Okay. So let me try to play with the whole program. Okay, for the teacher, I can just say that the teacher is teaching now, because that teacher has such a function in the teacher.rs file. Okay. And for the second line here, when we want to prepare a lesson, the teacher is able to do so by saying this statement from the printline macro. And for the clerk, here, I need to write the docs, and the write docs function can be executed. Same for the contact schools function. So the two functions will just print out two strings by using the printline macro. Okay. So we can see that we can separate the long code into a number of files, and we have to notice that we need to put the module name into a folder, and that folder can store the original sub-modules or the inner modules. Okay. And now we can see another example of splitting the long code into several files when the library.rs file is included initially. Suppose I have a project called lib.example, which is this one. Okay. I already moved to this particular project. And this name also becomes the library crate name and the binary crate name that is already discussed in the previous part of this section. And the main.rs file and the lib.rs file are as follows. I already put the file content onto the rs files already. So let me take a look. So for the lib.rs file, I have just got some functions that are public and a function that is private. And this private function will be called by the public function, okay, called in direct access, okay. And for other functions, they are public, so you can expect that the main function can just call them directly. And in order to bring the functions stored in the lib.rs file into the current scope, I have to say use lib.example : asterisk. This asterisk is meaning the global action. And this meaning is shown here. We can use the glob operator, which is an asterisk, to include all the items in a module. So when I want to include all the items in the lib.rs module, I just make an asterisk so that all these functions can be brought to the current scope. Okay. And I can also have some other way to bring the functions into the scope. I can use the as keyword to make an alias. So I can say use lib.example func from lib2 as func2. Func from lib2 is this one. So I have such a function here in the lib.rs file, and I can just make it as a new name called func2 func2. So in the main function, I can just use this new name to represent the original function called func from lib2 stored in the lib.rs file. Okay, it means that I can make an alias to a previous function. Okay, and in the main function, I just call all of those functions one by one. And if we want to put some of the functions in lib.rs into a separate file, the module tree can become the following one. That means if I think that the lib.rs file is too long, and I want to put some of the code into other files, I can have an idea like this one by setting up such a module tree. Okay. I have the source code folder, and in the source code folder, I have the main.rs and the lib.rs as usual. Additionally, I have one more rs file called my func. So I want to put some of the functions from the lib.rs file into this particular rs file. Okay. And I can repeat something here. we can use the as keyword to make an alias of a path. That means this path can be replaced by this alias called function2, okay? So let me see how I can do it by following this module tree. I can make some changes to the lib.rs file so that some of the functions will be put to the myfunc.rs file instead of putting all of them together in just the lib.rs file. So for the library.rs file, I just rename 2 functions only. And before renaming the 2 functions, I have to make a public module called myfunc so that the library.rs can refer to the new file called myfunc.rs so that other functions stored in the myfunc.rs can be brought to the scope as well. And then I make a new file called myfunc.rs, which is put in the same directory called src. Okay, you can see that some of the functions originally in the lib.rs file are put to the myfunc.rs already. And in the main.rs file, I need to make some changes. The idea is to use the use keyword so that I can bring the modules to the current scope. I can go to the library create and then I can get the function from lib, which is already stored in the lib.rs folder file. And I can also bring the myfunc module, which is already declared in the lib.rs file, okay. And after linking to the myfunc module, I can do the myfunc.rs files here, okay. I can play with the functions stored in the myfunc.rs file later. And then I can just do the action of bringing the myfunc from lib2 function to the scope, and I can change it to func2 as the alias, okay. Okay, you can see that myfunc is already brought to the scope by this statement, myfunc, so that the function content stored in the myfunc.rs file can be brought to the current scope. And I can just pick up one of the functions called func from lib2 in the lib.rs to make it have a new name called func2. And you can see that the myfunc module can be brought to the scope so that the public function stored in it can be called. And also the indirect access function stored in the myfunc.rs file can also be called. And additionally, the private function which is not declared as public can also be called by the public function named indirect access, okay. So these 2 lines are already understood. And of course, I can just call the functions from the lib.rs file, which is the first one, and the second one, which is already named as another alias shown here, okay, called func2. So let me try to play with the code. Okay, you can see that all the things are executed pretty smoothly. For the first part here, public function, I can print out this statement, which is the first one here, okay. And for the second line, I can do the indirect access function, which is doing this sentence. And this one is shown here. And you can see that I can also call the private function, which is not a public function. Okay. The private function content is shown here, okay. And after that, I can run the func from lib, which is stored in the lib.rs file. And this function is just making this sentence to come out. And for the alias part called func2, I can just refer to the func from lib2 function, and I can just print this line on the terminal, okay. So you can see that all the functions can be executed pretty well by using a new file called myfunc.rs. The key idea is to just link the myfunc module into the lib.rs file, and then we can just use the content from the myfunc.rs file in the lib.rs file. This is the end of the Introductory Rust tutorial. I hope everyone would have learned a lot of knowledge about Rust language. Feel free to comment on my video and give me a like and share the video and subscribe to my channel. Thank you for your support of this video.